Python is nowadays one of the most popular, if not the most popular programming language. And there's actually one reason for it. So it's not the Python standard library, and it's also not the performance. So there are other languages that are faster actually. Python is so popular because the ecosystem of add-on libraries and packages has steadily grown in the last couple of years. And today there exists an outstanding quantity and quality of add-on packages and libraries for scientific and numerical purposes, for data science, data handling, and data manipulation, and also for statistics, regression, data visualization, and last but not least, for machine learning and deep learning. And if there's one key message in this course, then that we should use the add-on packages and libraries whenever possible. So there's no need to reinvent the wheel. However, there's one pitfall when using these high-level packages. So typically we do not see what is going on in the background and in the underlying code. And therefore it can easily happen that we do something wrong. And sometimes we do not even recognize it. So it's even more important to learn and understand and master these packages in a careful and comprehensive manner. And we have already worked with an add-on library, so the matplotlib library for data visualization. And here's another example, so the math module for advanced math workflows. And first of all, we have here a time value of money problem. We have the present value of 100, and we want to calculate the future value in 2 years. And we have an interest rate of 3% per year. And then we can calculate the future value with the present value times the compounding factor to the power of 2. So this is actually an exponentiation, and there's also a specific function in the math module. But first of all, we have to import the math module with import math. And then actually we can replace f to the power of n with math.pow. And here we can actually then define that we want to have f to the power of n. So let's have a look here. So here we can pass x and y, and the function returns x to the power of y. And then we also multiply with the present value, and by doing so we calculate the future value. And of course this gives you the same result. And now let's assume that the future value and the present value are given, and we have here an investment period of 2 years. So if you want to calculate the underlying interest rate, then we have to take the square root. And actually there's also a function for the square root in the math module, so math square root. And here we pass the future value divided by the present value. And finally, if you want to calculate the interest rate, then we have to deduct 1. And here we get 3%. And of course, there are also other math functions. And for example, we can calculate the sinus of 3. And this gives 0.14. And we can also get the Euler number with the math.e. So it's 2.718. And we can also get pi. It's 3.14. And actually you might question yourself, so what is the best way to import the libraries, packages or modules? So here we imported math, but we can also import a package or library and define an abbreviation. So we could also import math, and then we have the keyword s. So import math as ma. And then instead of coding math.py, we can also get pi with ma.py. Alright, now let's restart the kernel here and let's start from 0. So we haven't imported math. And first of all, let's recalculate present value, future value, and so on. So we haven't imported math, so math.sinus does not work. So the name math is not defined. And actually we have the option to import the complete math module, so we import math. Or we could only import certain functions of the math module. So for example, we could say that from math, we import the square root. And then we can calculate the square root and the underlying interest rate simply with the square root of future value divided by present value. However, here it's important to understand that we didn't import the full math module. So for example, math.py does not work. And also we cannot calculate the square root with math.square root because we didn't import the complete math module, so we only imported the square root. And finally, we could also use a customized abbreviation for square root. So we could say that from math, import the square root as SQ. And then we could actually calculate here the interest rate simply with SQ. However, I highly recommend that you follow the conventions and use the abbreviations that the vast majority of Python coders use, because this improves the readability of your code for others. So when everybody follows the conventions, it's easier to read the code written by others. And one good example is actually the NumPy package. So the convention is that we import NumPy as NP. So I highly recommend that you always import NumPy as NP. And we will actually see the power and the functionality of the NumPy package in the next videos and throughout the course. So no need to give you an overview here, and just a simple example. So also the NumPy package. So NumPy stands for numerical Python, and it is designed for numerical operations with numbers. And therefore it also offers some math functions. And also with NumPy, we can calculate the square root. And we can do this with np.square root. And also here we can pass future value divided by the present value. And this also gives 3%, so -1. And finally, we can also perform exponentiation with np.power. And let's have a look here. So here you can pass x1 and x2, and actually NumPy returns x1 to the power of x2. And also here we can calculate the future value. Alright, thanks for watching, and I'll see you also in the next video. Bye. This is an introduction to NumPy arrays, and the same as lists, NumPy arrays are also collections or sequences where we can store many elements. And actually NumPy arrays are much more functional and powerful than lists when we have homogeneous data. So if we only have numbers, then we can do a lot of more things with NumPy arrays than with lists. And we will see this in a minute. But first of all, let's import NumPy as NP as always. And now let's assume that we have some kind of cash flow projections for the next 6 years. So for example, 50 in 1 year, 100 in 2 years, and so on. And as always, we create here a list with the 6 elements and save the list in the variable CF. So that's the list here. And then we can actually convert the list into a NumPy array. And we can actually do this by passing the list inside the parenthesis of np.array. And by doing so, we create a NumPy array, and we save the NumPy array in the variable CF array. And here in our output, we can see a NumPy array. And the word array indicates that this is a NumPy array. And we can also check the data type with the type function. And here we can say that it's a NumPy ND array. So we will see later what ND array means, but it's sufficient to know that here we have the NumPy array, which is a sequence of elements or values. And actually we have already seen some pitfalls of lists. So it's actually pretty hard to perform element-wise operations. And let's assume that our projections changed. And there's an additional fixed cost of 20 per year. So from each and every element in our list, we have to deduct 20. And we have seen with lists that this is not possible with the following code. So CF minus 20 does not work. And alternatively, let's assume that we changed our projections and there's some positive news that allows us to increase our projections by 10%. And it would be great to actually multiply each and every element with 1.1. But with the lists, this is actually not possible. However, we can multiply a list with an integer, but actually this is not element-wise operations. So by multiplying the list with 2, we actually create 2 copies of the list, and then we concatenate the 2 copies into one list. So here we actually kind of doubled the list. So if we want to perform element-wise operations with the lists, then we have to use a for loop. So we create the list CF new, and then we iterate over all elements in CF, and we deduct 20 from each and every element, and then we append the new values to the new list here. So here we have all elements decreased by 20. And now let's come to NumPy arrays. And NumPy arrays actually allow element-wise operations. So to deduct 20 from each and every element in our NumPy array CFA, we can simply code CFA minus 20. And here we have all elements decreased by 20. And of course, we can also increase all elements by 10% by multiplying the NumPy array with 1.1. And of course, also we can double each and every element, so this is no problem. But also here it's important to understand that so far we didn't modify the NumPy array CFA, so it has still the original elements and values. So far we have used a single scalar value, so we reduced each and every element by 20, or we increased all elements by 10%, but now let's assume that we made a more detailed projection. And it turns out that we should increase the first cash flow by 10, then the second cash flow by 20, and decrease the third cash flow by 10, minus 10, and so on. So we create here the new NumPy array additional cash flows. So now we have 2 NumPy arrays, and then we can add 2 NumPy arrays, and actually NumPy performs here element-wise or vectorized operations. So we could also say that these 2 NumPy arrays are vectors. And if you recall some high school math, then you might remember that we can add or subtract vectors. And actually adding or subtracting NumPy arrays works in the very same way. So let's add CFA and add CF. So now we have here 60, 120, 110. So maybe let's print out again CFA. So what we actually did here, we added the first elements of the NumPy arrays, so 10 plus 50. Then we added the second elements, 20 plus 100. Then the third elements, minus 10 and 120, and so on. Alright, and actually NumPy arrays have many methods and also attributes. And one attribute is the dtype. And here we can actually check the data type in our NumPy array. So the data type of the elements. And here it's integer. So we have seen that with NumPy arrays we can perform element-wise or vectorized operations. And this gives us much more functionality than lists. However, there's one major drawback. So we have learned before that in lists we can store many elements with different data types. So for example, here we can create the list L, and we have an integer, we have float, integer, float, we have a Boolean value, and we have a string. But this we can do here with lists. However, NumPy arrays only accept one data type. So now let's try to convert the list L into a NumPy array. And here we can see in the output that each and every element is a string. And we could actually say that the data type string is the lowest or least common denominator here. So actually we can convert integers and floats to string and also Boolean values. However, we cannot convert a string into an integer or float. So the lowest common denominator data type is here string. And therefore we end up with a NumPy array of strings only. And we can also check this explicitly by iterating over the NumPy array. So of course we can also iterate over a NumPy array with a for loop. And we check for each and every element in A and print out the data type of the element. So let's have a look here. And here we have string. So that's the pitfall of NumPy arrays. So we have to make sure that we have only one data type. And actually NumPy arrays work perfectly if we only have numbers, so integers or floats. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video we will see that indexing and slicing NumPy arrays works in the very same way as indexing and slicing lists. And also here the concepts of zero-based indexing and negative indexing apply. So first of all we import NumPy as NP, and then we create a NumPy array by passing here a list with 6 elements or cache flows to the NumPy function np.array. And actually we save the array in the variable cf. And then we can actually index for the very first element at index position 0, so 50, also here with square brackets, and we pass the index position 0. And we can also get the third element at index position 2, 120. And negative indexing also applies, so we can get the last element 300 at index position -1. Or we can also get the third last element 150 at index position -3. Next we can also slice from position 2 until 4 exclusive, so 2 inclusive and 4 exclusive. And we get actually here the third element at index position 2 and the fourth element at index position 3. Then we can also slice the NumPy array for the first 3 elements, 50, 100 and 120. Then we can also get all elements starting from the third element at index position 2 until the very last element inclusive. So here we have 120, 150, 200 and 300. Then next we can get all elements until the very last element excluding the last element. So all elements except the very last element at index position -1. So here we are missing 300. Then we can also get the last 2 elements by slicing from the second last till the very last. So here we have 200 and 300. And then we can also get every second element. So for example, first of all, we want to get the elements from index position 1 till 4 inclusive, but only every second element. So here we have 100 and 150, starting from the second element and every second element, 100 and 150. And finally, we can also reverse the order by having all elements and then every -1 element. So here we are starting with 300 and ending at 50. Alright, thanks for watching, and I'll see you also in the next video. Bye. We have already seen one of the most powerful features of NumPy arrays, vectorized or element-wise operations. And in this lecture we will perform some more advanced vectorized operations. For instance, we will calculate the net present value of an investment project with only one line of vectorized NumPy code. So we import NumPy, and let's assume we have here projected cash flows. Then we have already learned that we can increase all elements by 10%. And we can also add 20 to each and every element. So here we multiplied the NumPy array with a scalar value, or we added a scalar value. But we can also add 2 NumPy arrays. So let's create a second one. And let's add both NumPy arrays. And here we can also perform element-wise or vectorized operations. So here we added the first elements, 50 plus 10 is 60. The second elements, 100 plus 20 gives 120, and so on. All right, now let's go back to XYZ company's investment project. So we want to buy an additional machine for 200, and we have some inflow projections here. And we want to calculate the net present value based on a required rate of return of 6%. And first of all, we can create here the NumPy array with the cash flows. And we have the interest rate and the discounting factor. And then we also create a NumPy array with the discounting periods. So we want to discount minus 200 by 0 periods, 20 by 1 period, and so on. And we can actually simply discount each and every cash flow by its respective period with vectorized NumPy code. So we have here our CF NumPy array divided by f to the power of n, and n is here the NumPy array with the discounting periods. So let's simply run the cell here. And here we get another NumPy array with the present values for all cash flows here. So the present value for minus 200 is minus 200. Then the present value of 20 discounted by 1 period is 18.86, and so on. So this is the NumPy array with the present values. And we can also save the NumPy array in the variable PV array, present value. And then finally, to get the net present value, we simply have to take the sum over the present values. And actually also NumPy arrays have plenty of built-in methods. And one method is the sum method. And here we sum up all elements in the NumPy array. So let's sum up all elements here, and let's assign the result to the variable npv. And no surprise, we get here the same result, 38.71. And actually we could also have this in one line of code. So here we calculate the NumPy array with present values. And we could create here parentheses and take then the sum. So this is here in one line of code. And we get the net present value. And finally, we can also compare this with the code that we needed when we used lists and for loops. So here we have actually a couple of lines of code. And this is here definitely an improvement with vectorized NumPy code. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video we will change elements in a NumPy array, and we learn that NumPy arrays are mutable objects. However, there's one major and really important difference to lists, and I will show you this difference in this and the next lecture. First of all, we import NumPy, and we have our savings plan, so 100 today, 10 in 1 year, and so on. And we create a NumPy array and save the array in the variable CF. And now let's assume that today we do not want to save $100, but only $95. And we can actually change the very first element in the very same way as we change the first element of a list. So first of all, we index for the element. So it's here 100, and then we reassign the element and assign the new value 95. And let's check this. So here we have 95 as the first element. Next, let's assume that in the future years we want to save a constant amount, so 40. And therefore we can actually change the elements here starting from the second element. And with lists we have learned that we can assign here a list with new values. So for example 40 So this also works with NumPy arrays. However, NumPy arrays also allow so-called broadcasting. So now let's assume that we want to save 45 in the next year, so in each and every year. Then instead of creating a list with 5 times 45, we can use here broadcasting and simply assign here a scalar value to the 5 values in our NumPy array. So this works with NumPy arrays. And here we have 45. Next is a short repetition. We can add 20 to each and every element. However, it is important to understand here that by doing so, we create a new object. So we didn't actually change the original NumPy array. So here we have still the old numbers or the old values. And actually, if you really want to change CF, we have to use here variable reassignment. So we assign CF to the new object where all elements are increased by 20. Now let's come to mutability of NumPy arrays. And here we create a NumPy array with our savings and save the array in the variable CF1. And now let's assume that we create another variable CF2. CF2 equals CF1. And if we change now the very first element of CF1 to 95, then also CF2 changes. So same as lists, NumPy arrays are mutable, and let's have a short look how this works in detail in memory. So here we have our memory, and we have the following code. So we create a CF1 and the object here, the NumPy array, and CF1 is pointing to the NumPy array. Then we create another variable CF2, and CF2 is also referencing or pointing to the same object. And now if we change the very first element of CF1, then we actually change or mutate the object to 95 in the first element. And therefore we have also changed the object that CF2 is referencing or pointing to, because it's the very same object. And therefore we can say that NumPy arrays are mutable objects. Alright, now let's go back to our Jupyter notebook. And let's create the NumPy array one more time in CF1. And now let's assume that we want to create a CF2 with the same values, but we want to have CF1 and the CF2 pointing or referencing to different objects. So whenever we change CF1, we actually do not want to change CF2. And with lists, we have learned that we can use the following code. So we actually slice CF1 and slice for all elements. And by doing so with lists, we actually create here a new object. And let's try this also here for NumPy arrays. So we create a CF2, and actually CF2 has the very same values. And now let's change the very first element of CF1 to 95, and let's check CF2. And obviously we have also changed and mutated CF2, because CF2 is still referencing or pointing to the very same object as CF1. So by slicing CF1, we actually didn't create here a new object. And actually, if we want to avoid this, there's only one viable solution. So let's again create CF1. And now let's create a CF2 by using the copy method. And by doing so, we create a new object with the same values. And if we change now the very first element of CF1, then of course we didn't change CF2. So we have seen that slicing NumPy arrays can be a dangerous thing actually here. And in the next video we will go here more into details, so hope to see you there. Bye. This lecture shows one of the most commonly made mistakes, and actually one of the most painful mistakes when working with NumPy arrays. So when slicing NumPy arrays, the question is always, do we create a copy of the original object or a view on the original object? So that's a difference. And the difference has actually severe consequences. So let's import NumPy and let's have a look at an example. And again, we have our savings plan. And now let's assume that we want to slice the last 3 elements, 50, 30, and 25. And we want to store the last 3 elements in another variable. So for example, the variable last 3. So let's do this here. And now our plan is to play around with the slice here and to change maybe elements. But our intention is not to change the original object, so our complete savings plan here. And let's assume that we want to change the first element in our slice, so 50, from 50 to 55. Then we can do this here with this code. And let's check our slice here, last 3, so we have now 55. And actually I assume that we wouldn't expect that we also changed the original CF numpy array. So we would expect to have still here 50, but this is actually not the case. So we have here also 55. And this is actually a complete different behavior than we have seen with lists. So let's do the same operations with a list. So we have here the list CF. Then we create here a slice with the last 3 elements. And then we change an element or a value in the slice to 55. Then, of course, we have changed the slice, but we did not change the original list. So still we have here 50. So now let's have a detailed look what happens in memory when we slice a numpy arrays. So here we have our memory, and we have the following code. We create a numpy array and assign the variable cf1. And then we slice the numpy array and save the slice in the variable last 3. And it's really important to understand here that we do not create a new object here. So here we have the variable last 3, and actually the variable last 3 is referencing or pointing to the last 3 elements in our original numpy array. So to say, this is a view on the original numpy array, a view on the last 3 elements. And actually, if we change now the very first element of the last 3, so 50, then we also change the original numpy array. So here we have changed the original numpy array and also the slice the last 3. Now let's assume that this is not our intention. So we want to create a different object, last 3. And if we change the slice, we do not want to change CF1. And there's one solution that we have already seen. So again, we create the CF1. And now we slice CF1 and create the last 3. And we have to use the copy method here. And by using the copy method, we create actually a different object or a new object with the last 3 elements. And actually the variable last 3 is referencing or pointing to the new object. And of course, if we change now one element in the slice in last 3, then we do not change the original numpy array CF1. Alright, now let's go back to our Jupyter notebook. And let's follow the solution here. So again, let's create the numpy array here, CF. And we create here the slice, but we use here the copy method. And now if we change the very first element to 55, then of course we have changed the element in the slice. But we did not change the element in the original numpy array CF. So still here we have 50. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video I will show you some helpful numpy array methods and attributes. So we import numpy SMP, and then we are working with our investment cash flows so that we save as a numpy array in the variable CF. And then we could determine the maximum element in our array with the Python built-in function max. And here we pass the CF to the max function. And the highest element is 100. But there's also a built-in method for numpy arrays max. So let's have a look here. And it says returns the maximum along a given axis. So here we only have one axis. So we have here a one-dimensional array. And let's run the cell, and also here we get 100. And of course we can also determine the minimum value with the min method. Next we can determine the index position of the maximum element. So the index position of the element 100, and it should be 0, 1, 2, 3, and 4. And we can actually do this with the argmax method. So let's have a look here. So it returns indices of the maximum values, or the index here. And here we get 4. And we can also get the index position of the minimum element, so minus 200. And we should get index position 0. So here we have the argmin method. And we can also sum up all elements in our NumPy array with the sum method. And we can also calculate the cumulated sum. So we start at the very first element, and then we add another element and another element. So we start with minus 200, then we have minus 180, minus 130. And we've already seen that our investment project breaks even in year 4. So here we turn positive. So before with lists, we have seen that we need a for loop to calculate the accumulated cash flows. But here we simply have a method. And let's store here the accumulated cash flows in the variable array. Then let's import matplotlib. And actually visualizing NumPy arrays works in the very same way as visualizing lists. So first of all, we determine a fixed size of 12.8. And then we simply pass the array, our NumPy array, with the accumulated cash flows to the plot method. And finally, of course, we have plt.show. So this is a line plot with the cumulative cash flows, and we have here the break even between year 3 and year 4. Next, with the sort method, we can also sort the elements in our NumPy array from low to high. And it says here that the sort method sorts an array in place. So we change the object in memory, so we do not create a copy. And let's have a look here. So here we have now the order from low to high. Next, let's add a float to each and every element, for example 0.0235. So now we have float objects here, or floats in our NumPy array. And with the round method, we can actually round each and every element, and we can determine the number of decimals. So here we define 2 decimals. So let's have a look here. 20.0235 gives 20.02, and so on. Now let's come to an attribute, and we have the size attribute. So here you can identify that this is an attribute, as we do not have parentheses, so we cannot kind of call an attribute like a method or a function. And the size simply returns the number of elements in the NumPy array CF. And last but not least, we can determine also the shape of our NumPy array with the attribute shape. And actually here in this case, so we have here a one-dimensional NumPy array. But later in this course, we will see that we can also have two-dimensional NumPy arrays with rows and columns. So there, for example, we could have a shape of 3 rows and 4 columns, but in a one-dimensional NumPy array. This is pretty straightforward. So here we have a one-dimensional NumPy array with 6 elements. So these were a few methods that are available. So let's have a look here, cf dot, and let's press the tab key. And here we can see that we have many more methods and attributes. All right, thanks a lot, and I'll see you also in the next video. Bye. NumPy universal functions are pretty similar to Python built-in functions. And we can actually apply universal functions not only on NumPy arrays, but also on other collections and sequences like lists. So universal functions allow us to perform element-wise operations and broadcasting, not only on NumPy arrays, but also on lists. This sounds complicated, but let's have a look how it works. And we import NumPy. And then we create the list CF with some numbers. And then actually we can perform an element-wise operation and take the square root on each and every element with the NumPy universal function np.square root. So let's have a look here, and here we can see that's a universal function, and it returns the non-negative square root of an array. And this works actually element-wise. So let's run the cell here. And here we get for each and every element the square root, and the output is here an array, so not a list. Next, we can exponentiate each and every element, so we can calculate e to the power of the element by passing cf to the NumPy universal function np.exp. So here we have the results, and we get pretty high numbers here, so this is in a scientific format. And we can also square each and every element with the universal function np.power, and we pass cf, and we want to square each and every element by passing here 2, but we could also raise each and every element to the power of 3, 4 or whatever. So let's have a look here. So the first array elements are raised to the powers from the second array element-wise. So let's run the cell here, and here we get, for example, 100 squared or 10 squared and so on. Next, let's assume the following list with floats. So we have cf1, and with the NumPy universal function np.abs, we can actually return the absolute value of each and every element. So let's have a look here. So abs calculates the absolute value element-wise. And let's run the cell here. So here we get plus 200, plus 20, and so on. And we can also round each and every element in our list. And we can do this by passing the list cf1 to the function np.round. And we can determine the number of decimals. So for example, here 1. So for instance, we rounded 20.53 to 20.5. and 70.87 to 70.9. Next, we can increment each and every float number to the next higher integer with the function np.ceil. So let's have a look here. We have minus 200.6, and the next higher integer is minus 200. Then we have 20.53, and the next higher integer is 21, and so on. And we can also round all floats to the next lower integer value with np.floor. So we have minus 200.6, and the next lower integer value is minus 201. Then we have 20.53, and the next lower integer is 20, and so on. Alright, this were some NumPy universal functions, and there are many more. So in particular for math and scientific purposes. Thanks for watching, and I'll see you also in the next video. Bye. Earlier in the course we have seen that we can check for each and every element in a list whether the element meets a certain condition or not, and we combined a for loop with a conditional statement. And finally we were also able to create a new list containing those elements that meet the condition, and another new list with those elements that do not meet the condition. And actually these workflows are way easier with NumPy arrays. So we import NumPy, and we have our investment project here stored as a NumPy array in the variable cf. And now let's assume that we want to check for each and every element whether the element is positive or negative, so whether it is an inflow or outflow. And actually we can simply do this with the following code. So cf smaller 0. So we check for each and every element whether the element is negative. And actually we get as an output also here a NumPy array with Boolean values. Therefore this is also called a Boolean array. And we can see here that we checked element-wise whether the elements are negative or not. So minus 200 is negative, and we have a true. And all of the other numbers or elements are positive, and therefore we get a false here. And actually we can also store the Boolean array here in the variable negative. And the same we can also do for the opposite. So we can check for each and every element whether the element is greater than 0, so positive. And we can store the Boolean array in the variable positive. So this is, in this case, exactly the opposite. So we get only a false here for -200 and trues for all of the other elements. And now let's assume that we want to create one array with all negative elements and one array with positive elements. So this is also called conditional filtering, and this works pretty well here with NumPy arrays. So we have here our NumPy array CF, and then actually we slice our NumPy array. So we open here square brackets, and we pass the respective Boolean array. So here we pass the Boolean array negative, and here we get the array with only negative numbers. So what actually happened here, we sliced our array CF and we passed the Boolean array, and NumPy actually only returned these elements here where we have corresponding truths in the Boolean array. So here we have only one true in the very first, or for the very first element, and therefore the output is only the very first element -200. And the same we can also do for all positive elements. So we pass the Boolean array positive to the CF NumPy array. And actually NumPy returns back all elements except the very first element where we have a false here in the Boolean array positive. And of course we do not have to save the Boolean array first in a variable. So we can directly code the following. So we can actually filter the NumPy array CF for all elements that are negative or less than 0. And actually then we can save the resulting NumPy array in the variable negative. So only -200. And the same we can also do for positive elements. So we filter CF for all positive elements greater than 0. And finally, you might question whether we create here a new object or only a view on the original NumPy array. So it's actually not for granted that we created here a new object. And therefore, let's try this out. So we could actually change the very first element in the NumPy array positive to 30. So now let's have a look here. So we changed here the element to 30. And let's also check our original NumPy array CF, and still we have here 20. So by performing conditional filtering on NumPy arrays, we actually create new objects. Alright, thanks for watching, and I'll see you also in the next video. Bye. Alright, this lecture is on advanced filtering, and it is often the case that we have to filter data based on more than one condition. And we have already learned that we can link many conditions with logical AND, logical OR, and NOT. So let's have a look at an example, and let's assume that we are working for the XYZ company, and that we are responsible for an investment project with the following projected cash flows here. So first of all, we import NumPy, and then we have our projected cash flows. And actually in larger companies, it's quite common that the controlling or risk department asks for all projected cash flows that are either negative or very large. So large positive or large negative. And in our case, controlling asks to filter our projections for all negative cash flows and all cash flows that have an absolute value greater than 60. So we have two conditions, and at least the one condition must be met. So either the cash flow is negative or very large. And now let's create two so-called filtering masks. So mask 1 and mask 2. And these are actually Boolean arrays. So mask 1 is actually the array where we check for each and every element whether the element is negative. And then we check for each and every element whether the absolute value is greater than 60. So first of all, we calculate or transform into the absolute value with the NumPy universal function np.abs. And then we check whether the elements are greater than 60. So we want to filter out all elements or all cash flows where at least the one condition is met. So the very first cash flow minus 200 meets both conditions. Then for the second we have a false, also for the third. And then for the next two cash flows we have one true. So at least one condition is met. And finally for the last condition we have two falses, so no condition is met. Alright, now let's link mask 1 and mask 2 with an OR operator. And we can actually try to do so. And we get here an error message, and it says the truth value of an array with more than one element is ambiguous. So the problem is here that we combine two sequences with many elements with the OR operator, and this does actually not work. So with the OR operator we can simply combine a true and a false, or a false and a true, but we cannot combine sequences with Boolean values. But for these cases here we have bitwise operators, so let's have a look. And for example here we have the bitwise operator for logical OR, it's the pipe symbol. Then for the logical AND we have the AND symbol, and for NOT we have the tilde symbol. So now let's go back to our Jupyter notebook. And instead of combining mask 1 and mask 2 with OR, we combine them with the pipe symbol. And here we get a true for the first element, so true or true gives true. Then we get a false for the second, false or false gives false. Then also for the third element, false or false gives false. Then for the fourth and fifth element, we have false or true gives a true. And finally, false or false gives a false. So by combining here mask 1 and mask 2, we again create a Boolean array. And we can actually filter our initial cash flow array with the Boolean array here. And here we get the elements or the cash flows that we have to report to controlling. So minus 200, it's negative and large, and 70 and 100, which are large cash flows. And an alternative question now might be, so what are the cash flows that we do not have to report? So the opposite of this here. And one might think that we have to use here the NOT operator. But again, here we get an error message. And instead we have to use a bitwise operator, so here the tilde symbol. And here we get actually the inverted NumPy array. So for true we get false, for false we get true, and so on. And then we can also filter again our cash flow NumPy array. So the cash flows 20, 50 and also 50 we do not have to report to controlling. Next, let's assume that we have a closer look at the small positive cash flows. So if something is going wrong, then these cash flows will turn negative. And let's assume that we need to have a closer look at all cash flows that are between 0 inclusive and smaller than 30, so between 0 and 30 exclusive. And therefore we can create mask 3 and mask 4. And actually now we want to filter out all elements that meet both conditions. So greater than 0 and less than 30. And therefore we have to use here a logical AND. And also here the AND does not work. And instead we have to use the bitwise operator AND. And here we have all small positive cash flows. So in this case only 20. Alright, thanks for watching, and I'll see you also in the next video. Bye. Alright, in this video we will determine a project's payback period with NumPy arrays and np.var. So we import NumPy. And again we have X, Y, Z's investment project, and we have to calculate the payback period. So first of all we have here the projected cash flows stored in the NumPy array CF. And then we're actually interested in the accumulated cash flows, and we can actually create the accumulated cash flows with the method comeSum. So let's do this. And here we have the accumulated cash flows calculated with NumPy arrays, so pretty easy actually. And then we can check for each and every element whether the element is positive or not. So we can create a Boolean array here. And we can see that our Boolean array turns true here at index position 4. And that's exactly what we are interested in. So the first index position where we get a true. And actually we can do this with the NumPy function np.var. And here we have to pass a condition. So let's simply pass here the condition, or to say the Boolean array. And we actually get back here a tuple, so you can see this here with the outer brackets. And first of all, we have to select the very first element at index position 0, so this here. And here we have actually the index positions for the elements that meet the condition here. So it's index position 4 and 5. And we are interested in the very first element, so the first year where we break even. And therefore we select again the element at index position 0. So let's cross this out first. So here we have the array with 4 and 5, and then we select 4. And here we have index position 4, which is actually a year 4. So the payback period is 4 years. So that's actually one functionality of np.var, returning index positions for that elements that fulfill a certain condition. But there's also another functionality which we will see in 2 minutes. But if we only want to get the index positions of elements that meet certain conditions, then NumPy recommends to use np.non-zero. So let's have a look here. And np.non-zero returns the indices of the elements that are non-zero. And if you recall, so here we are creating a Boolean array with trues and false values. And actually true stands for 1 and false for 0. So np.non-zero returns the index positions of actually the true values. So let's have a look here first. And also here we get back a tuple, and we have to select the first element. And then we have here an array with the index positions that are non-zero. And we are interested in the very first element. Therefore, we have here 2 indexing operations, and 2 times we select the first element. And also here we have 4. And I said before that np.var also provides another functionality. So first of all, here we have to pass a condition. So we check for each and every element whether the element is positive. And then we can map for each element that is positive a new value. So for example, break even. And for all other elements that do not meet the condition, we map another value, so not break even. So let's have a look here. And instead of getting here trues and false, we get not break even, and finally here in year 4 and 5, we get break even. So with np.var, we can actually map alternative values based on whether elements meet a certain condition or not. And actually we can do the same for our initial cash flow array. So we can assign a positive to all cash flows that are greater than 0, and the negative to all cash flows that do not meet this condition here. And here we only get at index position 0, 1 negative, so minus 200 is negative, and all other cash flows are positive. Alright, thanks for watching, and I'll see you also in the next video. Bye. So far we created NumPy arrays manually by passing a list to np.array. However, there are quite powerful tools to create larger NumPy arrays. So first of all, let's import NumPy as np. And we've already seen that we can create a list, for example, with integers from 0 till 6 with a range object, and by passing a range object to the list function. And very similar to this, we can create a NumPy array with integers from 0 till 5 with the NumPy function np.arrange. And here we can pass, for example, 6. and we get all integers by default from 0 until 6 exclusive. So now let's assume that we want to create all integers from 1 till 10 inclusive. Then we can code here np arrange from 1 inclusive till 11 exclusive. And similar to the range function, there's also a third alternative. So we can say that we want to have all integers from 1 till 10, but only every second integer. So we can define here the step, and here we can pass, for example, a step of 2, and the default step is 1. So here we have 1, 3, 5, 7, and 9. And actually, in contrast to the range function, we are not limited to integers. So for example, for the step, we can also select a float 0.5. So here we have 1, 1.5, 2 until 9.5. And also for start and stop, we can have floats. So for example, from 0.1 till 1 with a step of 0.1. And here we get 0.1, 0.2 until 0.9. And now let's assume that we want to have interest rates from 1% till 15% at a step of 0.1%. Then we can do this here. And here we have 1%, 1.1%, and so on until 14.9%. So the stop point is always exclusive. However, if we want to create many values within a specified interval, so for example, between 1 and 10, and we want to have in total 10 numbers, then we can also use np.linspace. So let's have a look here. So here we have a start parameter and a stop parameter and a num parameter, and the default value is 50. And actually np.linspace returns evenly spaced numbers over a specified interval. So the specified interval is from 1 till 10. And here we can define that we want to have in total 10 evenly spaced numbers in that interval. And this gives here 1 till 10. But we can also have the default argument 50 here. So these are 50 evenly spaced numbers between 1 and 10. So in total we have 50 numbers. And again, for the start point and the end point, we are not limited to integers. So we can also have floats here from 1% till 15%. So here we have 15 evenly spaced interest rates, so to say. But we can also have 1000, so this is no problem. And there's actually one major application for np.linspace. And let's assume that we want to plot the sinus function in the interval from -10 till 10. Then we have to create many x values. So in total, we create here 1000 x values in the interval -10 till 10. So starting with -10, then -9.97, and so on. And in total, we have 1000 elements. And then we can create the y values. So for each and every x value, we calculate the corresponding sinus with np.sinus, and we pass here our numpy array x. And by doing so, we create a numpy array with 1000 values, and we save the array in the variable y. And now let's create the plot. So first of all, we import matplotlib as plt. And we create a figure with fixed size 12.8. And then we pass the x array and the y array to the plot method. So let's simply run the cell here. And this is actually the sinus function from -10 till 10. So here we have the x-axis and the y-axis. And we also have here a title, so the function sinus x. And last but not least, we can also create many ones with np.ones, and here we have to pass the number of ones that we want to have. So here in this case 10. And the same we can also do for 0. So we can create, for example, 10 zeros with np.zeros. Alright, thanks for watching, and I'll see you also in the next video. Bye. We've already learned that lists are collections where we can store many elements. And so far we had numbers, strings, and booleans in a list. But we can also put other lists into a list, and this is a so-called nested list. And now let's assume that we have 3 investment projects and with the cash flow streams. So we have project 1, project 2, and project 3. And the term is actually different for those projects. For project 1, we have the initial investment, and then we have 5 years of inflows. And for project 2, we have 4 years of inflows. And for project 3, we have 7 years. So let's save those lists in the variables project 1, project 2, and project 3. And then we can actually create a nested list with the 3 project lists here. And we save the nested list in the variable all projects. And here we can actually see the outer square bracket. So this is a list. And within the list, we have a list with the cash flows for project 1. Then we have another list with project 2. And a third list with the project 3 cash flows. And of course, this is here also a list. So a nested list, but it's a list with in total 3 elements. So we have 3 lists in the list. And then we can actually select the single elements of the list. So for instance, we can select the very first list at index position 0. And that are the cash flows for project 1. But we can also get the very last list at index position 2. Or alternatively at index position -1. And we can also create slices. So let's slice the nested list for the first 2 lists, or the first 2 elements. So here we have project 1 and project 2. And of course, you can also get the last 2 lists. And now we can also chain index operations, for instance, 2 index operations. And let's assume that we are interested in the initial investment for project 1. Then first of all, we can select project 1. So the list by passing here 0 at index position 0. And this gives actually the list for project 1. And then we can select the very first element. And here we have -200. So we simply chained here 2 index operations. Now let's assume that we are interested in the initial investment for all 3 projects. And it would be great if we can also do this here by chaining index operations, but this is actually not possible with lists. So we could use the following code. We could say that for all projects, so for all 3 lists, we want to have the very first element. But this actually didn't work, so we have here the list for project 1. And the reason is that the first index operation simply gives us all 3 elements of the list. And then we select the first element, so the first list. And in fact, to get the initial investment for all 3 projects, we actually need to use a for loop. And therefore, we create the empty list initial investment. And then we iterate over the projects or over the lists in the nested list. And for each list or for each project, we take the very first element, so in the investment, and append the investment to the list I0. And this is actually our desired result. So here we have the initial investment for the 3 projects. So as a summary, working with nested lists is pretty limited. And if we have kind of a 2-dimensional or tabular data, then we should better use 2-dimensional NumPy arrays. And this complete section is all about 2-dimensional NumPy arrays. Thanks for watching, and I'll see you also in the next video. Bye. Alright, in this lecture we will make our very first steps with 2-dimensional NumPy arrays. And it's 2 dimensions because we have rows and columns with numerical data. So first of all, let's import NumPy as NP. And we are starting with an easy case where we have 3 lists with the same shape. So we have here 6 elements in each list. And later we will relax this assumption. So we have the list CF1, CF2, and CF3. And we actually create the nested list NL with those 3 lists. So here we have a nested list. And then we can create a 2-dimensional NumPy array by passing the nested list to np.array. And we get actually a 2-dimensional NumPy array. And we have rows and columns. And each row is actually one project. So the first row is the project 1, the second project 2, and so on. And we have in total 6 columns. So the very first column, there we have the initial investments. And in the very last column, we can see the cash flows for the year 5. Now let's save the 2-dimensional NumPy array in the variable CFS. And let's also check the type. So this is a NumPy array as well. And there's the attribute shape where we can check the shape of the NumPy array. And here in this case, it's 3, 6. And this means that we have 3 rows and 6 columns. And now let's perform some simple indexing and slicing operations. So we can get the very first row and the very first project by having here square brackets, and the index position of the very first row, it's 0. So also zero-based indexing and negative indexing applies here. And we can also get the very last row at index position -1 or 2 alternatively. And we can also slice, so we can get the last 2 rows or the last 2 projects with 1 colon. And let's assume now that we want to get the initial investment for the very first project, -200. And we can do this by chaining indexing operations. So first of all, we can select the very first row and the very first project. And this gives here actually a 1-dimensional NumPy array. And then we can index for the very first element -200. So here we have chained and used the 2 indexing operations. But with 2-dimensional NumPy arrays, we can also do this in 1 indexing operation. And we can open here the square brackets. And we have here a comma. And on the left-hand side of the comma, we can define the row or the index position of the row or the rows that we want to slice or index for. And on the right-hand side of the comma, we can define the index position for the column or columns. So in our example here, we want to get the element in the very first row at index position 0, in the very first column at index position 0. And this also gives -200. All right, these were some easy and straightforward indexing and slicing operations. And in the next video, we will have a look at some more advanced indexing and slicing operations with 2-dimensional NumPy arrays. Thanks for watching, and I'll see you there. Bye. In this lecture, we will continue with some more advanced indexing and slicing operations for 2-dimensional NumPy arrays. And first of all, we import NumPy. And again, we have our 3 projects with 6 cash flows. And we create the 2-dimensional NumPy array CFS. And we have 3 rows and 6 columns. And we've already learned that we can simultaneously index and slice for rows and columns in 1 indexing operation. So we do not need to chain indexing operations here with 2-dimensional NumPy arrays. And we can simply open here square brackets. And now let's assume that we want to get the initial investments for all 3 projects. And that's actually here the very first column at index position 0. And therefore we code here colon. So we want to have all rows or for all projects, and then comma, and then we define that we want to have the very first column at index position 0. And here we have the initial investments, -200, -150, and -250. And of course, we can also get the very last column, 50, 40, 200, by selecting all rows and the last column at index position -1. Next, let's assume that you want to get the first 2 cash flows for all projects. So the initial outflow and the first inflow. And again, we want to have all rows. and then actually the first 2 columns, so colon 2. And this gives minus 200, minus 150, minus 250, 20, 25, and 10. Next, let's assume that we want to get the positive inflows for the last project, starting here with the second element at index position 1. And therefore we select the third row at index position 2. And we want to get all columns starting from the second element until the very last one. And finally, let's assume that we want to get for project 2 and project 3. So for the last 2 projects, the very first 2 cash flows. Then also we can do this here. So here we have the initial investments and the first positive inflow of the project 2 and project 3. So when indexing 2-dimensional NumPy arrays, we have the full flexibility and we can create slices or select elements or whatever. And now let's come to a more complex case. So let's assume that we have 3 projects with different terms. So in the first project, we have 5 years of positive inflows and in total 6 cash flows. Then for the second project, we have in total 5 elements. And for the last one, we have 8 elements. So let's create the 3 lists here. And then we create the nested list and pass the nested list to np.array. And this is obviously not a 2-dimensional NumPy array. So we have here an array with 3 elements. So the first list, the second list, and the third list. And we can also check this with the shape attribute. So we have a 1-dimensional array with 3 elements. And therefore we cannot index and slice for rows and columns. So this does not work actually. But there's a simple workaround, at least in our case. So for project 1, we simply have 0 cash flows in the year 6 and 7. And also for project 2, we have in the last 3 years 0 cash flows. And by adding here the zeros, we make sure that all projects have the same amount of elements, so in total 8. And now we can actually create the 2-dimensional NumPy array and save it in the variable projects. And we have actually the shape of 3 rows and 8 columns. And now again we can index and slice for rows and columns. So for instance, the very first column, so the investment amounts for all 3 projects. And instead of adding here the zeros and resizing the projects manually, there's also a better solution. For instance, here for project 1, so here we have 6 cash flows. But we have here the resize method, and here we can actually change the size or the amount of elements in our 1-dimensional NumPy array here. And let's have a look. So here we can define a new shape, and actually we want to have 8 elements. So by default NumPy adds here 2 zeros, and it actually does this in place. So we change the original object stored in project 1. And let's have a look here. So now we have added 2 times 0, and we have a shape or a size of 8. And for the sake of completeness, let's assume that we have passed 4 to the resize method. Then NumPy would simply cut here the NumPy array after the 4th element. So after 70 here. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture, I want to show you an additional option when indexing and slicing NumPy arrays. So we import NumPy, and then we create the NumPy arrays CF1, CF2, and CF3. And we also create the 2-dimensional NumPy array CFS. And first of all, let's focus on project 1 and CF1. And let's assume that we want to have the first element and the 4th element and the very last element. And with the NumPy arrays, we can do this by passing here a list of index positions. So we have here CF1, and we open the square brackets, and then we pass a list with the index positions of the elements that we want to have. So we have the very first element at index position 0, the fourth element at index position 3, and the very last element. And this works pretty well. And actually for lists, we do not have this option. And now let's come to our two-dimensional NumPy array. And let's assume that you want to have the initial investment for project 1 and project 3. And therefore we can open here the square brackets. And on the left-hand side of the comma, we can pass a list with the index position 0 and -1, so the first project and the last project. Alternatively, we can also pass here 2. And we want to have the very first column. So here we have -200 and -250. Now let's have another example, and let's assume that you want to have for the very first project the elements at index position 0, 2, and -1. Then we can pass here 0, comma, and for the columns a list with the index positions. And here we have -200, 50, and 50. Alright, thanks for watching, and I'll see you also in the next video. Bye. This is a short recap on how to change elements in a NumPy array and in slices of NumPy arrays. And actually for two-dimensional NumPy arrays, this works pretty much in the same way as for one-dimensional arrays. So we import NumPy, and we have our 3 projects, and we create the two-dimensional NumPy array CFS. And now let's assume that you want to change the initial investment for all projects to -200. Then we can actually do this by first of all slicing for the elements and then setting a new value, so -200. And let's have a look. So we changed or mutated the original object that is assigned to the variable CFS. Here we have now -200. Next, let's assume that you want to decrement the initial investments by -10. So it should be -210. And therefore on the right hand side of the equal sign, first of all we slice for the elements, and then we deduct 10 from each and every element, and then actually we reassign the elements and actually the new values. And here we have -210 for all elements. And of course we can also set different values. So let's assume that the initial investment for project 1 is -200, for project 2 -150, and for project 3 it's 250. Then we can simply create here a list and actually change the values by slicing for them. So let's have a look here. And here we have -200, 150, and -250. Next, let's assume that we want to slice for the initial investments and save the very first column here in a variable, for example, initial investment I0. And of course, we can do this here. So this is I0 with the elements -200, -150, and -250. And now let's assume that the initial investment for project 1 changes to -180. Then we can actually change the element by selecting the very first element here and setting the new value -180. And we have successfully changed it here in the slice in I0. But let's have a look at our original two-dimensional NumPy array. And also here we have changed the element here. So we've already learned that when we create slices of a NumPy array, then this is actually by default a view on the full and original NumPy array. And if we change the slice, then we also change the original NumPy array. But we can also avoid this by using the copy method. And now let's assume that you want to create a slice for the very last cash flows, so 50, 40, and 200. Then we can select the very last column, and we use here the copy method, and then we save the new and independent object in the variable CF5. And if we change now the very last element in CF5, so 200, and set a new value, 150, then we have changed the slice, which is a new object, but we didn't change the original NumPy array CFS. So here still we have 200. Alright, thanks for watching, and I'll see you also in the next video. Bye. We have already learned that two-dimensional NumPy arrays have rows and columns. And actually NumPy arrays and the methods are designed to perform row-wise and column-wise operations. So in many methods we can find the axis parameter, where we can define whether we want to perform an operation along the rows or along the columns. So let's import NumPy and let's set some printing options here. And we have project 1, 2, and 3. And we have the two-dimensional NumPy array projects with all 3 projects. And now let's assume that we want to take the sum over all projects. And there are actually some alternatives and options how to take the sum here. So first of all, let's simply pass the whole array projects to np.sum. And here we get the total sum over all elements in our two-dimensional NumPy array. So it's 1850, but that number is not really meaningful. And first of all, let's assume that for each and every timestamp and for each and every column, we want to add the cash flows over all 3 projects. So for instance, we want to calculate the total initial outflow here today. So minus 200, minus 50, minus 1000 is a total outflow in T0 of 1250. And again, we can use here np.sum. And let's go inside the parentheses here with Shift Tab. And actually we get here the sum of array elements over a given axis. So first of all, we have to pass here the array projects, and then there's the axis parameter. And here we can define the axis along which a sum is performed. And in a two-dimensional NumPy array, we have 2 alternatives. So we can either pass 0, which stands for the very first axis, so the row axis, or we can pass 1 for the columns axis. So if we pass 0 to the axis parameter, then we take the sum along the rows or column-wise. So this is actually the same. So now let's run the cell here. And here we get the summed cash flows for each and every timestamp. So initially there's an outflow of the 1250. And for instance, in the year 7, we have a total inflow of 250. Alternatively, let's assume that you want to sum the cash flows for each and every project. So the sum over the first project, the sum over the second and the third project. And instead of passing 0 to the axis parameter, we can pass 1 to the axis parameter. And by doing so, we take the sum along the columns axis, or to say row-wise, so for each and every row. And here we get 90 for the first project, 60 for the second, and 1700 for the third project. In this course, we have already calculated cumulative cash flows also with np.comSum. And also here we can define that we want to take the cumulated sum along the columns or row-wise, so for each and every project, by passing 1 to the axis parameter. And for instance, for project 1, we start at minus 200. Then after 1 year, we are at minus 180. And finally, after 7 years, we have a surplus of 90. And as I said before, many NumPy functions and methods have the axis parameter. So here's another example. And also we can take the mean along the rows or the columns. And by passing 1 to the axis parameter, we calculate the mean for the projects, so project-wise. And the mean cash flow for the first is 11.25, for instance. And we can also take the mean cash flow for all timestamps by passing 0. So for instance, the average initial investment is minus 416. And finally, if we simply pass the whole two-dimensional NumPy array to np.mean without defining the axis, then we get the mean over all elements. And in this case, it's 77. All right, thanks for watching, and I'll see you also in the next video. Bye. Hi and welcome to the very first lecture on pandas and pandas data frames. In this and the next lectures and sections, you will learn pandas coding from scratch. But before we move to Jupyter Notebooks and start coding, first of all, I want to introduce the concept of tabular data and some terms and vocabulary that I will frequently use in this course. So in the whole course, we will work with data that is organized in a tabular manner. And in pandas, this is a so-called pandas data frame. So that's a data frame here with 5 famous football players, for instance, Lionel Messi and Cristiano Ronaldo. And actually each row here is one football player. For instance, we have the row Cristiano Ronaldo with some features or characteristics of this player here. For instance, we have the nationality or the club, or also the height. So the height is one column of this data frame here. And actually we can see that the height of Cristiano Ronaldo is 1.87 meters. And 1.87 is also called an element, a value or an entry of the data frame. And we can also have slices or subsets. So here we have only 2 players and only the columns nationality and club. And we can also say that tabular data or pandas data frames are 2-dimensional. So we have 2 axes, we have rows and columns. And actually all rows and columns are labeled. And first of all, we have the so-called row index, or simply the index. And each and every element here is called an index label. So Neymar Jr. is the label of this row here. And the index shouldn't be mixed up with the columns. So the index is not the first column of the data frame, it's the index. That's the difference. And a row index can also have a name. So the row index name, in this case, it's a player, but it could also be player name or whatever. And second, we have the column index, or short columns. And the elements in the column index are called column labels or column headers. And last but not least, there's an optimal data organization in data frames. And we should always have the observations in the rows. So the observations here are the football players, and each single row should be one observation or one football player. And in the columns, we should have the characteristics, the variables or the features of the observations. So for instance, the height is a characteristic or a feature of a football player. So when working with data frames, we should always have this structure here to have the full functionality of a data frame. And the reason for this is the following. So we should make sure that we have only one data type per column. And let's have a look here if this is the case in our example. So we have the nationality column with string or text data. Then we have the club column with string or text data. Then we have the world champion column that indicates whether the player already won the world championship or not. And here we have bool or boolean values. Then next we have the height column where we have floats. So with 2 decimals, 1.70 for instance. And finally we have the column goals 218 with the number of goals that the player scored in the year 2018. And here we have integers. So in this case, we have an optimal data organization, and we can be sure that we have full or maximum functionality. And in case we have mixed data types in some columns, this can restrict the functionality of the complete data frame, and this can cause severe problems. Alright, this was a short overview on tabular data and pandas data frames. Thanks for watching, and see you in the next lecture. Bye. In this video, I will show you how to open and work with the downloaded Jupyter notebooks and datasets. And we will also create our very first pandas data frame. So this is probably one of the most important lectures of the whole course. And we have still the downloaded folder course materials part 1 on our desktop. And now let's go to Anaconda. So here we are on the Anaconda navigator. And we go to Jupyter Notebook. And that's the Jupyter dashboard here. And it's important to understand that this is a view on our users or home folder. So let's open our users or home folder. And here we can actually see the very same folders and elements. So for instance, Anaconda 3, contacts, desktop, documents, and so on. And also here. And if we add another element or another folder here to our users folder, then we will also see this here in our Jupyter dashboard. So this is a view on our users or home folder. And actually we know that our course materials part 1 folder is on our desktop, and therefore we click here on desktop. And this is a view on our desktop, and here we can see the unzipped folder course materials part 1. And let's click on it. And now let's go to video lecture notebooks. And here we can actually see all notebooks and also all datasets that we will use in part 1 of this course. And actually we could simply open the very first notebook, Pandas Basics. So that's the section here. And here we can see the complete code that we will create in the next lectures. But now let's create a new Jupyter notebook, and let's try to start from scratch. So we go to New, and we select the Python 3 notebook. And actually we should title or name our notebook. So for instance, Pandas 1. And let's click on Rename. So we have created now the Jupyter Notebook Pandas 1, and if we go now to our Jupyter dashboard, here to our overview, then here we can see that we have successfully created Pandas 1 Jupyter Notebook. And as this is actually a view on the folder Course Materials Part 1, then we should also see this new Jupyter Notebook also in the folder here. So let's double check this. Let's go to Video Lecture Notebooks, and here we can see the new Jupyter Notebook Pandas 1. So again, this is a view on the folder, and now the plan is to import the Titanic dataset that is stored in the CSV file titanic.csv into our Pandas 1 Jupyter Notebook. And it's important to see and understand here that both files are in the very same folder. So we have the Jupyter Notebook Pandas 1 and the CSV file titanic.csv. So they are located in the very same folder. And therefore the import is pretty straightforward. So now let's go back to Pandas 1. And let's create some more cells with the B key. And first of all, we have to import the Pandas library. And we should always import pandas with the code import pandas spd. So PD is the abbreviation for pandas, and it's the convention to import pandas spd. So everybody knows that PD stands for pandas. And now we can import the Titanic dataset from the CSV file titanic.csv. And there's actually the pandas method pandas pd .read CSV, and then we have to pass the file name within the parentheses, and actually as a string in quotation marks. So let's again have a look here. So the file name is the titanic.csv, and now let's run the cell. And this looks like a data frame. So here we have 891 rows and 9 columns. And finally, we can also store the data frame in memory and assign it to a variable. And let's select the variable Titanic. And let's run the cell. So we have successfully saved the data frame in the variable. And let's simply print our data frame again. So here we have the data frame. And we can see that we have actually 891 rows and 9 columns, but by default we can only see the first 5 rows and the last 5 rows. And I will show you in the next lecture how to change the display options here. But now let me show you the most frequently made mistake when importing CSV files into pandas. And let's go back to our desktop. And here you can see the CSV file iris flowers, so short iris, and the name is iris.csv. And obviously this CSV file is not in the course materials folder, it's just located on our desktop. And now let's try to import the iris flowers dataset into our Pandas 1 Jupyter notebook. So let's copy here the code, and let's paste it. And actually the file name is iris.csv. And here we get a file not found error. And it says here that the file iris.csv does not exist. Well, it actually does exist, but on our desktop. However, we can only import a CSV file if the CSV file and the Jupyter notebook where we are coding in are located in the very same folder. And now let's go back to our Jupyter dashboard. So here we have the folder video lecture notebooks. That's the subfolder, and the main folder is course materials part 1. And actually we were able to import the CSV file titanic.csv to pandas 1 because both files are located in the very same folder. And now we tried to import the iris.csv file into pandas 1. And this does not work because they are not located in the very same folder. So here we do not have the iris flower CSV file. And therefore we get the file not found error message. So now what can we do if we want to import the iris.csv file into pandas 1? Then actually there are two solutions. So either we can simply drag and drop here iris into the video lecture notebooks folder where we have pandas 1. So that's the hands-on approach. Or let me show you a better approach. Or we can also upload here in the Jupyter dashboard, and let's click here on upload. And let's select the desktop. And here we can see the iris.csv file, and let's click on it. And here we have now the option to upload the CSV file into this folder here. So we have done this, and we can actually now see iris.csv. And now let's go back to our pandas 1 Jupyter notebook. And let's again try to import the iris.csv file. And now it works. And again, the reason is pretty simple. So the Jupyter notebook pandas 1 and the CSV file are located in the very same folder. And if they are not located in the very same folder, we get a file not found error. However, there's an alternative way how to import a CSV file, even if the file is not located in the very same folder. But this is more complicated, and you can drop me a message and ask for the alternative way. But actually, I do not recommend the alternative way. All right. So as a final remark, if you get a file not found error, and if you do not know why and what to do then the best advice is to rewatch this video. All right, thanks for watching, and see you in the next lecture. Bye. Hi and welcome back. We have still imported the Titanic dataset, and we have saved the data frame in the variable Titanic. And we've already seen that we can simply print or output the data frame by running the cell with the variable Titanic. So here we can see the data frame, or at least the first 5 rows and the last 5 rows. And you might know that there's a second way how to print things in Python. It's with the print function. And let's pass Titanic. And now let's run the cell here. And actually the data is of course the very same, but the style isn't as nice as we had before here. And by default, Jupyter notebooks nicely display pandas data frames in an easy to read HTML table if the data frame variable, so in this example Titanic, is in the last line of a cell, and if we simply run the cell. However, if we use the print function here, then the data frame is rendered in a less readable, poorly formatted text-based output. So there's actually no reason why we should print or display a pandas data frame with the print function. So that's actually the best solution here. Now we still have the problem that by default we can only see the first 5 rows and the last 5 rows. And the reason is that there are some standard or default display settings. And let's have a look here. So we have pd.options.display. And the first setting is the max row setting. And the default setting is here actually 60. And there's also a second display option or display setting. And it's actually the min row setting. And the default value is here 10. Now the rule how pandas displays the data frames and the rows is pretty simple. So if the data frame has equal or less rows than the max row setting, so by default it's 60. So if the data frame has less than 60 rows, then by default pandas shows all rows. But if the data frame has more rows than the max row setting, so by default more than 60 rows, and typically our data sets have more than 60 rows or more than 60 observations, and in all these cases, then the min row settings prevail. So by default we see in total 10 rows, and that's actually the first 5 rows and the last 5 rows. Now what if we want to change this, and let's assume that we want to see the first 10 rows and the last 10 rows, so in total 20 rows, then we can simply set the min row setting to 20. And let's run the cell. And let's again print Titanic, so let's do this here in a new cell. And then we can see that we have the first 10 rows and the last 10 rows, so in total 20 rows. And actually we could also print or output all rows of a data frame. So of course this doesn't make sense if the data frame has thousands or even millions of rows. But in our example here with 891 rows, this is still feasible and could make sense. And the only thing we have to do is actually we have to set max rows to a number that is equal or higher than the total number of rows in our data frame. So in our case, at least 891. And let's again print Titanic. And here we can now scroll down, and we could actually analyze and observe all 891 rows of our data frame. All right. And actually at this point, it's important to mention that the display settings changed in Pandas version 0.25. So they actually introduced the min row setting. So before we only had the max row setting with the default value 60, and there was no min row setting. So min rows was actually none. So that was actually the setting in Pandas version 0.24 and earlier. And the default behavior was when printing the data frame with more than 60 rows, then by default Pandas showed the first 30 rows and the last 30 rows. So in total 60 rows. And this is just for you to know, as you might see this behavior in other courses or other videos, and also in some videos of this course that are based on Pandas version 0.24. So just for you to know here. And now let's come to the very helpful methods head and tail. And first of all, let's focus on the head method. So we have here Titanic.head. And by default, the head method shows the first 5 rows of a data frame, but we can change this. So if you want to see the first 10 rows, then we can simply pass here 10, or the first 20 rows. And second, there's the tail method. And by default, we can see here the last 5 rows. But of course, we can also get the last 10 rows by passing 10. So the default argument is actually here 5. But we can change this to 10 or also to 2 to see the last 2 rows. And now we're actually best equipped to make a very first inspection of our data frame. So we can change display options and we can inspect the first 5 rows or the last 5 rows or all rows or the first 30 rows or whatever. And actually we will do the very first inspection in the next video. So hope to see you there. Bye. Alright, after having imported the data, we are coming now to the next and one of the most important steps when working with data, the very first inspection. And typically when working with data and with new data sets, we don't know much about the data. And before we can start with our primary task, and this can be explanatory data analysis, data visualization, statistical analysis, machine learning, or whatever. So before we can start with this, we need to perform a very first inspection, and based on that first inspection, we can plan the next steps. For instance, we could come to the conclusion that we need additional data, or that we need to clean the data, or transform the data, or handle missing values, or whatever. And it is very often the case that this first inspection is underestimated. However, coming from the business side, I have to emphasize that understanding your data and understanding your task is the key to success. So we have still imported the Titanic dataset, and we have saved it in the variable Titanic. And here we can see the first 5 rows and the last 5 rows, and also the column headers or column labels. And in the vast majority of cases, this is already sufficient to get a very first impression. So here we can see we have 891 rows and actually 891 observations, and each and every observation or each row is here one passenger on board of the Titanic, and we have 9 columns. And each column is actually a characteristic or a feature of the particular passenger. So here on the left side, we can see the index of our data frame, and the default index is actually a range index. And a range index simply consecutively numbers the rows, so starting with 0, 1, 2, 3, and until 890. And typically when importing data from a CSV file, by default we can see here a range index. And now let's come to the columns. So first of all, we have the survived column, and this indicates whether the passenger survived the disaster or not. And actually 0 stands for the passenger did not survive, and 1 stands for survived. Then we have the passenger class. So in total we had 3 passenger classes, so 1, 2, and 3, and 1 was of course the first class. Next we have the gender or the sex of the passenger, so we have of course the males and females. Then we have the age in years, so for instance here 22. Then next we have the column SIP-SP, and this stands for siblings and spouses. And this is actually for each and every passenger the number of siblings and the spouses of this passenger on board of the Titanic. Then we have PARCH, which stands for parents and children, and this indicates the number of parents and children of that particular passenger that were also on board of the Titanic. So the very first passenger here was a 22-year-old male passenger in the 3rd class, and he obviously did not survive the disaster. And he also had probably his wife on board. Then next we have the fare or the ticket price, and I don't know if this is in dollar or in British pound, but this passenger paid $7.25 or pound for the ticket. Then next we have the port of embarkation, and for instance S stands for Southampton. And last but not least we have the deck where the cabin of the passenger was located, and for instance here we have the C deck or the B deck. And we can also see some values called NaN, and this stands for not a number, and this indicates missing values. So for instance, for this passenger here, we simply do not know the age. And typically when working with real-world data, missing values are very common, and actually Pandas is designed to work with and handle missing values. So this is a very important concept, and we will go into much more detail later in this course. Next, there's one very important method for data inspection. It's the info method. So let's run the cell here. And the info method is actually one of the most important methods in Pandas, as it summarizes the data frame and shows important meta information at a glance. So let's have a look at the output here. And first of all, we can see the data type or the class that the object that is stored in Titanic belongs to. And it's obviously a Pandas data frame. Next, we can get some information on the index. And we've already seen that here we have a range index with 891 entries from 0 to 890. And then we get an overview on the columns. So we have 9 columns. And these columns here are consecutively numbered from 0 till 8. And first of all, here we have the column label. Then we have the non-null count, which gives us actually the number of non-missing values. So in total, we have 891 entries, and obviously in the survived column and in the P-class column and the sex column, we have no missing values. So we have 891 non-null or non-missing values. But here in the H column, we can see that we have 177 missing values. And also in the embarked column, we have 2 missing values. And we have over 600 missing values in the deck column. Finally, we have also some information on the data type in the columns. And it's actually no surprise that in the survived and P-class column, we have integer. Then in the sex column, we have a so-called object data type. And actually, this stands either for string or text data, or also for mixed data types. So whenever we have object, it's not 100% clear whether we have string or text data, but this is pretty likely. Then next in the H column, we have float data. So here we have 1 decimal, 35.0 for instance. Then in the zip-sp and in the parch columns, we have integers. So we have actually 0 parents or 2 parents and children and so on. And finally, in the embark column and deck column, this is also here an indication that we have string or text data. So this makes sense. Here we have S, C, C, B, and so on. And finally, we get here a summary of the data types. So we have 2 columns with floats, 4 columns with integers, and 3 columns with the data type object. And last but not least, we also have the memory usage. So this is a very small data set with 62.8 kilobyte. But of course, we could also have data frames or data sets with megabytes or even gigabytes. So again, the info method is really useful and helpful. And actually, the functionality and the behavior of a data frame is determined by only a few things. It's the index. So a range index behaves different than a datetime index with datetime information. And second, we have the columns and the data types in the columns. And last but not least, also the missing values. So these factors actually determine the functionality of our data frame. And we can see those factors at a glance by calling the info method. So as a summary, before and also while you are working with your data and your data frame, you should regularly check your data frame with the info method. And to draw an analogy, when you go by car, you regularly check fuel, oil, and speed to reach your destination safely. And that's exactly the same with data frames and the info method. All right. And finally, let's have a look at the very helpful method to describe. And by default, the describe method returns some summary statistics on numerical columns. So here we have the numerical columns survived, P class, H, and so on. And first of all, we have here count. So this is the number of non-missing values. Then we have the mean value. And the mean value in the survived column actually stands for the survival rate. So in total, 38% of all passengers survived the disaster, as we have 1 for survived and 0 for not survived. Then we have the standard deviation of the values and also the minimum. So the youngest passenger on board was, for example, 0.42 years, and actually that's a baby. Then we have the 25th percentile, the 50th percentile, which is actually also the median. And that means that, for instance, 50% of all passengers were younger than 28 and 50% were older than 28 years. And also we have the 75th percentile and finally also the maximum values. So the highest fare or the highest ticket price was 512. And actually with the describe method, we can also analyze the non-numerical data. So let's copy here. And let's paste. And then we can use the include parameter. And here we can pass capital O. And by doing so, we actually select all columns where the data type is object. And typically these are non-numerical columns with text data. So let's run the cell here. And here we have a summary for the sex, embarked, and deck column. So count also stands for the number of non-missing values. Then unique actually indicates the number of unique values. So in the sex column, we only have male and female. Then next, we have the most frequent value, and this is here in the sex column male, and the frequency is 577. All right, this was the very first inspection of our data, and by simply inspecting the data and by running 2 or 3 methods here, we already know quite a lot about the data, and this helps for our further analysis. So thanks for watching, and see you also in the next video. Bye. We are coming now to one of the most frequently used operations in pandas, selecting one or many columns. And we have still imported and saved the Titanic dataset. And you might recall from sequences like lists, strings, or NumPy arrays that we can index these objects and select certain elements with these square brackets index operator. So let's try this out here. And then we can open square brackets. And actually to select one column, we can simply pass the column label as a string, so within quotation marks. And let's assume that we want to select the H column. Then we can simply code here H. And now let's run the cell here. And here we have only the H column, the first 5 elements and also the last 5 elements. And on the left-hand side, we can still see the range index. And actually the output here is a so-called panda series. So actually the pandas library has some data types. So we already know the pandas data frame. And this is here a panda series. And we could say that a panda series is very similar to a data frame, but a series only shows one column or one row. So to say, it's a one-dimensional labeled array, and it's called labeled because still we have here the index. So the values in the H column here are still labeled with the index labels. And later in the course, we will have a closer look on panda series. But for the time being, you should simply notice that this is here a panda series. And the name of the series is actually the former column label H. And here we can see that in total we have 891 elements, and the data type is float. And we can also check the data type with the type function. So let's go here to command mode, and let's copy and paste with C and V, and let's use here the type function. And no surprise, this is a panda series. So now we have selected one column, but now let's assume that we want to select 2 or many columns. And again, let's copy here and let's paste. Now let's assume that we want to select the H column and also the sex column. Then let's try the following. So let's pass here H and sex. And here we get an error message. And it says here key error, so there's no column label that consists actually of a tuple with H and sex. But of course, there's a workaround for this. So let's again paste here the code. And actually, if we want to get 2 or many columns, then we have to pass the column labels as a list. So we have to create here a list and actually pass H and sex as 2 elements of the list. And now let's also close the list here. And let's again run the cell. And here we get now the 2 columns H and sex. And obviously, if we select 2 or many columns, then the output is again a pandas data frame. And we can also check this here. So this is a pandas data frame. Now let's again copy and paste the code. And actually we have coded age and sex, and therefore the sequence is here age and sex, but we can also change the sequence. So first of all we have sex, and then we have age. And by doing so we can also change the output. So let's have a look here. And now we have the sequence sex and age. And finally we can also select multiple columns. So let's copy and paste. And for instance, we can also select the fair column. So we code comma and fair. And here we have now the 3 columns. And actually before we have seen that if we select only one column, then the output by default is a panda series. But if we pass only one column also within a list. So let's try this out here. And now let's create a list with only one element, so the age. Then here we get obviously a pandas data frame, and we can also check this here. So when selecting only one column, you might ask yourself whether it's beneficial to have a series or a data frame. And we will see later in the course, in the vast majority of cases, it doesn't matter, as series and data frames share most of the methods. So there are only very few methods that only work for data frames, and there are very few methods that we can only use on series. But generally speaking, most of the methods are available for both types. Alright, thanks for watching, and see you also in the next lecture. Bye. Hi and welcome back. There's also a second alternative to select one column, and we can use the dot notation or attribute notation. And we have still imported the Titanic data frame or data set. And a data frame with the column age has also an attribute dot age. And let's run the cell. And here we can see the age column, and also here this is a panda series with 891 elements. So when selecting one column, the dot notation and the square brackets notation are equivalent and lead to the same output. And we can also check this with the equals method. So let's have a look inside here with Shift tab. And the equals method tests whether two objects contain the same elements. And let's copy here our code where we selected the age column with the square brackets notation. And let's paste it here inside the method equals. And now let's run the cell. And here we can see that we get a true, so both alternatives lead to the very same result, the age column. And there's actually some controversy which alternative to prefer. And some people argue that we shouldn't use the dot notation, as it can lead to errors in some cases where we have unclean data. For instance, the dot notation does not work in case the column label contains white spaces. And actually I don't agree with that, because we should avoid to work with unclean data anyway, and we should clean the data before we start with our primary tasks. So I use both alternatives, but I'm pretty lazy and I prefer the dot notation as it is less to code. So for instance, to get the embarked column, I simply use the tab completion twice, and that's it. So I start with Titanic, then I use tab and enter, dot, and then I start with emp, and also here I use the autocomplete, and that's it. Alright, thanks for watching, and see you also in the next lecture. Bye. In the next 2 lectures, you will learn how to select the rows, columns, and elements of a data frame by their positions. And this is called position-based indexing. For instance, you will learn how to select the second row or the last row, or the first 2 columns of a data frame, or even more complicated, the element that is located in the 7th row and 3rd column. But before, I want to recap 2 fundamental concepts that are valid not only for pandas, but for Python in general and also for other programming languages, it's zero-based indexing and negative indexing. And you might recall from sequences like lists, strings, or NumPy arrays that the very first element is at index position 0, then the second element is at index position 1, and so on. So we start with the position 0. And that's the reason why it's called zero-based indexing. So zero-based indexing also applies for pandas data frames. And the only difference is that a data frame is two-dimensional, so we have rows and columns, and therefore we have index positions for rows and also for columns that follow the zero-based indexing concept. So first of all, let's focus on the column index positions, and just to recap here, so player here is not a column but the index. And therefore, the very first column is nationality at index position 0. Then we have club at index position 1, and so on. And the same applies also for the row index. So we have the very first row, Lionel Messi, and this row is at row index position 0. Then we have Cristiano Ronaldo at index position 1, and so on. So this is zero-based indexing, but there's also a second concept, and it's called negative indexing. And this can be applied as well. So we can either use zero-based indexing or negative indexing, and it depends on the specific case which one makes more sense. And now let's have a look. So negative indexing means that the very last column is at index position -1. That's the goals to 18 column. Then the second last column is at index position -2, and so on. So finally, the very first column, nationality, is at index position -5. And of course, this also applies for the row index. So the very last row, Manuel Neuer, has the index position -1. And then we have -2, -3, and so on. And actually, for your convenience, you can find this slide for download in the attachment of this lecture. Alright, thanks for watching, and see you in the next video. Bye. In this lecture, we will perform position-based indexing with iLoc. But before we start, let me introduce a new dataset that I will frequently use in our course. It's the Summer Olympic Games dataset, containing all medals that were awarded in Summer Olympic Games from 1896 until 2012. And first of all, let's import pandas. And then we import the Summer Olympic Games dataset from the CSV file summer.csv. So in our download materials in our folder here, we have also the CSV file summer.csv. And we save the resulting data frame in the variable summer. And let's have a look at summer, a very first quick inspection. So we have in total over 31,000 rows and 9 columns. And actually each and every row is one medal that was awarded to an athlete. And for instance, let's have a look at the very first row. So we have the athlete Alfred Haryo from Hungary. He's a man. And he won the gold medal in the edition 1896 in Athens in actually the event 100-meter freestyle. And this is a swimming discipline or event, and the sport is aquatics. And let's inspect also the very last row. And here we have Jimmy Lidberg from Sweden, and he won the bronze medal in the event freestyle wrestling until 96 kilograms in the edition 2012 in London. Now let's also call the info method. And here we can see that we have a range index with over 31,000 entries. And actually we have 9 columns. And we only have very few missing values in the country column. And actually we have only one numerical column, so we have the data type integer in the year column. And in all other columns we have text data and actually strings, and this is indicated by the data type object. And finally we can also see that we have a memory usage of 2.1 megabyte. So this is a larger dataset than the Titanic dataset, but still it's a pretty small dataset. And again, by default, we can see that we have a range index, but actually we can also change this. And we can set each and every column of our data frame as being the index. And we can determine this already when we import the CSV file. And there's the parameter index col. And here we can pass the column label for the column that we want to have as index. And here in our case, it could make sense to have the athlete column with the athlete names as the index. So let's pass here as a string athlete. And now let's run the cell again. And let's have a look at our data frame. And now here on the left-hand side, we have the new index athlete with all of the athlete names. And we can also rerun the info method. And here we can see that our index changes from a range index to an index with over 31,000 entries from Alfred Hayos until Jimmy Littberg. And now let's start with position-based indexing. And let's assume that we want to get the very first row. So the row with Alfred Hayos. And let me show you the code. So we start with summer. And then we have to use the ilog operator. So whenever we want to perform position-based indexing, we have to use ilog, and then we have to open square brackets. And then we have to pass the position of the row that we want to get. And in our case here, it's the very first row at index position 0. So 0-based indexing applies also here. And let's run the cell, and here we can see the very first row. And the same as with columns, if we only get one column or one row, then by default the result is a panda series. So here we have the values of the very first row. So for instance, 1896 are Athens and aquatics. So that's the values in the columns here. And actually, as the name of our panda series, we have the index label Alfred Hayos. So as a summary, our panda series here consists of the values taken from the very first row. And we also have an index here. And these are actually the values that we had before as column labels. So here, city, sport. And these labels are now the index labels in our panda series. And for the sake of completeness, we can also check the data type. So it should be a panda series. And that's true. And now let's go on with a second example. And let's assume that we want to get the second row. It's Otto Herschmann at index position 1. And then we can simply pass 1 to the ilog operator. And then we get the second row with the values, and the name of the panda series is Otto Herschmann, which was the former row label. So these were two examples of zero-based indexing, and now let's come to negative indexing. And let's assume that we want to get the very last row. So here Jimmy Littberg at index position -1. Then the code is pretty straightforward. And here we have to simply pass the index position -1. And then we get the row with the values for Jimmy Littberg. All right. Next, let's assume that we want to get the rows at index positions 1, 2, and 3. So these are those 3 rows: Otto Herschmann, Dimitrios Drivas, and Ioannis Malokinis. And we simply have to pass a list with the index positions. So that's one solution. So we open here a list with additional square brackets, and then we have the index positions 1, 2, and 3. And of course we get here Otto Herschmann, Dimitrios Drivas, and Ioannis Malokinis. But there's also a better solution for this, and instead of passing all positions explicitly, we can also actually slice here our data frame. So let's remove the list here. And actually we want to get the rows from index position 1. So this is inclusive. And actually we can code the following. So we want to have 1 until, and for until we can code a colon. And if we pass now index position 3, then we only get 2 rows. So the rule in position-based indexing is that we slice from position 1 inclusive until position 3 exclusive. And therefore, if you want to have positions 1, 2, and 3, then we have to slice from 1 until 4 exclusive. And here we have those 3 athletes. Now let's assume that we want to get the first 5 rows, and there are actually 2 options. So either we can explicitly code from index position 0 until index position 5 exclusive, so this works. Or even more efficient, if we start from the very first row, we can simply code colon 5. So the first 5 rows. Next, let's assume that we want to get the last 5 rows. And this works pretty much in the same way. So we can code from index position -5 until the very last index position. And actually it's important to understand that the very last row is here inclusive. And it would be wrong to code the very last row explicitly. So this gives from index position -5 until index position -1 exclusive. So here we have lost Jimmy Littberg, and therefore the last 5 rows is simply -5 colon. All right. Finally, we can also get all rows. So this is a no-brainer, but we could do the following. So from the very first row until the very last row inclusive. And here we get all rows, so over 31,000 rows. And finally, we can also perform some more advanced operations. So for instance, we can pass a list with index positions that are not neighbors actually. So for instance, 2, 45, and 5,467. So this also works. And this was a short introduction to position-based indexing with ilog. And in the next video, I will show you how to select rows and columns, and also single and multiple elements with ilog. So see you there. Bye. Alright, we are continuing with position-based indexing with ilog, and we have still imported and saved our Summer Olympic Games dataset in the variable summer. And let's get the first 10 rows here. And now let's assume that we want to select one single element of our data frame, for instance, the element Hungary. So Alfred Haryos is from Hungary. And actually the element is in the very first row at index position 0 and in the column with index position 0, 1, 2, 3, 4. And getting this element is pretty straightforward with ilog. So we code the following: summer.ilog, and then we open the square brackets, and we already know that we can get the very first row with 0 here. So that's the first row, but we are only interested in the value in the column at index position 4, and therefore we code the following. So we introduce here a comma, and then we have 4. And actually the rule is pretty simple. So on the left-hand side of the comma, we can determine the rows or the index positions of the rows. And on the right-hand side of the comma, we can determine the columns or the index positions of the columns. So in our example, it's 1 row at index position 0 and 1 column at index position 4. And let's run the code here. And here we get Hungary. And actually that's the real power of the ilog operator. So we can, in only one operation, we can index and slice for rows and columns. And of course we can also perform some more complex operations. And let's assume that still we are interested in the very first row, but now we want to get the values in the first 3 columns. Therefore we can code the following. So on the left-hand side of the comma, we have the row at index position 0. And on the right-hand side, we want to have the first 3 columns, so colon 3. And this gives us here a panda series with these 3 elements. And of course, instead of having here a slice, we can also perform more complicated operations. So let's assume that we are still interested in the very first row at index position 0, but we want to have the values in the columns at index positions 0, 2, 5, and 7. And of course, this also works here. And finally, let me show you an even more complicated example. So of course, also on the left-hand side of the comma, we can make it more complicated. And we could slice from the row at index position 34 inclusive until row at index position 39 exclusive. So this is no problem. And last but not least, we can also select complete columns with ilog, and that's pretty straightforward. So let's assume that we want to get the country column at index position 4. And we simply have to code here on the left-hand side of the comma that we want to get all rows. And that's here the country column with over 31,000 elements. And actually before we have also seen 2 other alternatives how to select entire columns. So either with the dot notation or with square brackets. And let's simply make sure that these 3 alternatives deliver the same output. And we can check this with the equals method again. And then we can pass here summer.country. And let's run the cell. And here we get a true. And for the sake of completeness, the third alternative is the square brackets alternative. And this actually gives us, of course, the same output. Alright, thanks for watching, and see you also in the next lectures. Bye. This and the next videos are about label-based indexing and slicing with the log operator. And in a minute you will see the limitations of position-based indexing and why we also need label-based indexing. And you will understand the difference between position-based and label-based indexing. And we have still imported our summer data frame. And let's assume that we want to get the third row at index position 2 with Dimitrios Drivas. Then we have already learned that we can do this with the ilog operator and pass the row index position 2. And this works pretty well. So here we have Dimitrios Drivas. However, our task is typically a bit different. So we actually don't know the index position of a row, and we simply want to get the row or the medal of Dimitrios Drivas. In this example here it's obvious, so we can simply count the 0, 1, 2, but there might be more complicated or less obvious cases. And therefore there's also the option to select this row with label-based indexing by passing the label of the row Dimitrios Drivas. And this works pretty much in the same way as position-based indexing, but now with label-based indexing we have to use the log operator. So let's do this here. We have summer.log, and also here we have square brackets. And then we have to simply pass as a string, so within quotation marks, the row label Dimitrios Drivas. So let's copy here and let's paste and let's run the cell. And of course here we get the very same output, so the row with Dimitrios Drivas. Next, let's come to a more real-world example, and let's assume that we want to get all rows with Michael Phelps. So Michael Phelps was a very successful athlete in swimming actually. And let's try to get the rows. And we can simply replace Dimitrios Drivas with Michael Phelps. And we actually apply the very same format. So we have the surname with only capital letters. So we have here Phelps. And the first name is Michael. And now let's run the cell. And here we get multiple rows. So we have multiple entries of Michael Phelps. And that means that he actually won many medals in Summer Olympic Games, starting in the year 2004 and ending here in 2012. So when we perform label-based indexing, then we got all occurrences of the particular label, in this example Michael Phelps. And with this we have actually reached the end of this video, and we will continue in the next lecture. Bye. In the last lecture we have seen that our index contains duplicates like Michael Phelps. This is allowed in pandas, and actually a data frame index should not be mixed up with a primary key in relational databases. So a primary key in databases must contain unique values and uniquely specifies a row. So each and every row can clearly be identified by the primary key. And in pandas, there's no obligation to have unique values in the index. And the question is now, should we have a clear identifier? And the answer is probably yes, that's the best practice. However, pandas gives us the flexibility to have an index with duplicates. And in some cases, it is totally fine to work with that, as long as you know the pitfalls and limitations of a non-unique index. And in this and the next lecture, we will see some of these pitfalls. And actually, to summarize, in case you have any doubts, you are definitely on the safe side when you simply use a range index, because a range index is unique. Alright, now let's go on, and similar to position-based indexing with ilog, also label-based indexing with log allows to simultaneously index and slice for rows and columns. So let's assume that we are interested in all medals that Michael Phelps won, but actually we are only interested in the column medal. Then we can actually do this. So let's copy and paste. And also here with the log operator, we can introduce a comma. And on the left-hand side of the comma, we can define the row labels. And on the right-hand side, the column labels. And in this case, we want to have all rows with Michael Phelps and the column medal. So let's run the cell. And here we get only the column medal for all rows where we have Michael Phelps. Alright, now let's copy and paste the code. And of course you can also get more than only one column. And let's assume that you want to get the columns medal and event. Then we can simply pass here on the right hand side of a comma a list with the column labels. So let's open here a list. And for instance, let's also select the column event. And here we have now the medal and also the event for all medals that Michael Phelps won. Alright, now let's copy and paste. And of course also on the left hand side we can have more complexity. And let's assume that you want to have medal and events for all medals that either Michael Phelps or Carl Lewis won. Then we can also pass a list here on the left-hand side. So we add here Carl Lewis. And let's again run the cell here. And here we have first of all Michael Phelps and finally also all medals of Carl Lewis. Last but not least, we can also select complete columns with the log operator. And let's copy and paste. And let's assume that you want to have all rows for the columns medal and event. Then here we can simply pass a colon for all rows. And this works as well. Now let's go on and let's have a look at the first 10 rows with the head method. And so far we simply passed row and column labels in a list to the log operator, but we can also perform slicing, so from to. And actually label-based slicing with text data in the index is not the most relevant case in practice, so there's hardly any reason why you should slice from Michael Phelps to Carl Lewis, but this is a good example to show you some pitfalls when slicing an index with duplicate entries. And in practice, label-based slicing is heavily used with datetime data in the index, a so-called datetime index. And you will see this in later sections of this course. But for the time being, let's assume that we want to get all rows from the very beginning until and including the row with Spiridon Chasapis. And actually, this is pretty straightforward with the log operator. So let's code summer.log. And then we can say that we want to have all rows from the very beginning until colon Spiridon Chasapis. So let's copy this and let's paste. And let's run the cell here. And here we have all rows starting with Alfred Haryos until Spiridon Chasapis. And it's important to see the difference between ilog and log. So with ilog, the left boundary is included and the right boundary excluded. And in contrast to that, here with the log, both boundaries are included, so the left and the right. So here we have all rows from the very beginning until Spiridon Chasapis, including. And now let's try the same with Michael Phelps. So let's copy and paste. And let's assume that you want to get all rows from the very beginning until Michael Phelps. So let's run here. And here we get an error, and it says that it cannot get the right slice bound for the non-unique label Michael Phelps. So Michael Phelps is a duplicate in our index, and therefore we cannot perform slicing operations with Michael Phelps. And the reason is pretty simple. So Panda simply does not know to which occurrence of Michael Phelps to slice. So should Panda slice until the first or the second or the third occurrence? So Panda simply does not know this. And actually we almost get the same error message if we try to slice from Michael Phelps to the very last row. So let's copy and paste here. And let's try to get all rows from Michael Phelps until the very last row. And also here we get an error message, and this is almost the same. But here it says that it cannot get the left slice bound for non-unique label Michael Phelps. So Panda simply does not know from which occurrence of Michael Phelps to start with. Alright, now let's have a look at the first 20 rows with the head method. So let's focus on the entries Dimitrios Drivas and Arthur Blake, and I can tell you that these values are unique, and therefore we should be able to slice from Dimitrios Drivas including until Arthur Blake including. So let's try this out. So let's copy here Dimitrios Drivas. So from him until Arthur Blake. And obviously this works. So we are starting with Dimitrios Drivas, and finally we are ending at Arthur Blake. And actually the same we can also do on the right hand side of the comma. So we can slice the columns from city till discipline. And by doing so we get all columns from city including until discipline including. Finally, let's try the following. So let's first of all copy the code here. And let's assume that we want to get labels that actually do not exist in our data frame. So let's create here a list with Michael Phelps. But then we can also try to get Donald Duck. And this obviously does not work, and we get here an error message, and it says that passing lists to log with any missing labels is no longer supported. So this was supported until I think it was version 0.22 or 23. and then it was deprecated. And finally now with version 1.0 it's completely removed from pandas. And actually the same applies also for missing column labels. So let's copy and paste here. And let's try to get rows with Michael Phelps. And column-wise, we want to get 2 columns. So the columns here, and this actually does exist. And we assume that we also have the column H with the age of the athlete. And let's try to do so. And also here we get an error message, and it says that again passing list likes with any missing labels is no longer supported. However, we can use in these cases the re-index method, and that's exactly what we will do in the next lecture, so hope to see you there. Bye. In this video I will briefly summarize what we have learned so far, and it's more than just a summary. So in anticipation of later and more advanced lectures, I will show you best practices, and you might have recognized that sometimes there are different ways how to do the very same thing. But even if we get the same result or the same output, the ways can still differ in the background, and they're actually best practices and non-optimal solutions that can cause problems later on. And finally, I will give you an outlook on the upcoming sections and lectures. So let's start, and we should always import pandas as PD. And then we can import a dataset from a CSV file with pd.readcsv. And we can also determine a column that should be the index. And then we can simply print and inspect the data frame. So by default, we can see the first 5 rows and the last 5 rows. And it's always advisable to have a look at the info method to get some more information on our data frame. And this could enable us to identify potential problems in our data frame. Then next we have 2 options to select one column. It's the dot notation or with square brackets, so you can use both. Then we have actually 2 options how to select multiple columns. And first of all we have the square brackets, and we can pass a list with column labels. And we can do the same with the log operator. So we actually slice for all rows and the columns year and medal. And actually the result or the output of both alternatives is the same, but there is a difference in the background, and I would highly recommend to use only the log alternative. So later on, when it comes to manipulating elements in a data frame, then the square brackets notation with more than one column could cause some problems. So you should definitely use the log even if it's a bit more to code, but that's the best practice here. And next we can select the positional rows with ilog, for instance from index position 10 inclusive until 21 exclusive. And we can also perform label-based indexing and select the labeled rows with log. So here we get all instances of Carl Lewis. Finally, let's assume that we want to get all rows with Carl Lewis and only the columns year, event, and medal. Then actually we have 3 alternatives, and 2 alternatives are bad practice and only 1 alternative is recommended. So first of all, let's start with 2 non-optimal solutions. And actually we could first of all select the columns year, event, and medal with the square brackets notation. So let's cross out the log. And here we get all rows and the columns year, event, and medal. And then we can chain another indexing operation with log and select all rows with Carl Lewis. So this works actually, but this can cause some problems in the background. And we can also do this the other way around. So first of all, we select all rows with Carl Lewis with the log operator. And here we get all rows with Carl Lewis and all columns. And then we chain another indexing operation and select only the columns year, event, and medal. So this works as well, but also here we have kind of two indexing operations. So we chain indexing operations like here. So here we have two. This is the first indexing operation, and here the second, and also here this is the first, and here the second. This is called chained indexing. And this can cause severe problems later on when we want to create slices or copies of a data frame, and if we want to manipulate elements in a data frame. So that's definitely bad practice. And finally, let me show you the best practice that is highly recommended. And actually, we index and slice our data frame for rows and columns. And we should do this in one indexing operation only. And it's pretty straightforward to do this with the log operator. So we have log, and then on the left-hand side of the comma, we select the rows, Carl Lewis, and on the right-hand side, we select the columns. So let's run the cell here, and the output is the same, but in the background it's a bit different. And again, this is only one indexing operation, but these two examples, here we have two indexing operations, chained indexing, and this is bad practice, so don't do this. Alright, now let's have a short outlook on the upcoming sections and lectures. And there are actually three major data types or classes in pandas. It's the data frame, and so far we have actually worked with the data frames. So here we have, for instance, the summer data frame with rows and columns. And second, we have panda series. So only one column or one row is a panda series. And one example is the year column. This is a panda series. And finally, we have index objects. So if we select either the columns index or the row index with the attribute columns, then this is here an index object. And also if we select here the row index, so this is also an index object. And before we go on with the data frames, in the next lectures, we will go deeper into pandas series and pandas index objects. So thanks for watching, and see you there. Bye. This is the first lecture on pandas series, and we've already learned that pandas data frames, pandas series, and pandas indexes are the three major classes or data types in pandas. And when selecting only one column or one row of a data frame, we typically get a pandas series. So let's have a look, and we import pandas and also the Titanic data set. And we already know that we have 9 columns in the Titanic data frame. And then we can select one column, for instance, the H column with the square brackets notation. And this gives a pandas series. So let's also check this here with the type function. And actually a pandas series is a one-dimensional labeled array. So we have an array with 891 elements, and these elements are labeled with the very same index labels that we have in the data frame, and it's here a range index. So the passenger with index label 0 is 22 years old, and we can find the very same passenger also here in the data frame. And we've already learned that there's also a second alternative how to select one single column, and it's with the dot attributes notation Titanic.h, and this gives the very same result as the square brackets notation. So let's save the h column in the variable h. And actually pandas data frames and pandas series share most of the methods and attributes. So there are only very few methods that are only available for data frames, and very few methods that are only available for pandas series. And for instance, let's try to call the head method on the pandas series h. And this works. So here we have the first 5 elements. And we can also customize this and select, for instance, the first 2 elements. Then next also we can call the tail method on the pandas series h. And there's the attribute dtype, and here we can check the data types in the pandas series. And it's no surprise that it is float. Then next we can check the shape. And here we get the result that we have 891 elements. And then we can also pass a pandas series to a Python built-in function, for instance, the length function. And also here we get the number of elements in the pandas series, 891. Now we've already seen that a pandas series is a one-dimensional labeled array. And we can also get the labels or the index with the index attribute. So here we have the range index from 0 till 891. Then next, let's try to call the info method on our pandas series h. And here we get an error, and it says that the series object has no attribute info. So the info method is only available for a pandas data frame. And finally, there's the method toFrame, and with toFrame, we can convert a pandas series into a pandas data frame with only one column. So let's have a look here. And here we have now a data frame with the column h, and of course still we have on the left hand side the range index. And now we could also call the info method on our data frame, so this is kind of a workaround. And this works pretty well. So here we can see that we have only one column, it's the h column. Alright, these were the very first steps with the pandas series, and in the next lectures we will go into more detail, so hope to see you there. Bye. In this video you will learn when and why to use the copy method. So first of all we import here pandas, and we import our Titanic dataset. So that's the first 5 rows here. And in the last videos, we selected a numerical or a non-numerical column, and we analyzed the column and played around with it. That's a typical workflow with pandas, selecting a subset of a data frame, for example a column, and playing around with it. But actually we do not want to change the original data frame. And that sounds easy, but there's a severe pitfall here that causes one of the most frequently made mistakes when working with pandas. Again, we select here the h column and save the h column in the variable h here. And let's have a look. So these are the first 5 elements. And let's assume that we want to change the third element here at index position 2. And the passenger here is not 26 years old, but 29 years old. And we can actually change and override that element by selecting the element here, for example, with the ilog operator, and we assign the new value 29. So let's do this here. And here we get a warning message, the so-called setting with copy warning. And it says here a value is trying to be set on a copy of a slice from a data frame. So this sounds weird actually, but let's simply have a look what we did here with our code. So we have a look here first of all on our h column here. So that's the 5 elements. And we can see here that we changed the third element from 26 to 29. And let's also have a look here at our Titanic data frame. And the intention was actually not to change the element here in the overall data frame, but that's exactly what we did here. So also here we have 29. And that's really a severe pitfall here in pandas. So we only intended to change an element in a slice of a data frame, so here in our h column, but we effectively changed also the overall data frame. And there's a simple workaround to prevent this behavior here. And let's go up again here. So let's rerun here the cells. So again, we import here the Titanic CSV file. So again, here we have 26. And now we want to select the h column, and we want to play around with the h column, but we do not want to change the original data frame. And there's a simple workaround. So we chain here the copy method. And by doing so, pandas creates a separate object. So our h column that is stored in the variable h is completely independent now from our Titanic data frame. And before, without the copy method, the object that was stored in the variable h was not independent from the data frame. And in fact, the object that was stored in the variable h was a view on the data frame. So it was actually still part of the overall data frame. And we can prevent this by creating here a copy. And let's do this here. And let's repeat the process that we change here the third element to 29. And here we can see we do not get any warning message. And let's also check here the consequences on the object that is stored here in the variable age. So here again we have changed the third element, but here in our original data frame we did not change the element. So here we have still 26. So that's the most important use case for the copy method, and with this we are finished here, and I hope to see you also in the next video. Bye! In this video we learn how to sort panda series. So let's assume we have the age column of our Titanic dataset, and we want to sort the age from young to old or from old to young. And we can do this with the sort values method. So that's option number 1. We can sort a panda series by values, but we can also sort a panda series by the index. So let's go into our examples here and we import pandas. And then we create a dictionary with daily sales. So we have on Monday, so 1 stands for Monday, we have 10 sales. Then we have Wednesday, 25 sales. And then we have Tuesday, 6 sales. So our dictionary here is not really sorted. So Wednesday comes before Tuesday. Then we have Thursday, 36 sales. Then Friday, 2 sales. Saturday, 0 sales, because we do not work on Saturday. And Sunday, as we do not work on Sundays as well, we have also 0 sales, but instead of having here 0, we have just here none, so we can do this, and let's see what we get here. We get here a dictionary with weekdays values pairs, and you can see here on Sunday it's still the value none included. So let's pass our dictionary to pd.series and let's create a panda series. So now you can see here our panda series with on the left side our keys of our dictionary and in the same order as we passed it. So beginning with day 1 and then day 3, day 2, 4, 5, 6, 7. So here again. And we also have on the right side the values. And here you can see on Sunday we have a NaN or missing value. So the keyword none actually transforms in a pandas series in a pandas data frame to a missing value NaN. And as we do not have here the right sequence in our index, so starting from Monday but then having Wednesday and then Tuesday, we can sort our index with the sort index method. So now you can see we have our index sorted starting from 1 and then we have 2, 3, 4, 5, 6 and 7. And we can also determine whether we want an ascending or descending order. So by default here we have an ascending order starting with the lowest index. So here 1. So here with the sort index method we have a parameter ascending. So let's press Shift Tab here and have a look. So here we have the ascending parameter and by default it is set to true. So let's run again here. So we have here the ascending order, but we can change this to the descending order by setting the parameter to false. So now we have the descending order starting from Sunday or from 7 here, 7, 6, 5, 4, 3, 2, 1. Alright, so now let's change it back to ascending order. Alright, so now we have changed here our panda series sales by sorting the index, and let's print again our panda series. And now you can see here that our change, so sorting the index, is not stored in memory, so we haven't actually changed our series here. And what we did here actually, we just created a copy of our panda series sales and we sorted the index of the copy only. But yeah, what if we want to change our original series and there's a solution for it. So let's go inside the sort index method and check with Shift Tab, and here is the parameter in place. And in place is by default set to false, and if it's true it performs the operation in place. So what in place is doing, if it's set to false, all changes we made, so for example sorting the index, are performed only on a copy and the original series has not changed. And if we set the in place parameter to true, then all changes also apply for the original series, so the changes in place. And the in-place parameter in pandas is a very important parameter, and you can see it in many methods for panda series and also for panda data frames. And it helps you a lot to understand if a change is actually made on a copy or on the original panda series or data frame. And yeah, depending on what you actually want to do, you can set the in-place to true or false. So let's explicitly here introduce the in-place parameter, and by default is set to false. So now here we created a copy of sales and sorted the index, and if we print our original sales, it's still not in place, the change here, but if we change the in-place parameter to true, and now you can see here we do not see any printed copy of the sales, so that's the first good indication that we changed the original sales panda series. And let's print here our panda series, and now we can see that yeah, the change is in place. So here we sorted our index and we changed our original panda series sales. Alright, so now let's head over to sorting values. So far we only sorted our panda series by the index, and we can also sort our series by the values. And we set in place to false, and let's see what we get here. So by default the in place parameter is set to false, so I only want to make this explicitly here. And we can see here on the right side we have sorted our sales panda series by the values and in an ascending order. So starting from 0 sales on Saturday and ending with 36 sales on Thursday. And the NaN value is at the very end. And also for the sort values method there are some parameters. So we have the ascending parameter where we can determine whether we want to sort in an ascending or descending manner. So by default the ascending parameter is set to true, but we can set it to false. And let's check here. So now we sorted our values in a descending order, starting with the highest value 36 on Thursday. And we can also determine here, you can see that still our NaN value is in the last position, and we can also determine the position of NA values. So here we have last, but we can also change this, for example, to first. So now here we have our NaN value at the first position. But in the end, so it makes more sense to have it at the last position. And sorting our sales from high to low makes sense, so we keep ascending equals false. And once we are happy here, we can set our in-place parameter to true. And in this way we save our changes actually in our original panda series. So let's run here and let's print our series. And here we can see that the changes we make here are in place. Alright, so now let's again create our dictionary, and now with Monday, Tuesday, Wednesday and so on as strings. And we can pass also this dictionary to pd.series and create a panda series. Let's have a look here. And now if we sort the index with the sort index method, then let's see what we get here. So then our index is actually sorted in an alphabetical manner. So Friday starts with an F, and then we have Monday with M, Thursday, Tuesday and Wednesday. So if we have a numerical index, then the numerical index is sorted from high to low, and with a string index it's sorted alphabetically, and we can also change here the order from ascending to descending. So now it's starting with the Wednesday. W. Alright, so now we are finished with this video. In the next video we'll have a look at the methods n-largest and n-smallest. So hope to see you there. Bye! In this video we will have our first steps with the pandas index object. And first of all let's import the pandas. And we also import our Summer Olympics medals dataset and store it in the variable summer. And we have a look at the first 5 rows and the last 5 rows. And we can call the info method to have a look at some metadata, and we can call the attribute index. And with the attribute index, we can get information on our row index and the row index labels. Here we have a range index starting from 0 till 31,164. So we can also check the type of the index here, and it's a pandas index, range index. And we can do the same with the columns, so we can get additional information on our column index and our column labels with the attribute columns. So we can see here that it is a index object with here the index labels or column labels. And we can also check the data type, and it's a index object here. And actually here it looks a bit like a list or an array. However, compared to a list or an array, the index object or index data type has special methods and attributes specifically designed for large data sets. So with index objects you can do much more than, for example, with a list. And that's why developers of pandas created the index object to allow special index operations. And with the attribute axes we can have a look at both row index and column index. So here we can see for the row we have a range index, and the column index is an index with the following labels here. And we already learned that we can customize the import with the read CSV method, and we can say that as index column we want to have, for example, the column athlete. So now we have here on the left side the athlete column as a row index. Let's run here. And now if we call the index attribute, we get here the new index with our index labels, so the athletes here. And the type of the index is not a range index, but an index with string objects. Alright. And also with index objects we can select and slice single and multiple elements of the index object. So for example, if you want to slice the columns index for the first 3 elements, we can slice from the very first element until the 4th element at index position 3 excluding. So here we have the first 3 elements. So this is position-based indexing with all the rules of zero-based indexing. And we can also select in the row index in the first element, for example. It's Alfred Haryos, and the last element, it's Jimmy Lidberg. And we can make slices from the 100th position until the 102nd position excluding. So I would expect to have 2 elements here. So we have Alfred Flatto and Gustav Felix Flatto, so that's maybe brothers. So before we said that the index object has specific methods and attributes which makes it so powerful, but yeah, actually it looks like a list, and we can transform also a index object into a list with the method toList. So now before we had the index object, the column index object here with our elements, and we saw here that it's an index object, and here we have just the list with the year, city, sport, discipline, country, gender, event and medal. And before we learned that with the label-based indexing it makes a difference if we have only unique values in our index or if we have also duplicates. So if we selected Michael Phelps, we got all occurrences in the data frame, and if we only have unique values or labels in our index, we get only single results organized in the panda series. And also with label-based slicing, so for example, if we slice for all rows from the beginning of our data frame until Michael Phelps, it does not work because slicing with duplicates does not work actually, and there it definitely makes sense to check our index if there are duplicates or if all labels are unique and there is the attribute is unique. And here in our summer index with our athletes we get a false. And last but not least there is another attribute called getLoc, and if we pass a index label to getLoc, we get the position of the index label. So let's try Dimitrios Rivas. And we get a 2, so this is index position 2, and we know that zero-based indexing applies, so let's check it. Here we have our index object, and at position 0 we have Alfred Hayos, at position 1 Otto Herschmann, and at position 2 Dimitrios Rivas. Alright, so now we are finished with this session, and I hope to see you in the next session. Bye! In this video we learn how to change our row index in a data frame, and we have already seen that by default we have a range index starting from 0, but in many cases it might be beneficial to have a different row index that enables us to label-based indexing. But first of all, let's import pandas, and we import our Summer Olympic Games dataset and store it in the variable summer, and we have a look at the first 5 rows. And we have a look at the index, so we have here a range index starting from 0. And we have already learned that we can change the index and select a column as the index and importing our data with the read CSV method. So we can say here index column equals, and let's say we want to have the athlete column as our index column, so we can pass athlete. And now we have here on the left side our athlete column as our index of the data frame. And we can check the index here. And here we can see our index is now the athletes column. So now what if we are not happy with our index and we want to change it back to the range index, and therefore we have the method reset index. So let's just try it out here. And we can see here on the left side, we again have our range index, and our athlete column jumps back as a column. So it's not anymore an index, but a normal column of our data frame. And we can also check here the parameters. And we have one parameter drop equals false. So this is set by default to false. So let's try it out again. And what if we set this to true here? Then we completely drop our index that we had before. So before we had the athlete column as our index, and if we set the parameter drop to true, we completely drop our index and replace it by the range index. And you can see here there's no athlete column in our data frame. So that's in this case actually not what we want. So we change it back to false. Now again we have our athlete column in our data frame, and also in the reset index method there is the in-place parameter. So by default it's set to false, so we do not change our original data frame, and if we want to change our original data frame and change the index back to the range index, then we have to set the in-place parameter to true. So now if we run here, so now we can see here that we do not get a view on a copy, so this is a good indication that we changed our original data frame. And let's check with the head method. And there we can see here on the left side, again we have a range index, and still we have our athlete column as a normal column of our data frame. So now let's assume that before we were not happy with the athlete column as the index, but now we want to have the year column as our index. And there are actually two ways to do it. So either we do this already when we import the data and set here the index call to year, or if we have already imported our data, there is in the set index method to do this. And let's press Shift Tab here. So the set index method set the data frame index using one or more existing columns. So what we can do here, actually we can pass the column that we like to have as the index. So in this case year in quotation marks, and let's see what we get here. Then here on the left side as in the index we have the year column. Alright, so let's again press Shift Tab here. And there's a parameter called drop. And by default drop is set to true. That means if we set the year column as index, it will be removed as an ordinary column. And if we change this and set the drop parameter to false, the year column will not be removed as a column. So in the end we have the year column twice, as an index and as an ordinary column. So let's check this out. So by default it's set to true. And here we can see that we do not have a year column as column, but if we set this to false, then we still have the year column as column and as index. So let's change it back here to true. And let's set the in-place parameter to true. And let's check again our data frame. And now we have the year column as index. And we actually removed the year column from the columns, so there's no column year. And now we can also check if the index is unique. So I would assume that we get a false, because already here we can see that we have duplicate values, so 1896. All right. So now we have learned how to change the complete index, so we can reset our index to a range index, and we can set a complete column as our new index. But what if we want to change only one element of our index? Then we can try this. So let's have a look here at our summer index. So we have here our year column as index, and if we select the first element, so here it's the first element 1896, and if you try to set a new value, so for example 1894, then we get here an error message: index does not support mutable operations. So with other words, the index object is immutable. And we can also try to set a new value for all elements of the index object, so-called broadcasting. So we can say that for all elements in our index, we want to set the new value, so the string here, before 2016, and we can try this. And again, we get here an error message. So this does not work. But what we can do, we can pass a complete list or sequence that has exactly the same amount of elements as our index, as the new index. So first of all, let's check the size of our index. So we have 31,165 elements in our index. So if we pass a list or a sequence with 31,165 new elements as our new index, this should work. And therefore we're creating here a list with 31,165 elements. And we want to have a new label, and starting from medal number 1, medal number 2, medal number 3, and so on. So we want to enumerate our medals from medal number 1 until medal number 31,165. And therefore we use here a list comprehension. So for E in range 1 till 31,165 including, we name our elements in our new list medal number 1, medal number 2, and so on. So now let's create our list here and let's have a look. So here you can see our list. So it starts with medal number 1. And yeah, in the end we are ending with medal number 31,165. And what we now can do, we can say, okay, we want to set our index to new index. So new index, here is our list, and let's try out if this works. Alright, we do not get an error message, and let's check the first 5 rows and the last 5 rows. And here we can see that we have set our list new index as the index of our data frame. And let's also check the last 5 rows. So starting from medal number 1 till medal number 31,165. And we can also check if our row index only has unique values, so I would assume so, yes. Alright, so and there's an additional attribute called index.name, and let's check if we have a name already for our index. And here we run the cell and we see nothing, so there's at this point no name for our new index, but we can set a new name by assigning, for example, medal number. So let's try this out. And let's again check the first 5 rows here. And now here we can see that we have a name for our index. So we have medal number. And now if we apply again the reset index method, we can see here on the left that we again have a range index, and our index that we had before here, medal number, is now a column of our data frame with the column label medal number. Alright, so now we are finished with this video, and I hope to see you in the next video. Bye! In this video we learn how to change column labels of our data frame. So first of all, let's import pandas as always, and we import our Titanic data set. And we have a look at the first 5 rows and the last 5 rows. And then we can have a look at our column labels with the attribute .columns. So it's here survived, p-class, sex, age, and so on. So same as here above. And we can also index our column index object, for example, for the first element. So the first element at the index position 0, it's survived. And now let's assume that we are not happy with the word survived. So we would like to change it to alive, for example. And we can try to do so by setting alive as the new value. So let's try this out. And here we get an error message. Index does not support mutable operations. So same with row index objects. Also column index objects are immutable. So we can only change the whole index by passing a list or a sequence with new values that has actually the same amount of elements in our index. So in our example here we have 9 elements, and we can pass a list with 9 elements. So for example, we can say that our column labels should be alive, class, sex, age, zip SP, parents and children, fair, embarked, and deck. So for each column label we pass here a new column label. And let's try this out. And let's have a look at the first 5 rows. So now we can see here we have changed all column labels. So we have here alive, class, sex, and so on. And we can also set a name for our column index object. So there's the attribute name. And so far we do not have a name for our index object, so we get nothing here. But we can change this, for example, to passenger characteristics. So now let's see again here. And there you can see here we have a name now for our column label. So these are the passenger characteristics. And we can also set a name for our row index. So let's try this out. So with .index.name, and so far we do not have a name, but we can change this to, for example, passenger number, so starting from 0 till 891. And let's check again here the first 5 rows. So now we have here a name for our column label, so passenger characteristics, and we have a name for our row index, passenger number. Alright, so now in this video, in the last video, we learned how to change the complete row index or column index, and we learned that an index object is in general immutable. But there is an option to change single entries of our index objects, and in the next video we learn how to do this, so hope to see you there. Bye! In this lecture I will show you how to change or rename row and column labels. And first of all we import pandas, and we are working with the Summer Olympics dataset with the column athlete as the index. And now let's assume that the spelling of Alfred Haryos is incorrect, and the correct spelling is Haryos with a Y instead of a J. And we've already learned that pandas index objects are immutable. So the following does not work, so we cannot simply select the element Alfred Haryos and try to override it or assign a new value. Here we get an error message, and it says that index is actually immutable. But there's a solution for it, and we can actually use the rename method. And there are actually two ways how to do it. And first of all, let's have a look at the first option. And we have the parameter mapper. And here we have to pass a dictionary with a key value pair. And on the left-hand side, we have the key, which has to be the old value. So Haryo with a J. And as a value on the right-hand side, we have to pass the new label, Haryo with a Y. And finally, we have to define whether we want to change a row index label or a column label. And there's the axis parameter. And here we have to pass either index or columns. And in this example, as we want to change a row label, we have to pass index. And let's have a look here. And here we have the new spelling with a Y. And now let's come to the second alternative. And this is, in my view, the better alternative as it has less code. So again, we have the dictionary with old versus new label. And then we can directly pass the dictionary to the parameter index. So we know that we want to change an index or row label, and therefore we have to pass the dictionary to index. And again, if you really want to change our data frame in place, we have to pass true to the in place parameter. So the default setting is false. And let's run the cell. And we have successfully changed here the first row label. And we can also change column labels with the rename method. And this works pretty much in the same way. And also here we have two options. So let's have a look at the first option. And we have the mapper parameter. And now let's assume that we want to change the column label sex to gender and city to host city. Then, of course, we can also change more than just one label here. And we can have more than just one key value pair in our dictionary. So here the key value pairs are simply separated by a comma. So this is an ordinary dictionary. And since we want to change column labels, we have to pass columns to the axis parameter. So this works pretty well. Now we have host city and gender. And finally, let's come to the leaner and cleaner option. So we directly pass the dictionary to the columns parameter. And also here, if you really want to save our change, we have to pass true to the in-place parameter. And we have successfully changed the data frame summer. And here we have host city and gender. All right, thanks for watching, and see you also in the next video. Bye. In this video we learn how to filter our data frames, and so far we selected rows of a data frame only by index position or index labels. So for example, we selected the first 20 rows, or we selected all rows with the index label Michael Phelps in our Summer Olympics data set. And actually in real world, the more important case is to filter a data frame based on information in one or more columns. So for example, in our Titanic dataset, we want to filter all male passengers on the Titanic, or we want to filter all passengers that are younger than 14 years old. And first of all, before we start, let's import pandas. And we are working with the Titanic dataset, and we will have a look at the first 10 rows here. And what we want to do now is we want to filter out all rows where the passengers are male. So in the end, we want to create a data frame with only passengers that are male. And therefore, we select our sex column, and we will have a look here at the first 10 elements in our sex column. So here you can see our sex column. And now we want to check element-wise each element if the element is male or female. And this works essentially the same way as with NumPy arrays. So let's use here the double equal sign, and let's see what we get here. We get actually here a brand new panda series with Boolean values. And pandas does this in a vectorized manner, so we do not need any for loops like with lists. So pandas checks here for each element. So let's start here with element 0. here we have a male and male is equal to male, so we get a true here. Then we have 3 times female, then we get here 3 times a false, and then again 4 truths. So now here we have a panda series with Boolean values for each passenger, if it's a male or female. So from index position 0 to 890 here. And now we can filter our data frame and we can pass here our panda series with Boolean values into spare brackets of our Titanic dataset. And this works essentially the same as with NumPy arrays. So by passing our Boolean series here within the spare brackets, we filter out all rows where the passenger is male. So let's try here. And we get here a brand new data frame with only male passengers. And what pandas does here, pandas checks the row-wise if we have a true or false in a row. So for example, let's go back here to our panda series and we can see here, so in row 0 we have a true, and in our new male data frame we have also the row with index position 0, and in index position 1, 2 and 3 we have a false. So in our new data frame we do not have the rows with the index position 1, 2 and 3. And then again for the index positions 4, 5, 6, 7 we have a true, we have a male, and now a new data frame we have here the rows 4, 5, 6, 7. Alright. So let's copy here our code. And what we can also do, instead of having here the square brackets notation, we can also use the log notation and filter for all rows where the sex column is male. So this works as well. So we have here the same result, actually, the same new data frame. And if you ask me which notation to use, I would clearly recommend the log notation, and that for 2 reasons. So first of all, with the log notation, we can also filter here not only for rows. So here we want to have all rows where we have a male. And in addition, we can also filter for columns. So we can make here a comma, and then we can say, okay, I want to have only the fair column. So for all male passengers, I want to know the fare they paid. And now here we have a panda series with all the fares that the male passengers paid. And with the spare brackets notation, you cannot do this within here one spare bracket. So let's go back. So here in this case, if you want to filter or only select the fare column, you have to add here another spare bracket and filter for the fare column. So this gives actually here obviously the same result. So the first advantage of the log notation is actually that you only have here one spare bracket, and the code is actually easier to read, and it's more comfortable. And here you have 2 spare brackets, and this is a so-called chained indexing. So what you are doing here, you actually chain index operations. So first of all, you filter the data frame for only males, and then in the second step, you select only the fare column. And chained indexing is actually a very bad way to filter your data frame, because it creates huge problems and confusion when it comes to manipulating data frames, so changing elements in the data frame. And we will see and check this later in our course, so chained indexing is not a good idea. And if you are already familiar with pandas, you might have learned filtering here with the spare brackets notation. But this is a clear recommendation from my side. Please use here the log notation. So again, as I said, when it comes to manipulating data frames, you will have less problems with the log notation than here with the spare brackets notation. Alright, so now let's move on here. And as a matter of taste, we could also call our pandas series with the Boolean values here, Titanic.sex equals male. We can also assign the variable mask. So here mask 1. And again, here we get our Boolean series. And to increase the readability of our code, we can now also pass mask 1 to our log operator here and filter our Titanic data set in this manner. So this Gives us, of course, the same result, but it's a bit clearer and it improves the readability. So this is a better style than passing here the whole line here into the spare brackets. But the result is the same, of course. And what we also did here, actually, we saved our brand new data frame with only the male rows to the variable Titanic male, and we can now print and check our new data frame. We check the first 5 rows, and we have here our brand new Titanic male data frame with only male passengers. And with the log notation, we not only can filter for specific rows, but we can also filter specific columns. So we learned that before, but we can do more than just filtering, for example, the fair column or the age column. What we can do, actually, we can check here the data types of our columns with the attribute Titanic.dtypes. And here we got the data types of our columns. So in the survived and passenger class column, we have integers. In the age and fair column, we have float objects. And also here in the zip, sp, and parch, we have integer objects. And in the sex, embarked, and deck column, we have actually strings. And now what if we want to filter our data frame? So we want to have all rows where we have a male, and we only want to have the columns with numeric objects. So we want to filter for the columns survive, passenger class, zip, sp, parch, and fair. And we do not want to have the string columns sex, embarked, and deck. So now we could check for each column if the dtype is object and call it mask2. So now we have here for the sex column, the embarked column, and the decked column are true, because here we have string objects. And then we can also filter our Titanic data frame with the log notation. So we want to have all rows, and we want to have the opposite of mask2 with the tilde symbol here. So if we would filter for mask2, we would get all columns with string objects, and with the tilde symbol, we get all columns with actually numeric values here. So let's try this one. So here we get all rows of our Titanic data frame with only numeric columns here. And we can further customize here our filtering and pass mask1 and the opposite of mask2. And then we get here all rows where we have a male passenger, and we only get the columns that have numeric data. So we have survived, passenger class, age, zip, sp, parch, and fair. So here with the log notation, we can not only filter for rows, but also for columns. And with the spare brackets notation, this wouldn't be as easy as we have it here with the log notation. Alright, so now we are finished. So the key message is, when we want to filter data frames based on a condition that is in a column, you should always use the log notation. So that's here a clear recommendation from my side. Alright, so see you in the next session. Bye. In this video we learn how to filter data frames based on many conditions that must all be met. So first of all, we import pandas, and we are working with our Titanic data frame. And here we have the first 10 rows. And from the movie, we know that after hitting the iceberg, there was a clear code of conduct to first save all women and children. So women and children had priority for the few lifeboats that were on board. And therefore we can make the hypothesis that being an adult man was a pretty bad combination for surviving the disaster. And yeah, actually what we want to do, we want to check now if the data supports our hypothesis. So we want to filter all male that were older than 14 years old. So we use here 14 years, but we could also use 16 or 18 years. And actually we have two conditions. So the passenger must be a male, so Titanic.sex equals male. And we store here the Boolean series in the mask1 variable. And the second condition is that the age must be greater than 14, and we save the resulting Boolean series in the variable mask2. So let's check here, and we check the first 5 elements of each mask. So now we have to combine both conditions with an AND operator, and only if both conditions are met we get a true. So for being an adult male, the person must be a male and it must be older than 14 years old. So we can here use the AND sign and combine mask 1 and mask 2 with the AND sign, and we will have a look at the first 5 elements. So let's go to index position 0. Here we have true, and true gives true. Then index position 1 we have false, and true gives a false because both conditions must be met. And at index position 2 we have false and true again, and we got a false, and so on. And now we can pass mask 1 and mask 2 into our log operator, and by doing so we can filter out all rows where we have a male passenger that is older than 14 years old, and we can also select here for the columns. So we are only interested in the survived column, in the passenger class column, in the sex column, and in the age column. So we create here a brand new data frame, and we store the data frame in the variable male survived. So let's run here the cell and check the first 5 rows of our new data frame. And here we have our new data frame where we have only male that are older than 14 years old. So we can also check, let's say, 20 rows. So only male passengers and only male that are older than 14 years old. So this works here. Alright, so now we can also get more information on our new data frame with the info method. So we have in total 414 passengers that are male and older than 14 years old. And let's use the describe method. So we have 414 passengers. And we actually know that in the survived column we have a 1 for survived and a 0 for not survived. And we have a mean here of 0.17 in our survived column. This means that only 17% of all male passengers that were older than 14 years old actually survived the Titanic disaster. And let's recall the survival rate for all passengers. So let's use the describe method on the total data set here. And here we can see that on total 38.3% of all passengers survived. But in the subset of male passengers older than 14 years old, only 17% survived. So it's pretty likely that our hypothesis is true, that being an adult male passenger on board of the Titanic was a pretty bad combination for surviving the disaster. Alright, so now we are finished with this session, and hope to see you in the next session. Bye! In the last video we learned that being an adult male on the Titanic was a pretty bad combination for surviving the disaster. So now we want to check the opposite hypothesis, and we know that there was a clear code of conduct to save women and children first, and what we want to do now is actually we want to check if being either a female or a child was favorable when it comes to surviving the disaster. So first of all we import pandas, and we work with our Titanic data frame. And we have actually 2 conditions. So we want to check if we have a female, and we store the resulting panda series with Boolean values in mask 1. And as a second condition, we check whether the age of the passenger is less than 14, and we store this in mask 2. So now we have here 2 panda series with Boolean values. And now we want to combine both conditions with an OR operator, so we have to use here the pipe symbol as OR. And the pipe symbol stands for the logical OR. So by combining mask 1 and mask 2 with the pipe symbol, we should get all passengers that at least meet one condition. So we should get adult females, we should get young boys, and at least one condition means that we also should get all passengers that meet both conditions. So we also should get girls below 14 years old. So let's combine here mask 1 and mask 2, and let's have a look here. So we get also here a Boolean series. So if we have a look at index position 0, we have false or false. So no condition is met and we get a false. And let's have a look at index position 1, where we have true or false. So at least one condition is met and we get a true. So here we have no example where we have 2 times true. So maybe let's increase here to 10 rows. That's still not enough here, maybe 20 rows. So I'm searching now a young girl. So here at index position 10, we have a true for the female, so it's female, and also we have a true for being younger than 14. So we have true or true, and this gives us, by combining it with or, this gives here also a true. And now we can pass the combined Boolean series here to our Titanic dataset and the log operator. And by doing so, we are filtering out all rows that meet at least one condition. So let's check it here. So here we have adult females, then we have a baby male, adult females, a very young female here, a very young male here. So we created here a brand new data frame with only females and young boys. Alright, so now we can further filter our data frame. So we again use mask 1 or mask 2, and we are only interested in the survived column, in the passenger class, sex and age. So we are creating here a brand new data frame, and we are storing the data frame here in the variable women or children. And let's check here our new data frame, the first 5 rows. And let's get more information on our data frame here. So we have 351 entries. So we have 351 passengers that are either women or children. And let's use the describe method to get even more information. And we see here in the survived column, so we have a mean of 0.72, and that means with being either a woman or a child, the probability of surviving the disaster was actually 72%, and that's quite high actually. So we can also compare this to the survival rate of all passengers, and we already know that the survival rate of all passengers was only 38%. So actually our data set supports our hypothesis that being either a woman or a child was a very favorable characteristic on board of the Titanic to survive the disaster. Alright, so now we are finished with this session, and I hope to see you in the next one. Bye! In this video we learn how to use some more advanced filtering techniques with the methods between is-in and the tilde operator. So first of all, let's import pandas, and we are working with our Olympic Games medals dataset. And now let's assume that we want to have all medals from the Summer Games in 1988 in Seoul. And we can filter our data frame by checking in the year column if the value for each row in the year column is 1988. And by doing so here, we're creating a Boolean series, and by passing the Boolean series here to the log operator, we are creating a brand new data frame with only rows that fulfill the condition here. So let's try it out and store the new data frame in the variable Olympic Games 1988. And let's check head and tail. So you can see here that we only have medals that were awarded in the year 1988 in Seoul. Let's check also the info method. So we have in total 1,546 medals. And now what if you want to have not only the medals for 1 year, but for example all medals since 1992. So from the edition in 1992 in Barcelona, including until today. And what we could actually do, we could create a Boolean series for each edition. So let's say we create a Boolean series for 1992, then a Boolean series for 1996 with the equal sign and so on. And then we could combine all Boolean series with an OR operator. Or what we could do, we could simply use the greater equal sign. And there we are filtering all rows where the year is 1992 or later. So we do not have to use here many conditions and combine them with an OR operator. We can just use here the greater or equal sign. And let's do this and save the new data frame in the variable Olympic Games since 1992. And let's have a look at the first and last rows. So here we can see we have a data frame starting from 1992 until 2012. So the data set ends here in 2012 and the 2016 edition is not in our data frame. Alright, so now let's assume that we want to have all medals that were awarded in the 1960s. So we want to include all games in the 1960s. And we can do this with the between method. So we can first of all select the year column and then use that between method and check if the values in the year series are between 1960 and 1969. So let's check this here. So we get here a Boolean series, and obviously here for the very first rows we get a false because the data frame is starting with 1896. And now again we can pass here our Boolean series to our complete data frame with the log operator. And with the between method there is one additional parameter here. So with the between method we have to define the left boundary, it's 1960, and the right boundary, it's 1969. And we have to define if the boundaries are inclusive or exclusive. So since we want to have all editions in the 60s, we pass here true. And here we're creating a brand new data frame and we are storing the data frame in the variable Olympic Games 60s. So let's run here the cell. And let's have a look at the first rows and the last rows. And you can see here we are starting with the rows where the year is 1960, so we have here the edition in Rome, and we are ending with 1968 in Mexico. So, and this is actually the good thing with the between method, that this works even if I'm not sure in which years some Olympic Games took place. So I do not have to pass a specific year where I know that there was Olympic Summer Games, so for example 1964. I simply pass an interval, so between 1960 and 1969, and I get here the medals for the editions 1960, 1964, and 1968. Alright, so far we selected editions that were in a sequential order. So for example here we selected all games from 1992 until today, or here we selected all games between 1960 and 1968. But what if you want to select Olympic Games that are not sequentially ordered? So let's assume that our favorite games were the editions in 1972 and 1996. So they are obviously not sequential because there are games between those two, for example in 1976 or 1992. And let's create here a list with my favorite games, so 1972 and 1996. And now if we want to filter the data frame, we could use two conditions. So we filter for 1972 and for 1996. And we combine those two conditions with an OR operator, or we could use the is-in method. So we select first of all the year column, and then we use the is-in method, and then we pass our list my favorite games with the two values 1972 and 1996. And then Pandas checks for each value in the year column if the value is either 1972 or 1996. So let's run here the cell, and I would expect to get a Boolean series. Correct. And now we can pass here our Boolean series to our summer data frame and the log operator, and then we create a brand new data frame with medals that were awarded in 1972 or 1996. And we call the data frame Olympic Games 72-96. So let's run here. And let's have a look at the first 5 rows and the last 5 rows. So we are starting here with 1972 and ending with 1996. And now let's assume that we deeply analyzed here our data frame, and now we want to analyze all other years that are not 1972 or 1996, and we can do this by passing simply here again our panda series with all rows with 1972 or 1996, and then we can use the tilde symbol, which gives us the opposite. And then we can pass here the whole statement to our summer data frame and the log operator, and we should get a brand new data frame with all medals in all years except the editions 1972 and 1996. And we store the new data frame in the variable Olympic Summer Games, not 72 and 96. So let's check this out here. Let's have a look. So starting from 1896. And we can check with the unique method which unique values we actually have in our year column. So let's check this. And we can see that we have all years except the years 1972 and 1996. So our code worked here. Alright, so now we are finished with this session, and I hope to see you in the next one. Bye! Welcome to the introduction video on NA values or missing values. And before we are going to detect and handle missing values in our Titanic and Olympic dataset, we should first of all understand what NA values are and how and why NA values are generated. And actually NA values or missing values are also a very important topic, because in real data we always have missing values and we always need to handle missing values. And so far throughout the course we already have seen missing values and we have worked with these missing values, and now it's time to dig a bit deeper into this topic. And we have already imported pandas, and we also import here NumPy. And we are working with a sales data set which is stored in the CSV file sales.csv. So let's import this. And let's have a look here. So here on the left hand side, as the index of our data frame, we see the 4 salesmen Stephen, Mike, Andy and Paul. And as columns we have here the weekdays Monday, Tuesday, Wednesday, Thursday and Friday. And the values here in our data frame are actually sales data. So for example, Mike had 45 sales on Monday. And we can see here that for Stephen on Thursday we have here a NaN value. So NaN stands for not a number. And in pandas, this is a strong indication that we have here missing values in our data. So it might be a good idea to also open the original CSV file. So let's do this here. So this is here the CSV file. And we can see here the column labels Monday, Tuesday, Wednesday, Thursday, Friday. And on the left hand side here, the row index labels Stephen, Mike, Andy and Paul. And we have seen that for Stephen we have a NaN value on Thursday. So let's start here with Monday, and on Monday we have sales of 34, then on Tuesday 27, on Wednesday 15, and then again we have here a comma, and after the comma we have actually no value here at all, so no information. So not even a white space or an empty space. And then again we have here a comma, and then we have the value for Friday. So here in our CSV file, whenever we have no value or no information at all, then we get a NaN value in our data frame. So now let's go back to our Jupyter notebook, and we can also call the info method here. So here we have the columns Monday, Tuesday, Wednesday, Thursday and Friday, and we can see here that in the Thursday column we have only 3 non-null values. So obviously here we have a missing value. And we can also select the missing value. So we use here the log operator. And then we are going into the row with the row label Steven. And into the column with the column label Thursday. So let's do this here. And here we can see we get NaN, so not a number. And this is a strong sign that we have here a missing value. And we can also produce some more missing values. So let's go back here to our CSV file. And for example, let's delete here also the sales information for Friday. So let's save here our CSV file and let's go back to our Jupyter notebook. And let's re-import here our file sales.csv. And now we can see here that we have two missing values, so on Thursday and on Friday. And we can also produce missing values with Python. So for example, let's assume that we want to have a missing value at the index position 1, 1. So we take the row with the index position 1, here it's Mike, and then the column at index position 1, it's here Tuesday. So we want to replace here 9 with a missing value. And what we can actually do, we can assign the keyword none. So let's do this here. And let's again check our sales data frame. And now we can see here that we have a NaN or missing value also here for the Tuesday sales of Mike. However, the preferred and more reliable way to produce missing values is by assigning np.nan. So now we are selecting the element at index position 2, 2. So it's actually here 54. And we are assigning the value np.nan, which stands actually in NumPy for missing value or not a number. And let's again check our sales data frame. And now we have also here missing values for the Wednesday sales of Andy. And once again we can call the info method. And now we can see that on Monday we have 4 non-null values. On Tuesday we have only 3 non-null values. And also on Wednesday, Thursday and Friday we have only 3 non-null values, so we have 1 missing value in each column here. And with real data it's sometimes problematic to identify missing values, because instead of having no value or no information at all, there might be some other values that should indicate that there's no value. So let me demonstrate this, and we again go to our CSV file. And we have seen here that on Thursday we have no information or no value at all for Steven. However, it might be the case that somebody, instead of including here no value or no information at all, includes here a white space or an empty space. So let's do this here and let's save here our CSV file. And let's go back here to our Jupyter notebook. And let's re-import here our CSV file. So now let's have a look here at Thursday, and we can see here that we have here in our pandas data frame no information or no value at all. Because here in our CSV file we simply have a white space or an empty space. And also here we have a white space or an empty space, and we can also select here the element with the log operator again. And instead of getting a none, we simply get here a string object which only consists of a white space or an empty space. And if we call now the info method, then we can see here on Thursday that we do not see any missing value. So we have 4 non-null values, because here we have simply a string object with a white space. And with the real data, this is a real problem, because at a first glance we do not really see that on Thursday here we have a missing value. Alright, so now let's have another example. So when working with real data, it is very often the case that people, if there's no data, people assign just a value like no data or missing data. So for example here, for Paul on Thursday we have no value, and then Paul inserted here no data. So let's go back to our Jupyter notebook and let's re-import. And now we can see here on Thursday for Paul that we have here the string no data. And if we call here the info method, and if we have a look here on the Thursday column, we still do not identify any missing values. So still we have 4 non-null or non-missing values. Even in reality we have 2 missing values. So we have here a missing value for Stephen and we have a missing value for Paul. And we can only detect these 2 missing values if we further analyze the columns here. So for example the Thursday column with methods like nUnique, value counts, unique, and so on. Alright, so this was the introduction on NA values or missing values, and in the next videos we learn how to identify and handle missing values in our 2 datasets. So hope to see you there. Bye! In this video we learn how to handle missing or NA values. And this process actually includes 2 major steps. So identifying missing values, and once we have identified them, then we have to decide what to do with these missing values. And there are in principle 3 options. So the first one is that we do nothing and leave them as they are. And actually Pandas is best prepared to handle missing values, since in many methods we can decide whether to include or to exclude NA values. And in most cases the default setting is that Pandas simply ignores missing values. Then the second option is to delete missing values, or more specifically observations or rows with missing values. And we can also delete entire columns with missing values. And then the third alternative is to replace missing values by either the actual values, if you can manage to find them, or to replace by approximate values. So this is in principle a very complex topic, not coding-wise, but in the decision-making process, what to do when, as it always depends on the specific case, and there's actually no black and white. And in this video and in this course we will focus on the coding part. However, in my general Pandas course I will go much more into detail also on the decision-making part. So let's import Pandas, and again we are working with the Titanic dataset where we have many missing values. And let's have a look. And here in the info method we can already see our missing values. So we have here in the H column 177 missing values, or to put it the other way around, 714 non-null or non-missing values. And also in the embarked column we have 2 missing values, and we have many missing values in the deck column. And instead of identifying NA values with the info method, we can do the same with the isNA method. And here Pandas checks for each and every element whether the element is an NA value or not. So here we can see we get many falses, because here we have non-missing values. But here in the deck column we can see many truths, so here we have many missing values. And then we can also sum up the missing values, for example per column, to get the total amount of missing values. So as a short repetition, a true stands for 1 and a false for 0. Therefore we can chain here the sum method. And then we get here 177 missing values in the H column, for example. And actually the opposite of the isNA method is the notNA method. And let's have a look here. So also here for each element we get actually a true if the element is not missing, and we get a false if the element is missing. And again we can also take here the sum. And this is actually the same view as we have here in the info method. So 740 non-null values in the H column. And then we can also filter our data frame, for example, for all rows or for all passengers, where we have NA values in the embarked column, so these are only 2. And therefore we use here the isNA method on the embarked column, and we filter our data frame with the log operator. Here we get 2 passengers where we do not know the port of embarkation. And now let's have a look at the shape of our data frame. So we have 891 rows and 9 columns. And as I said before, we have 3 options how to deal with missing values. And here in the embarked column, this is a very good example where we actually do nothing because we only have 2 passengers with any n values. And also the embarked column is not the most important column here in our data frame. So we just leave it as it is here. So we leave here the NA values. And the second alternative would be to drop NA values. And here we can either drop rows with NA values or we can drop columns with NA values. And to do this, Pandas provides us with the drop NA method. And let's simply run here the cell. And here we have the data frame where we applied the drop NA method, and it's quite hard to identify and see anything. And therefore we also chain here the attribute shape. And here we can see starting from 891 passengers and 9 columns by just using the drop NA method results us in a data frame with only 182 rows and 9 columns. And the drop NA method actually by default drops all rows where we have at least 1 missing value. And as we have over 600 missing values only in the deck column, then Pandas deletes here actually all passengers where we have at least 1 missing value, and we only have left here 182. However, we can change this behavior, and there's the parameter how, and the default setting is any. So by default, Pandas drops all rows where we have at least 1 missing value. And let's again check it here. And alternatively, we can also pass all to the how parameter. And by passing all to the how parameter, then Pandas drops only rows where all values are actually missing values. And let's try this out here. So here we have all 891 passengers. So there's no passenger where we have only missing values. And in the drop NA method, we have also the axis parameter, and the default setting is 0. So Pandas drops rows. But we can also decide that Pandas should drop columns, and therefore we pass 1 to the axis parameter. And again, we can use here any or all for the how parameter. So let's try out the any parameter. And here we get a data frame with all passengers, but only 6 columns. So we dropped all columns where we have at least 1 missing value. And these are actually the columns age, embarked, and deck. And with the how parameter, we are actually quite limited. So either we can define that we want to drop all rows or columns where at least 1 value is missing, or where all values are missing. And this is actually quite unflexible. And therefore, there's the additional parameter thresh. And here we can define how many non-missing values we at least want to have in a row or in a column to leave the row or the column in the data frame. And let's focus here on the columns. So we pass 1 to the axis parameter, and we can say we want to drop all columns where we have less than 500 non-missing values. Or to put it the other way around, we want to drop all columns where we have more than 391 missing values. And let's check this out here. And here we lost 1 column, and obviously this should be the deck column, because here in the deck column we only have 203 non-missing values. And this might be actually a good strategy in our case. So the deck column is actually of little use for us, because the information itself is not too useful, and also we have only 200 non-missing values, and therefore we decide to drop all columns with less than 500 non-missing values. And also here we have to pass true to the in-place parameter. And let's have a look. So here we have successfully dropped the deck column. So as a short recap, we decided to leave the 2 missing values in the embarked column. We deleted the complete deck column. And now let's filter our data frame for all passengers where we do not know the age. So these are all passengers where we have missing values in the age column. And having 177 passengers where we do not know the age, it might not be the best decision to just delete all 177 passengers. So it might be a better idea to replace the missing values. And therefore we can either try to find the re-values, or we can replace the missing values by approximations. And here in this case, one good approximation could be to use simply the mean age over all passengers as a fill value. So first of all, we calculate the mean age over all passengers. And this is 29.69. And then we can fill each and every missing value in the age column with the mean age. And we can do this with the fill NA method. So first of all, we select the age column. And then there's a parameter value. And here we can pass the fill value that we want to have here. So here in this example, it's the mean age. And also here we have to pass true to the in-place parameter. So let's do this. And let's have a look here at our age column. So before we could see here that the passenger at index position 5, we have here a missing value. And now we have here the mean age 29.69. And also finally we can inspect our data frame again with the info method. And here we can see that we have no missing values now in the age column. So we have successfully replaced all missing values here by the mean age. And with this we are finished here with this video, and I hope to see you also in the next one. Bye! In the last video we handled missing values in the Titanic data frame, and we created kind of a clean data frame. And now it might be the case that we want to terminate our Jupyter session and save our progress locally on our computer. And one way to do this is by exporting and saving the cleaned data frame in a new CSV file. So we have still imported here the cleaned Titanic data frame, and we can also have a look here at the first 5 rows. And then we can actually export and save our data frame in a new CSV file, and we can do this with the method toCSV. And here we have to pass our new desired file name. So here, for example, cleandataframe.csv. And let's run the cell here. And actually Pandas creates a new CSV file in the folder where also the Jupyter notebook here is located. And we can also re-import our clean data frame CSV with the readCSV method. And here we can see that we have here an additional column, which was actually the former range index. And whenever we save or export a data frame with a range index, then we also save the range index in the CSV file. And when we re-import the data from the CSV file, then Pandas by default creates another range index if we do not determine a index column. And therefore, whenever we want to export a data frame with a range index, it might be the best option to pass false to the index parameter. So here we have an index parameter, and here we have to pass false. And when we pass false, Pandas drops the index and does not export the index. So let's run the cell, and we actually overwrite the CSV file. And again, we can re-import the CSV file. And here we can see that now we do not have this additional column. We just have here the range index. And with this, we are finished here, and I hope to see you also in the next video. Bye! In this video, we learn how to use summary statistics and accumulations to further analyze our data frames, and in particular data frames with numeric values. So first of all, let's import Pandas, and we are again working with our Titanic's dataset. And we checked the first 5 rows here. And we already know the very helpful describe method. So the describe method returns us many summary statistics for our numerical columns. So we have here our numerical columns survived, P class, age, zip SP, parch, and fair. And first of all, we have count. where pandas actually counts all non-missing values. So here in the age column we have some missing values. Then we have the mean value over all values in the particular column. So for example, the average fare or ticket price was $32 or pounds. Then we have the standard deviation, the minimum, 25th percentile, the median, the 75th percentile, and the maximum. So the oldest passenger is 80 years old. And for most of these summary statistics here on the left side, there also exists a method. So for example, there is the count method that we can apply for the whole data frame, and let's press Shift Tab here. So the count method counts non-missing values for each column or row. So now let's run here. And we get here for each column the amount of non-missing values. And we can define here the axes where we want to count actually the number of non-missing values, and by default it's set to 0. And alternatively we can also pass here in quotation marks index. And with 0 or index we get actually for each column the amount of non-missing values. And in my opinion this is a bit confusing, because we get here for each column the amount, but we set axes to index and not to column. And the reason is that axes equals index means that we go here along the rows and along the axes here for each column. So in my opinion this is a bit confusing, and there might be further room for improvement for the next versions here of pandas. And let's try also columns here, columns or 1. And here we get the amount of non-missing values for each row. And you could say that, okay, we are going here along the columns, and therefore I have to use here the parameter columns. Alright, so either you use columns or axis equals 1, so that's the same here. And then we can also take the mean, and if we set axes to 0, we get the mean for all columns or along the rows. So here again we have for the fare the average ticket price of $32 or pounds. And we could also try to calculate the mean for each row. And we still get here values. So actually if we look here at a row, we have here numerical values in each row, but also string values. So still the mean method returns for each row here a value. And let's check here why this is the case. So let's go here inside. And we have here the parameter numeric only. And let's check this. Include only float, integer or boolean columns, and if set to none, and by default numeric only is set to none, then pandas will attempt to use everything and then use only numeric data. So pandas is quite smart here. It tries to calculate the mean over all values, and if it finds some numerical values and non-numerical values, so string values, it then excludes the string values from the mean calculation. And pandas does this automatically. So here you again can see that pandas is quite powerful and quite smart. Alright, so there's also the method sum, and we can take the sum for each columns. So here for the survived column we have 342. That means that we have 342 passengers that survived. So we have the value 1 for survived and 0 for not survived. And depending on the column, actually the sum makes sense or does not make sense. Here for the sex column we have just male, female, female, female concatenated. So for example, if we want to take here the sum for all rows by passing here 1, we again get the sum over all numerical values. So also here pandas tries to take the sum over all elements, and once it finds some string values, it just ignores the string values and takes only the numerical values. Alright, so let's have a look again at our data frame. And the title of our video is here not only summary statistics, but also accumulations. And one example for accumulation is CumSum. So let's try the CumSum method on the fair column. So CumSum stands for cumulative sum, and we can see here. So we're starting with 7.25. And then for each row, CumSum sums up all rows that came before. So here in the second row, we should have here 78, and then 78 plus 7.9 gives 86, and then 86 plus 53 gives 139, and so on. Alright, let's go on, and there is the method .core, and .core actually calculates the correlation between numerical columns. And the correlation is actually an indication of the relationship of two random variables. So in other words, if and how two random variables move together. And the correlation can take values between -1 and 1. And -1 is an indication for strong and negative correlation, where one variable goes up and the other goes down, and vice versa. And the value of 0, so 0 correlation, stands for, or is an indication for, no relationship between those two variables. And a correlation of 1 is an indication for strong positive correlation. So when one variable moves up, the other moves up as well. And we can have a look here at our Titanic data set. And we can see here on the left, so we have the survived column, and of course the survived column is 100% positive correlated to itself. And we see here that there is a quite high negative correlation to the passenger class. So the lower the passenger class, so we have passengers in class 1, the higher is the likelihood that the passenger survived. So here's the indication that actually money rules the world. Not only in business, but also on board of the Titanic. And here for the age, we have a weak negative correlation. And also here SIP, SP, and PARCH, there's only a small correlation here. And for the fair column, we have a fairly strong positive correlation. So the more a passenger paid for his ticket, the more likely it was that the passenger survived. And we could also have a look here at the fair column. And the ticket price is actually positive correlated to the survived, so we already have seen this. And also ticket price is quite strong negatively correlated to passenger class. So this is a no-brainer. So a passenger in class 1 paid more for his ticket than a passenger in class 3. And we can also see here a positive correlation to the amount of parents and children and the ticket price. So obviously the passengers that traveled with parents and children paid more for their ticket than passengers who traveled alone. So it might be the case that in the first class the passengers traveled with their families in a suite, and in the third class there were many young men who traveled alone, trying to find their happiness in America. Alright, and there's also the core method for pandas data frame, and there we can return the correlation between only 2 columns. So we selected here the survived column, and then with the core method we can calculate the correlation between the survived column and the p-class column. So here within the brackets we have to pass the p-class column as a panda series. And here we get minus 0.33, so the same as here. So if you were a passenger in the third class, it was less likely that you survived the Titanic disaster. Alright, now we are finished with this video, and I hope to see you in the next one. Bye! In this video we are going to plot the data on our Titanic data frame with the method plot. But first of all, let's import pandas, and we import our Titanic data set. So here are the first 5 rows and some meter information. And if you want to create some plots and visualizations, we first need to import the matplotlib library, which is actually the most popular Python library for creating plots and visualizations. And actually, as convention, we import matplotlib.pyplot as PLT. So PLT is actually the most commonly used abbreviation here, so let's do this. And now we want to plot the numerical columns in our Titanic data frame. So we have some numerical columns here. We have the survived column, the P-class column, the H column, zipsp, parch, and also the fair column. And we can do this by simply calling here the plot method on our Titanic data frame. So for pandas data frames and panda series, there is the built-in method .plot. And before we run the cell here, we have to also call the show method. So this is a direct matplotlib.pyplot method. And with the show method, we can actually display our graph or our plot. So always when we create one or several plots with matplotlib, as a very last argument, we have to call here the show method. So let's simply call here the plot method on our entire Titanic data frame, and let's run the cell here. And here we can see that we actually see nothing. So by default, the plot method creates here a line plot with on the x-axis the index. So here we have the range index from 0 till 891. So these are actually the passenger numbers. And on the y-axis, we have actually the specific values in our numerical columns. And for each column, we have actually here a line plot. So we have 6 columns here, and as we have here 6 line plots within one graph or within one plot, it's quite hard to see anything. And therefore, let's go here inside the brackets with Shift Tab. And here we can see we have a parameter subplots. And by default, it's set to false, but we can set this also to true here. And by doing so, we're creating for each column a separate subplot. And still it's hard to see anything because the plot size is very small. And there's an additional parameter here. And it's called fix size. And here we can determine the width and the height of the graph. So let's do this here. We have here fix size. And then we have to pass within a tuple the desired width and height of the graph. So for example, we want to have a width of 12 and a height of 8. Then we get here a larger plot. And maybe we should further increase the size here to maybe 15 and 12. So now it's much easier to see and analyze it. So for each column we have here a separate subplot. So here for the survived column, the P-class column, the H column, the zipsp column, parch column, and fair column. And by default all subplots share actually here the x-axis. So we have here at the very bottom one x-axis with the range index from 0 to 891. But we can also create a separate x-axis for each subplot, and there is one parameter here. And the parameter here is share x. So let's have a look here. And by default it's set to true actually, so all subplots share one x-axis. But we can also set this to false, so let's do this. So we have here the share x parameter and we can set it to false. And now we can see here at the bottom of each subplot the x-axis with the range index from 0 till 891. And we can see here on the left-hand side for each subplot actually the y-axis. And here we have a specific y-axis for each subplot. So for example here for the survived column we have values between 0 and 1. So you can see here it's oscillating between 0 and 1. Then here for the P-class column we have the values 1, 2 and 3. Then for the H column we have values between 0 and 80. And a line plot like this is actually good to see the distribution of values. So the majority of ages are here between 20 and 40, but we have some outliers here around 0 and some outliers here around 75, 80. And specifically when we have time series data with a datetime index, so here we have then on the x-axis a datetime index, so for example starting from the year 2010 until 2015. And specifically in this case a line plot is very intuitive to see the evolution of some factors over time, so for example stock prices or weather data. But also here with non-time series data a line plot makes definitely sense. And here in the zip_sp column we can see that the majority of values are here actually 1. So most of the passengers have one sibling or spouse on board. And also here for the parents and children, the most frequent values are here between 0 and 2. And also here in the fare column we can see that the most frequent fares are actually quite low here between 0 and 20. However, there are some outliers here, so we have here some outliers until $400 or $500. And as we have seen on the left hand side, so for each subplot we have a different scale for the y-axis, but we can also change this here. So there's the parameter share y. So here we have share y. And by default it's set to false, so for each subplot we have a specific and appropriate y-axis, but we can also set this to true. And here we have for each subplot actually the same y-axis with the same scale. And as we have here the largest scale at the fare column, so the shared y-axis is actually most appropriate here for the fare column. So here we have values between 0 and 500. However, for the parch column, a scale between 0 and 500 does not really make sense. So here we actually see nothing. And therefore, in this case, it definitely makes sense to set the share y parameter to false. And actually, if we are only interested in the h column and if we only want to visualize the h column, we can also apply the plot method only on the h column. So let's do this. Let's copy here the code. And instead of using here the plot method on the entire Titanic data frame, we use it only on the h column. And if we only use it on the h column, we do not have to define here subplots. So this is not necessary. And maybe we make the figure size a bit smaller here, because we have only one subplot. And also we do not need the parameters share x and share y. So let's plot here the graph. And here we have actually a line plot only for the h column. So we can see here the x-axis with the index labels from 0 to 890. And we can see on the y-axis values between 0 and 80. And the majority of values are here between 20 and 40. And we have some very young passengers that are only a bit older than 0 years old, so babies. And we have some quite old passengers above 70 and until 80. Alright, this was the first video on data visualization, and in the next video we learn how to customize our plot here. So hope to see you there. Bye! Alright, so in the last video we created a line plot for our h column, and now in this video we will customize our plot here. So for example we will add a title and also labels for our x and y axis, and we will also learn how to change the line style and the color of our graph. So now let's first of all plot again here our line plot. So with no customizations at all. And we can actually see that the font size of our x-axis and the y-axis is quite small. And therefore there's another parameter here. And the parameter is called font size. So let's try this out here. And here we can actually define the font size for our x ticks and y ticks here. And let's try, for example, 13. So now here we can see that we have increased font sizes. And we can further increase the font size by passing here a greater number, for example 20. And now we have even larger font sizes, so let's go back to 13. And we can see here that our line plot has kind of a blue color, but we can also define the color here with the parameter C. And here we can pass our desired color. So for example, we could pass here red. And it's also possible to only pass here R for red. So feel free to have a look at the documentation of what colors are provided here. So now we will use here the red color. And we can also customize the line style. So there's the additional parameter line style. And by default it's set to a single dash here. But we can also create a dashed line, so with 2 dashes. And now we can see a kind of a dashed style. And we can also create a dot style by passing here a colon. Now we have dotted lines. And also here feel free to have a look at the documentation, what different line styles Matplotlib provides here. So let's go back here to the single dash. And now we can also create a title for our graph or our plot. And we can do this with the function or method pld.title. And within the brackets here, we have to define the title of our graph within quotation marks. So it should be Titanic Ages. And then there's an additional parameter font size where we can define the font size. And here for the title, the font size should be a bit larger than the font size of the X ticks and Y ticks. So let's run here the cell. And here we have our title, Titanic Ages. Next, we can also create a legend for our graph. And in particular, this makes sense if we plot here several columns. So let's assume we plot here the age column and the fair column. Then we should have a legend here somewhere saying that, okay, the red line is the age column, and for example, the blue line is the fair column. And we can create a legend with the method plt.legend. And here we can define also the font size and also the location of the legend. But first of all, let's run here. And here we can see on the upper right the legend age. So the red line is the age actually. And if we would have here another line, for example, for the fair column, we would have here red for the age column and blue for the fair column. And we can also define the location. So let's go here inside the brackets. And there are several locations that we can choose. So for example, we can choose the location best or 0. So we can pass here 0 or best within quotation marks. Then depending on the graph, Matplotlib locates the legend at the best possible place. But we can also define upper right, upper left, lower left, and so on. And instead of passing here the strings, we can also pass the codes. So for example, let's assume that we want to place the legend here on the lower left side. We can either pass the string lower left or 3. So let's pass here 3. And now we have here the legend on the lower left location. And with the font size, again, we can also change here the font size, for example, to 20. So we can make it larger. But let's stay here at 15. And we can also create labels for our x-axis and y-axis, and we can do this with the functions plt.xlabel and plt.ylabel. And here we have to pass within the brackets the labels at quotation marks that we want to have. So for example here for our x-axis we want to have the passenger number, and for our y-axis we want to have age. And again here we can define the font size. So let's do this here. Now we have here the X label passenger number and the Y label age. And we can also create a grid here with the function plt.grid. Next we can also define the limits of our axis. So here by default we have on the x-axis the limits between 0 and 900, and on the y-axis between 0 and 80. But we can also change this here, and let's press Shift Tab. So here we can see we have the parameters xlim and ylim, and here for both parameters we have to pass a tuple with the lower and the upper value. So for example, let's assume that we are only interested in the passenger numbers between 200 and 400. Then we can pass here to the parameter xlim a tuple from 200 to 400. So let's run here the cell. And here we only have on the x-axis the passengers between 200 and 400. And as you can see here, some blanks, so these are the missing values in the h column. So here we have a break everywhere where we have a passenger where we do not know the age. And we can also limit or customize here our y-axis with the ylim parameter. And let's assume we are only interested in passengers between the age 20 until 40. So now let's run here. And here we limited our y-axis from 20 to 40. So let's go back here on the x-axis from 0 to 900. And on the y-axis from 0 to 80. And here we can see on the x-axis we have x ticks 100, 200, 300, 400 and so on. But we can also customize this, and let's assume that we want to have ranges of only 50, so 50, 100, 150, 200 and so on. And there's also the parameter x ticks and y ticks, and here we can define the ticks that we want to have. So let's have a look here. So here we have x ticks and y ticks, and here we have to pass a sequence. So for example, a list with values we want to use for the x ticks and y ticks. And now let's assume that for the x-axis we want to have x ticks from 0 to 900. And we want to have a tick for each 50 passengers, so we want to have 50, 100, 150. And for the age we want to have the ticks 5, 10, 15, 20 until 80. And we can do this by creating two sequences or two lists. So here we can create a list for the x ticks, and for the range between 0 and 900 including, we create a list of values with the step 50. So let's run here and let's have a look. So here we have a list starting from 0 till 900, and we have a step of 50, 50, 100, 150. And the same we can do for the y ticks. So we are creating here a list from 0 to 80 including, and with a step of 5. So let's run here. And here we have the list 0, 5, 10, 15, 20 until 80. And now we can pass both lists to the parameters x ticks and y ticks. So we have here the parameter x tick. And here we pass the list x ticks. And we have the parameter y ticks. And here we pass the list y ticks. And let's run here the cell. And here we can see our customized x and y labels. And we can also see that the grid actually automatically adjusts. So we have here the grids for the ticks here actually. And here we can see on the x-axis, if we have many ticks, it might be more convenient to rotate the ticks a little bit to have here more space. And we can do this with another parameter. So let's check this out here. And we have here the parameter rot. And here we can define, for example, that we want to rotate our ticks by 90 degrees. And here we have our x ticks rotated by 90 degrees. And we could also define that we want to rotate them by 45 degrees, so this is flexible. So here we have 45 degrees. And actually now we are finished with the customization. However, there's one more option, and actually we can completely change the whole style of our graph. And we can do this with the method plt.style.use. But before we can also have a look which default styles matplotlib provides us, and we can do this here with plt.style.available. And here we can see several styles. So we have the classic style, then ggplot from the R programming language. Then we have grayscale, and we have several Seaborn styles. And once we have chosen a style, we can also set now a new style, and we can do this with plt.style.use. And here we can pass within the brackets our style that we want to have. And for example, let's choose here the Seaborn style. Now let's run the cell here. And now let's rerun our graph here, and our graph will automatically be transferred to the Seaborn style. And here we have the Seaborn style. And by default, actually, the Seaborn style has also grids, but by calling here the grid function or method, we actually removed the grids. So let's disable the grid function. And here we can see our Seaborn style. And we can also change the style, for example, to classic. And now we have here a classic style. So the options to customize a plot in matplotlib are actually unlimited. And if you like, you can have a look at the documentation site. But for the time being, we are now finished, and I hope to see you also in the next video. Bye! Alright, in this video we will learn how to create a histogram for our Titanic age column. So histograms are specifically useful to visualize the frequency distributions of values in numerical columns. So first of all, we import pandas, and we are also importing matplotlib as PLT, and we use the Seaborn style. And we are importing our Titanic dataset. And before, we also learned that we can analyze the frequency of values with the value counts method. So here we are selecting the age column, and we are analyzing the age column with the value counts method. And the most frequent value is actually 24. So 30 passengers are 24 years old. And here at the end we have some outliers, so 0.42 years, for example. And we can also organize our ages here in bins, and let's have a look here. So there's here the parameter bins, and by default it's set to none. But we can also set the bins to true, and then rather than count values, bins group them into bins. So for example, now let's set the bins to 10, so we're creating 10 bins. Alright, an S is missing here, so now it should work. And here we have 10 equal width bins, so starting here from 0 till 8, then 8 to 16 and so on. And the bin or the interval with the most values is here actually the interval between 16 and 24. So here we have 177 passengers. And the least frequent bin is here between 72 and 80 with only 2 passengers. And the same we can actually do graphically with a histogram. So we are selecting here the age column, and then we are using the plot method. And so let's run here first of all. So here we have our line plot. And instead of passing line, so line plot is actually here the default value. And instead of passing line to the parameter kind, we can also pass hist for histogram. And here we have the histogram. And by default we have here 10 bins, and these are actually the same bins as here above. So from 0 till 8, then from 8 to 16 and so on. And the very last bin is from 72 till 80. And here in this bin we have only 2 passengers. And the largest or most frequent bin is actually here this bin, and this is in the interval 16 to 24. So having here 10 bins is actually the default setting, but we can also change the amount of bins, and there is here the parameter bins, However, if we have here a look with the Shift tab, then the parameter bins is not explicitly displayed here. And this is actually a disadvantage if we use here the plot method. So some specific parameters which are only available for some specific plot types, so for example here the bins parameter for the histogram, are actually not listed here in the plot method. However, at least in this case for the bins parameter we can still use it here. So let's simply call here the bins parameter. And for example, let's assume we want to have 30 bins. Then let's run in the cell. And then we can see here that we have 30 separate bins. And as we have here a range between 0 and 80, it could also make sense to have here 80 bins. So for each year we have one bin. So for example here we have one 80-year-old passenger. And here the largest bin is actually, I think it's 24. Alright, so now we have seen that the plot method is actually not the optimal solution if we have here other kinds than line plots. And in the next video we will also learn some other alternatives how to create here the histogram. But for the time being we are now finished, and I hope to see you in the next video. Bye! In the last video we have created a histogram for our age column, and we did this with the pandas method .plot, where we passed the hist to the parameter kind. So here we can see this. And not only for histograms but also for other plot types, there's more than one way to plot data in a data frame. And in this video I will show you two other ways how to create here the same histogram, and we will see that there are slightly differences and the pros and cons for each way. So in my opinion there's no optimal solution, but let's have a look now. So the second alternative would be to use the direct method .hist. So instead of having here the method plot and we pass hist to the kind parameter, there's also a direct method called hist. And also here we can define the fixed size 12.8, and let's have a look here. So here we have some different parameters in the documentation. So here we have explicitly the bins parameter, and by default it's set to 10, but here we set it to 80. And we can also set the X label size and the Y label size here. So we set it to 15. And we can see that this is a slight difference here to the plot method. So here in the plot method, we can actually determine the X label size and Y label size with the font size parameter. And we've also seen with the direct plot method that there is no explicit bin parameter here. So here we do not see the bins parameter. But if we pass here hist to the kind parameter, then we can nevertheless here use the bins parameter, even if it's not explicitly listed here. Alright, so now we can run here our cell and we actually create the very same histogram. So we have here the same amount of bins, then the same size of the labels here. And we can see here by default that here with the plot method, we have here the Y label frequency, and here we do not have the Y label, so this is a minor difference. And now let's go to the third alternative, where we use the hist method directly on matplotlib.pyplot, so plt.hist. And here we have to pass then the sequence for which we want to have the histogram. So here in this case we want to have the panda series titanic.h. And also here we can set the bins parameter to 80, and let's try to run here the cell. And here we get an error message, and in the end it's because the direct matplotlib hist method cannot by default handle here missing values. So here in our age column we have missing values, and if we pass here our age column to the direct matplotlib method hist, then we have here a problem. So before we can plot here our age column, we have to drop the missing values. And we can do this with the method drop_na. So we will have a closer look later in this course on this here. So drop_na. And by doing so, we are dropping all missing or na values. And now actually our code should work. So let's try this out here. So this looks quite similar to the other graphs or histograms. And let's have a look here at the additional parameters. And we can see here that here we have some more parameters. So for example, we have the density parameter, and by default it's set to false, but we can also set this to true. And then instead of getting here the absolute quantity for all of the bins here, we get the relative quantity. So let's try this out here. So here we have the relative quantity for all bins, and we can also transform here our histogram into a cumulative histogram. So by passing here true to the parameter cumulative. And here we are actually adding up all bins starting from the left-hand side. So in the very end, here we end up with 1 or 100%. So still we have here normalized quantities, and in the end, if we sum over all bins, then we have 100% of the data here included. So here we are ending at 100% or 1. And actually in the other two direct pandas methods, there are explicitly no parameters density and cumulative. But still we can use them, so let's have a look here. So here we do not see any density or cumulative, but still we can use these parameters here. So let's try here the cumulative parameter, and let's set it to true. And here we get the absolute cumulative histogram. So starting from 0 here at the left-hand side till over 700 passengers in total at the very end. And also here for our plot method, for example, we can determine the parameter density. And here we can set it to true. And now we should get on the left-hand side, instead of absolute quantities, relative quantities. And this is true here. So actually the direct pandas methods have the advantage that by default they can handle missing values. But if we have a look at the parameters, not all parameters that the direct matplotlib method provides are explicitly here listed in the parameters. And if you do not know that these parameters exist, so then you could get limited here in the functionalities. So in the end, it's best to at least know all three alternatives and know all parameters that you can actually use. And then in the end, it's actually a matter of taste which one of these alternatives you use. Alright, with this we are finished here, and I hope to see you also in the next video. Bye! In this video we learn how to create two-dimensional scatterplots. So scatterplots are specifically useful to detect the relationships between two numerical features. So for example, in our Titanic dataset, we have the numerical features age and fare. And by creating a scatterplot for these two features, we might get a first visual impression whether there is a relationship between these two factors. So for example, our hypothesis might be that older passengers have more money and therefore pay a higher ticket price. So we will see this in a minute, but first of all let's import pandas, and we import matplotlib, and we are using the Seaborn style. And then we are working here with the Titanic dataset. And now if we want to create a scatterplot for the Titanic data frame, we can call here the plot method, and instead of passing here a line to the kind parameter, we can pass scatter. And now let's press Shift Tab here. So here we have the parameters x and y. And here we have to determine which column should be on the x-axis and which column on the y-axis. And here in our example, we want to have the h column on the x-axis. So we pass here the h column to the parameter x, and within quotation marks here. And on the y-axis, we want to have the fare column. And we've also set the figure size to 15.8. And now we can run here the code. And here we can see the scatter plot for the age and the fare column. And actually each single dot or scatter is a passenger. So for example, here we have a passenger that is 64 years old. and the passenger paid actually about 260 or 70 ticket price. And so we have for all passengers here, where we have non-missing values in the fare and age column, one dot or one scatter here. And apparently with a very first inspection, it's quite hard to detect here any relationship. So our hypothesis was that the older the passenger, the higher the ticket price. So if our hypothesis holds true, then we would actually expect scatters from the bottom left to the top right. But this is actually hard to confirm visually, and in this case you would need to perform some more advanced statistical analysis. So let's move on here with our plot, and actually we can determine the color of the scatters, and we can do this with the parameter C. And here we can pass, for example, red. And there's also a parameter where we can change the type of the dots or the scatters here. And this is called marker. And the default setting is that here we have a kind of a round dot. So the default setting here is this kind here. So here you can see nothing has changed. But we can also change the marker, for example, to D or to uppercase X or to lowercase x. And then we get here actually different scatters. And also we can change the size of the scatters here with the parameter s for size. And here we can pass an integer, so for example let's try 20. And we can also increase the size by increasing here the integer, so for example to 50. And now we have actually here larger scatters. So now let's go back here to 20. And there's actually one more feature where we can transform here our two-dimensional scatter plot into a three-dimensional scatter plot. And we can do this by passing here to the color parameter another column of the data frame. And if we pass here the survived column, then we get here for the dots or for the scatters different colors, depending whether the corresponding passenger survived or not survived. So for example, the passenger here has a white color, and white color actually means here a 0 in the survived column, which means that this passenger did not survive. So in the end we can say that here we have a three-dimensional graph. So the first dimension is here the x-axis age, then we have the y-axis fare, and we have the color, which gives us information whether the passenger survived or not. And we can also change the color style here of the survived column. And there is the parameter color map. And if we have a look at the matplotlib page, then here we can see some color styles. So we have Viridis, Plasma, Inferno, Magma, and some more here. So let's choose here Viridis. And we pass Viridis here as a string. And let's run the cell. And here we can see that we have successfully changed the color map. So now yellow stands for survived and the dark color for not survived. So here in the survived column we only have two different values, 0 and 1, and therefore we have only dots or scatters that are dark or yellow. But let's try also here the column P class. And here we can see now that we have dots or scatters with three different colors. So we have for the third class yellow, then we have for the second class green, and for the first class we have here kind of a dark color. And here we can see visually that the first class passengers paid the highest ticket prices. So we have here the dark scatters or dark plots here at the top. Then we have the second class, the green dots here in the middle. And then at the bottom we have actually the yellow dots for the third class. And actually the relationship between age and P class is less intuitive. However, one could conclude actually that the very young passengers here are more likely to be in the second or third class, and the older passengers are actually more likely to be first class passengers. Alright, this was the video on scatter plots, and I hope to see you also in the next video. Bye! In this video we are going to create our very first seaborn plot, a so-called count plot. But before we need to import pandas and also seaborn, and by convention the standard abbreviation is SNS. So we import seaborn as SNS, and we also import matplotlib. And in this video we are working with the Titanic data frame, so let's also import this here. So here we have the first 5 rows. And now we want to create a seaborn count plot. And earlier in this course we have seen that we can split our data into different groups by using categorical data. And we did this, for example, with the group by method. And with the group by method we were able to group our data by, for example, the sex column into female and male. Or we also created 6 groups by the categories sex and p-class. And with the group by method we were also able to count the number of elements in each group. So for example the number of first class male passengers on board of the Titanic. And exactly this we can do also with the count plot graphically. So first of all we set here the figure size to 12.8, and as a final statement here we have plt.show. So this is nothing new. And now we want to create a count plot, and we can do this with sns.countplot. And let's have a look here inside the brackets. So the count plot shows the counts of observations in each categorical bin using bars. And we have here several parameters, and the structure of the seaborn plots are quite similar. So we always have here the parameter data, and here we have to pass our data frame that we want to plot. So in this example, Titanic. And then in addition we have here the parameters x and y, and here we have to pass one column. So for example, let's assume that we want to count the amount of female and the amount of males on board of the Titanic. Then we pass here to the parameter x our column sex, here in quotation marks. So let's run here the cell. And here we can actually see a bar chart where we have here on the left hand side the amount of males, so it's about 570, and the number of females on board of the Titanic, so about 320 something. So this is here a vertical count plot, but we can also pass the sex column to the y parameter, and now we have the same chart horizontally. So let's go back to the vertical graph. And actually the very powerful thing with seaborn is that we can further split here our data into subgroups. So for example here we can split up the bin for the male passengers into a first class, second class and third class bin. And we can do the same with the female bin here. And there's the very powerful parameter hue, and we can find this parameter in many seaborn plots. So let's have a look here. So here we have the parameter hue, and here we can pass a column with categorical data. So in our example we could pass here, for example, the p-class column. And let's have a look what we get here. So here we actually split up our male bin and our female bin into 3 separate bins. So we have in total about 120 first class male passengers. Then we have here an orange for male and female, the second class passengers, and in green the third class passengers. So here we have our 6th group, and for each group we have the number of passengers which belong to the respective group. And we can also customize and change the style of seaborn plots. And we can do this here with sns.set. So let's have a look here. And it says here set aesthetic parameters in one step. So for example here we can change the font scale. Let's try this out here. So with this actually we can make the font size here on the x and y axis and on the legend larger. So for example let's pass here 2. And now we have here a significantly larger font size. And for example, we can also have some other changes here. So we can change the font itself, or we can also change the color map. So in Matplotlib, we know this as color map. Here we have the parameter palette. And for example, let's call this parameter here. And let's pass the color map variedis. And by doing so, we can change here the color style. And there are actually many more options to customize here our graphs, so feel free to have a look at the Matplotlib and also at the Seaborn documentation. And for the time being now, we are finished here with this first video, and I hope to see you also in the next videos. Bye! In this video we are creating several categorical Seaborn plots, and they all have in common that we group our data by categories. So for example, in our Titanic data frame we have the categories P-class and sex. So we split our data into groups and then we compare these groups, for example, by the age or by the fare. And we can draw conclusions like that the first class male passengers were older than the third class female passengers and so on. So we have still imported here pandas and the Seaborn and Matplotlib, and we still have imported our Titanic data frame. And for all of our plots we set here the figure size to 12.8 and we increase the font scale to 1.5. And our very first plot should be a categorical scatter plot, which is a strip plot. So we call here sns.stripplot and let's have a look here. So the strip plot actually draws a scatter plot where one variable is categorical. And also here we have the parameter data where we have to pass our data frame, here Titanic. And now let's assume that we want to have on the x-axis our categorical variable, so here sex. And on the y-axis we want to have the age. So let's simply run the cell here. So we split here up our data into male and female. And here for each single male passenger we have a dot corresponding to the age, and the same we have for all females. And you can see here that many points are overlapping. We have here the parameter jitter, and by default it's set to false, but we can also set this to true. And by doing so we make here the plot or the points non-overlapping. So now we can better see that the majority of male passengers are here around 20 to 35. And we have some pretty younger male passengers and also some quite old passengers here. And the same we have here for the female passengers. And also the strip plot provides for the option to further split here our two categories into more categories. So instead of having here only male and female, we could also have here male first class, male second class, male third class, and the same for the females. And again here we have the parameter hue, and by default it's set to none, but here we can pass also a categorical variable or a categorical column. And for example here we can pass the P-class column. So let's run here the cell. And we can see here that for each point or for each dot we have the additional information about the P-class. So most of the very old male passengers are actually blue, so this is the first class for example. But it's actually pretty hard to differentiate between the colors and between the classes, and therefore we have here the additional parameter dodge. And by default it's set to false, but we can set it to true. And by doing so we're actually separating here the points or the dots for the P classes. So now here we have one line with first class passenger dots or scatters. Then we have here one line with the second class males and so on. And actually at a very first glance we can now see here that for male as well for females it looks like that first class passengers are older than the second class passengers and that are older than the third class passengers. So you can see here that we have here a kind of decreasing trend. And we not only can split our data by the sex and the P-class column. So for example, instead of having here the P-class column, we can also pass here the survived information to the hue parameter. And now we have here in blue all passengers that did not survive, and in orange all passengers that did survive. Alright, now let's go on. And there's another categorically scatter plot called the swarm plot. So let's have a look here. And the swarm plot actually draws a categorical scatter plot with non-overlapping points. So let's have a look. And the swarm plot is pretty much the same as here the strip plot, with having jitter equals true. So let's have again here the P class to compare it. So these two plots are quite similar, but still here with a swarm plot we can even better see the distribution here. So for example here we have third class male passengers that are here all at the same age, and the swarm plot actually locates all dots side by side. So here we can even better see the distribution or the frequency distribution of the age for the 6 groups here. So the most frequent age for third class male passengers are here, and for example for first class male passengers we can see that there is actually no single concentration here. So we have quite a stable distribution across all ages here. And there's another plot where we can even better see the distribution, and this is the violin plot. And again here we have on the x-axis the sex, and on the y-axis the age. And additionally we split the male and the female group into the 3 passenger classes. So let's have a look here. And instead of having here a scatter plot, we have here actually a line or a curve where we can see actually the frequency distribution. So let's have a look here. And the line or the curve that you can see here is actually called a kernel density estimate. So this is kind of a smoothened histogram where we can see actually the frequency distribution. So here, for example, for first class male passengers, the highest frequencies here are around 40. And for second class passengers, it's around 30. And for third class passengers, it's around 20. And we can also see here that here we have a warning message. So here a future warning message. And this has something to do with the interaction between Seaborn and the stats library. So at this point here we can ignore it. And actually we can also combine the plots. So here we have a violin plot and here we have a swarm plot. And we can actually combine both plots into one plot. So we enable here the swarm plot. And in the swarm plot we have actually here the same parameters. So we have on the x-axis the sex column, on the y-axis the age. Then we additionally split here up into the passenger classes. And in addition we want to have a black color for all scatters or for all dots. So let's have a look here. So here we have now a combination of the violin plot and the swarm plot. So we can even better see now that the highest frequencies here, for example for third class male passengers, are here around 20. And for the violin plot there's actually another option here. So we can see here that on the x-axis we have 2 categories, and for both categories we have 3 plots. But actually if we swap the levels here, so if we have here on the x-axis the 3 classes, and for each class we have 2 plots, so for female and male, then we can actually merge the 2 plots. So here again we are creating a violin plot, and then we exchange P class and sex. So we pass P class to the X parameter and sex to the hue parameter. So let's have a look here. So here we can see on the x-axis the 3 categories, and for each category we have 2 violin plots, so for male and female. And if we have 2 plots for each category, we can also merge them. So we can have here 1 violin plot, and on the left hand side we have actually the distribution for the male passengers, and on the right hand side for the female passengers. And therefore we have to pass here true to the split parameter. So by default it's set to false, but we can set it to true. And let's see what happens. So now here we have only 3 violins. So one for the first class, one for the second, and one for the third class. So on the left-hand side, we have the distribution of the ages for male, and on the right-hand side for female passengers. And so we can even better compare male versus female. Alright. And there's an additional Seaborn plot called bar plot. And again, we pass here our Titanic data frame to the parameter data. Then on the x-axis, we want to have the p-class, on the y-axis, the age. And we pass sex to the hue parameter. So let's have a look here. So here on the x-axis, we have our 3 p-classes. And for each p-class, we have female and male. So female is here orange and male is blue. And here on the y-axis, we have the age, and by default, the bar plot actually calculates the mean age for all 6 groups. So here we have 6 groups, and the height of the bars here actually the mean age. So here for first class male passengers, we have a mean age of over 40. Then, for example, for females here in the first class, we have about 34, 35. And these are so-called point estimates because we simply calculate here the mean over all passengers in the respective group. And in addition, we can see here the black line, which gives us kind of a confidence interval. So instead of having only one point estimate and saying that the average age of first class male passengers is 42, the confidence interval says that, for example, in 95% of all cases, the mean age of first class passengers should be between these 2 points here. So this is a more statistical approach, and with this we can answer the question whether it is statistically significant that here the male passengers are older than the female passengers. So let's have a look here inside the brackets. And we can see here that here we have a confidence interval of 95, and we have 1000 simulations. So Seaborn simulates here the booking for the Titanic 1000 times and then creates here a confidence interval where we can find, for example, the mean age of all first class male passengers in 95% of all cases. So this is here the interpretation, and as we can see here that there's hardly any overlapping. So here we could conclude that it is statistically significant that first-class male passengers were older than first-class female passengers. And for example, if we have a look here at the second class, so here we have an overlapping of the confidence intervals. And here it's more hard to say that the difference in the point estimate here, so here the males are a bit older than the females, that this is really statistically significant. And instead of having here a bar plot, we can also have the same as a point plot. So there's the additional Seaborn plot point plot. And also here we have the same parameters. And actually we have here the same plot, but instead of having here bars for each group, we have here, for example, so we have here one line for the male passengers, and we can see here the confidence interval for the mean age of first class male passengers, and this is here the point estimate. So the mean age of all first class male passengers was this value here, but if we would repeat the Titanic booking 1000 times, then the mean age is in 95% of all cases in this confidence interval. And we can see here that there's no overlapping with the female confidence interval. And therefore we could conclude here that the males are older than the females with statistical significance. And the same we could conclude here for the third class, but we couldn't conclude this for the second class. Alright, this was the video on categorical plots, and I hope to see you also in the next video. Bye! In this video we learn how to create joint plots and regression plots. And with these plots we can graphically analyze whether there's a positive or negative functional relationship between features. So for example, in our Titanic dataset there are the features age and fare, and we could try to answer the question whether, for example, older passengers pay more than younger passengers for their tickets. And in this video we will also further graphically analyze whether the age or the fare of the passenger had influence on the chance to survive the disaster. So first of all, let's import pandas, seaborn, and matplotlib. And again, we are working with our Titanic dataset. And actually in our Titanic dataset, we have two numerical columns, two continuous numerical columns, age and fair. And in the first step, we can create a joint plot, which is actually a scatter plot, where we have on the x-axis the age and on the y-axis the fair. And as a kind of the plot, we can pass here scatter plot. So here we want to have a scatter plot. And here we can see on the x-axis the age and on the y-axis the fair. And each single dot here, or each single point, is a passenger. And here at the top and on the right hand side, we can also see the frequency distribution. So this is the frequency distribution or histogram for the fair. And this is the histogram for the age. So we can see that the majority of ages are here around between 20 and 40. And for the fair here around between 0 and 50. And also here we have a future warning, which is caused by an interaction between the SciPy package and the seaborn package, so we can ignore this here. And actually with the parameter height, we can determine here the size and the height of the graph. And we can also change here the kind of the plot. So instead of having a scatter plot, we can have different plots. So let's check this here. And here we have the option to pass scatter, regression, residual, KDE, or hex. So let's pass here hex. And hex stands for a hex bin plot. And here we can see that our plot, or here the area, is divided into equal sized hexagons. And the darker the color of the respective hexagon, the more data points we have here. So here we can see the majority of data points we have here at quite low fair prices and at ages between 20 and 38 or something. And we can also pass here KDE. And KDE stands for kernel density estimator. So here instead of having a histogram, we have a kernel density estimator, so kind of a line that approximates the histogram. And here in our graph, we can see actually some areas. And the darker the areas, the more data points we have here. So here we can identify where the majority of data points are located. All right, now let's go back to the scatter plot. So here we can see the scatter plot between age and fair. And the next question would be whether there is a significant relationship between age and fair. So for example, whether older passengers paid more than younger passengers. And we can answer this question by having a regression plot. And therefore we can here also pass a reg. And here we can see a regression line through the data points. And the regression line seems to be upward sloping. So here we have a positive relationship or a correlation between the age feature and the fare feature. So the older the passenger, the higher the ticket price. And you can also see here the shaded area around the regression line. And this marks actually the 95% confidence interval for the regression line. So the regression line itself is actually a point estimate. And let's assume that we statistically simulate the booking for the Titanic 1000 times. Then in 95% of all cases, the regression line between age and fare is in this area here. So it seems like that the positive slope or positive relationship is statistically significant here. And Seaborn actually provides some alternatives to create a regression plot with some more functionality. And for example, we can do this with a LM plot. So again, here we pass our Titanic data frame to the parameter data. Then we want to have on the x-axis age, on the y-axis fare. And with the parameters aspect and height, we can determine actually the size of the plot or the subplots. So we will see this in a minute, and let's run here. So here essentially we have actually the same regression plot with the same regression line and the confidence interval. So let's have a look here. So again here we have parameters like Ci, which stands for the confidence interval. So here in this confidence interval, here we have 95% confidence, and under the hood Seaborn actually simulates the booking of the Titanic 1000 times. And by doing so, it creates here a confidence interval for the regression line. So this is the same as above. But actually here the LM plot provides some additional functionality. And also here we have the parameter hue. And we can split up our data frame, for example, by the sex column. So here we can see that we have categorized all single points or dots as being either male or female. And here we have male with blue color. And for the male dots or points, we have here one regression line, and also for the females we have one regression line. And it seems like that for males and females, the positive relationship is here statistically significant. So we have here an upward sloping regression line. And instead of having here both regression lines in one graph, we can also create subplots, and we can do this. And instead of passing here the sex column to the parameter hue, we can pass it to the parameter columns, col. And by doing so, we're creating here two subplots and actually two columns. So here we have the regression plot for the male passengers and here for the female passengers. And both seems to be actually here upward sloping. And theoretically, we can also create subplots in rows by passing here sex to the rows parameter. So now we have here two rows. We have the regression for the male passengers and for the female passengers. But let's stick here to columns. And here with the parameters aspect and height, we can actually customize the size of the subplots here. So here we might conclude that there is a positive relationship between age and fare, not only for the male passengers, but also for the female passengers. And now we want to analyze the factors that actually influence the chance to survive. And again, we are creating here an LM plot. Then on the x-axis, our first factor is the age. And then on the y-axis, we have our survived column. So for the survived column, we know that we only have the values 0 and 1. And let's run here the cell. So here on the x-axis, we can see the age, and on the y-axis, we have either zeros or ones. And here we have a regression line. But here we have a so-called logistic regression, because our dependent variable here, so the survived variable, is actually a categorical feature where we either have the values 0 and 1. And therefore we have to set here the logistic parameter to true, because here we want to perform a logistic regression. So now we can see here our logistic regression line, and we can see that it's downward sloping, and also here the confidence interval suggests that this might be statistically significant. So the older the passenger, the lower is the chance to survive, and vice versa. So the younger the passenger, the higher the survival rate or the chance to survive. And this is actually in line with women and children first. So children had a better chance to survive than older passengers. And also here we can make a categorical split, so we can split our data frame into groups. And therefore we can pass here, for example, to the col parameter a categorical variable, so for example sex. So here we have the logistic regression between age and survived for male passengers and female passengers. And it looks like that here we have a difference. So for male passengers, it seems like the younger the passenger, the higher the chance to survive. And for female passengers, the relationship is actually the other way around. So that could mean that for male passengers, it was even more important to be a child. Alright, and actually we can do the same analysis also here, split it by the P class. So we have still here on the x-axis the age and on the y-axis the survived column. And then we split our data frame by the P class column. And again here, this is a logistic regression, as we have here on the y-axis the survived feature with categorical data 0 or 1. So we have to pass here true to the logistic parameter. So true with capital T, of course. And here we can see the logistic regression for the 3 passenger classes between age and survived. And it seems that for all 3 passenger classes, the relationship holds true that the older the passenger, the lower the chance to survive the disaster. Alright, this was the video on regression lines. And this is pretty helpful to visualize relationships between features. So now we understand better the factors that influenced actually the chance to survive the Titanic disaster. And with this we are finished here, and I hope to see you also in the next video. Bye! In this video we learn how to create matrix plots and in particular heat maps to visualize cross-tabular data. So we will see in a minute what I mean with this, and first of all we import pandas and Seaborn and Matplotlib. And again, we are working with the Titanic dataset. And we've already learned that we can split our data into different groups. And we can do this by categories. So for example, we have the sex column and the P-class column. And in total, we can create here 6 different groups. And then we can determine the size of each group. So we can determine how many first-class male passengers we had on board of the Titanic. And we can do this, for example, with the direct pandas method crosstab. So here we are passing the 2 categories sex and P-class, and by doing so we are getting here cross-tabular data. So here on the left-hand side we have the categories female and male, and as columns we have the categories first, second and third class. And for each combination of those 2 categories we have here actually the amount of passengers that belong to this group. So for example, the largest group by far is in the group male passengers in the third class. And this is pretty much the structure that we need for a matrix plot or heat map plot. So we can actually visualize and compare the size of the 6 groups with a heat map. And first of all, we determine the figure size of 12.8, and also we want to have a larger font scale here. And then we are using here sns.heatmap. And here we pass our crosstab that we created here. So let's run here the cell. So here we have on the x-axis the P-class and on the y-axis the sex. And actually the color here indicates the size of each group. So here we can see on the right hand side the color bar, and dark color means actually around 100 passengers in this group, and the bright color means 300 plus. And we can also include here the exact size of each group by passing here true to the anode parameter. So by doing so we are getting here the numbers. So this is here the largest group, third class male. And here we have 347 passengers, and here we have a bright color. And there's another parameter called CMap, and here we can define the color map. And actually for a heat map, the color map reds is quite appropriate here. So let's do this. So we have here reds with a capital R. So here we have red colors, and we have dark red for groups where we have 300 plus passengers, and we have bright red for groups where we have around 70 or 100 passengers. And actually we can see here that the scale is not really optimal or perfect here, because here we have actually one outlier. So the group male third class is by far the largest group, and the other 5 groups are pretty much equal here, so between 76 and 144. And therefore we can cap here our color map, for example, to 150. So all groups where we have more than 150 passengers are very dark red here. And here we can see that we can better differentiate the other 5 groups. So here we have a very bright color with 76 passengers. Then we have a darker color with 94 and so on. So here we have a heat map with the 6 groups, and the color is determined by the size of the groups. But of course the color could be also determined by the survival rate. And again we are using here the crosstab method. And we are splitting our data frame by the sex column and the p-class column. And then we have a look into the survived column and calculate the mean. So this is actually the survival rate for all 6 groups. So let's calculate this here. So for example, the survival rate for third class male passengers is only 13%. And the survival rate for first class female passengers is 96%. And again, we can pass here the cross-tabular data to the seaborne heat map, and we set the anode parameter to true, and we want to have reds. So let's have a look here. So here we have our 6 groups, and we can see in dark red color the groups with a high survival rate of around 90%, and groups with a low survival rate are marked with bright red. So here we can see the groups male second class and male third class. Here we have only 14 and 16% survival rate, and here we have a quite bright color. Alright, let's have another example, and we can also create a correlation matrix of all numerical features in our Titanic data frame. So here we have the correlation matrix, and here we have the numerical columns. So for the correlation we have values between -1 and 1, and -1 means perfectly negative correlation, and +1 means perfectly positive correlation, and 0 means no correlation. And here we can see that we have a lot of numbers here, and it's at a first glance quite hard to analyze here the correlation matrix. And in particular in these cases, it makes sense to visualize here the correlation matrix with a heat map. So we pass here titanic.core to the heat map. Then again we set anode to true, and the color map should be reds again. And here we can see a strong positive correlation in dark red and negative correlation in bright color. So of course in the diagonal we can see perfect positive correlations between the features itself, so this is no surprise. And we can also have a look here at the survived feature. So we have here a strong negative correlation to the passenger class. That means first class passengers had a higher chance to survive than third class passengers. Then here we can see small negative correlations with the age and SIP-SP features. Then quite weak positive correlation with the Parch feature, and a quite significant correlation with the fare feature. So the higher the ticket price, the better the chance to survive the disaster. And we can see, for example, the brightest combination is here between fare and P-class. So here we have the most negative correlation, and it's no surprise that between fare and P-class there's a strong negative correlation. So passengers in the first class paid more for their tickets than passengers in the third class. And here we can see quite a strong positive correlation between Parch and SIP-SP. So when passengers traveled with their husband or wife, then it was quite likely that also children were also on board. And as a summary, we can see here that we get at a very first glance an intuition on the correlations without having here a closer look at numbers. So we can see this here graphically. And this definitely helps if we have here even more rows and columns. So for the human eye, some colors are more intuitive than blank numbers here. Alright, and with this we are finished here with this video, and I hope to see you also in the next one. Bye! In this video we learn how to remove complete columns from a data frame, and first of all we import pandas and we import our Summer Olympic Games medal data frame and have a look at the first 5 rows. And here we can see that we have the columns sport, discipline and event. And let's assume we only want to keep the column event because the information in the sport column and discipline column are a bit redundant actually. So first of all we try to remove the sport column, and therefore we can use the drop method. And in the drop method we can pass the label of the column we want to remove to the parameter columns. And let's see what we get here. We get here a data frame without the sports column. Alright, so let's check again our data frame, and here we can see that the sport column is still in our data frame. So also the drop method has the in-place parameter, which is by default set to false. And if you want to change our data frame, we have to set the in-place parameter to true. But before we set, we want to drop the sports column and the discipline column, and we can of course also remove multiple columns with the drop method. And we can do this by passing a list of column labels to the parameter columns. So let's check here. So here we can see that we removed the column sport and the column discipline, and now if we want to make this in place and change our original data frame, we have to set the in place parameter to true. And let's check again our data frame. And now we can see that now in our data frame there is no sport and no discipline column. And now let's assume we want to drop also the event column. Then we again use the drop method, but instead of passing the event column to the parameter column, we can also pass event to the parameter label. So let's check here. So before we passed our columns that we wanted to drop to the parameter columns, but we can also pass this to labels and define the axis from which we want to drop our label, and in this case it's either we can use 1 for columns. So let's check here. Now we have removed the event, or we can use, in quotation marks, columns. An N is missing here. So that's actually the second alternative. So either we pass our column labels to the parameter columns, or we pass it to the parameter labels and define the axis as columns or as 1. And again we have to set the in-place parameter to true. And let's check again our data frame. So now we have removed the sports column, the discipline column and the event column. And there's another way to remove a column with the keyword delete and then selecting the event column from our summer data frame, but I wouldn't recommend this one. So I would definitely go for the drop method here and use the drop method to drop a column. So now let's import our summers data set again. So this is the original one. And before we dropped the columns sport, discipline and event. But instead of dropping the 3 columns, we could also explicitly select the other columns. So we could select year, city, athlete, country, gender and medal. And we can do this with the log operator. So we select all rows. And then we pass a list of column labels that we want to keep in our summer data frame. So year, city, athlete, country, gender and medal. And we override our summers data frame. So our new data frame, summer data frame, contains the columns year, city, athlete, country, gender, medal. And it does not contain the columns sport, discipline and event. Alright, so this also works. And it depends actually on the case whether you drop the columns that you don't need or you select the columns that you need. So let's assume we have a data frame with 100 columns and you want to drop one column, then you should definitely use the drop method. But if you have a data frame with 100 columns and you want to keep only 2 columns, then it makes more sense to explicitly select the 2 columns. Alright, so now we are finished with this session, and I hope to see you in the next session. Bye. Welcome to the Pandas group by section. So group by operations are one of the most powerful data analysis tools in Pandas, and the functionality and flexibility is almost unlimited. And that's why group by is actually my favorite Pandas tool. So it's simply fun to perform group by operations. Alright, so now I want to give you a very first intuition what we can do with the group by method. And let's assume we have here our data frame with male passengers and female passengers. And what we can simply do, we can calculate the mean or the average age over all passengers with the mean method. But what if we are interested in the group-specific mean ages? So for example, the mean age over all female passengers and the mean age of all male passengers. And group by actually provides us the easiest and most comfortable way to do this and to perform group-specific operations. So actually within one line of code we can transform here our data frame into a summary data frame where we have the mean age for all female passengers and the mean age for all male passengers. And we can simply do this with the group by method, where we have to pass the key by which we want to split our data frame here by the sex key. So we have male and female in our sex column, and then we apply the mean method. And by doing so within one line of code, we are getting here our new data frame. So no worry, I will explain this in more detail in the next videos, and we will also practice this in more detail. So this was just a little outlook. And actually this is just the top of the iceberg of what we can do with group by. And as I said, the functionality and complexity is unlimited here. So we will see this in the next videos where we will dive deep into this topic. So I hope to see you there. Bye. Welcome to our first coding video on group by operations. In this and the next video we want to figure out and really understand what group by does in the background. And we also want to understand what a group by object is. So first of all, we will have a deeper look into the split part of split, apply and combine. But first of all, let's import pandas. And we are working with the Titanic dataset. And let's have a look here at the first 5 rows and the last 5 rows. And also at some meta information with the info method. And for the time being, we want to work with a toy example. So we slice our Titanic data frame only for the first 10 rows and for the columns sex and age. And we are saving here the slice in the variable Titanic slice. So let's do this. And let's have a look here at our slice. So here we have the first 10 passengers and the columns sex and age. And now we want to use the group by method on our slice here. And what we actually want to do, we want to split here our data frame by the sex column. So the key is the sex column. And by doing so, we expect that we split here our data frame, and then we get all rows or all passengers who are female, and we get all rows and passengers who are male. So let's also press here Shift Tab within the brackets. And the most important parameter is here the by parameter, where we have to define the keys by which we want to slice our data frame. And here we have to pass one or several columns, and in this case here we are passing the sex column. So let's do this here. And here we can see that we get something like a group by object. So let's store here the group by object in the variable GBO, group by object. And let's also check the data type of GBO. So here it's a data frame group by object. And same as with all data types or classes in Python, Also, the group by object has specific attributes and methods, and one attribute is the groups attribute. So let's try this out here. And here we can see that we have two groups in our group by object. So we have the group female with actually all rows where we have a female. So we have in the rows 1, 2, 3, 8, 9 females. So let's check this out here in our data frame. 1, 2, 3, 8, and 9. So here we have actually the index labels where we have females in our data frame. And the second group is the male group. And also here we have the index labels for the rows where we have males. So we have here 0, 4, 5, 6, 7, 0, 4, 5, 6, 7. And now we could also transform here our group by object into a list by using here the list function, and we save our list in the variable L. And let's have a look here at L. So it's actually at a first glance hard to see what we have here, but apparently our list has two elements. So the first element starts here with the bracket and ends here, and the second element starts and ends here. So let's check first of all the length of our list, so the amount of elements. So we have two elements. And now let's select the first element of our list. So here we have the first element. And here it looks like a tuple. So we have here two brackets. And apparently our tuple consists of two elements. So we have here the string female. And it seems like that we have here a data frame with all rows where we have a female. And we can also check here the data type. So it should be a tuple. And now we can also select the first element in our tuple, so it should be here female. So let's try this out. And it's a female. And this is apparently a string object. And let's also select the second element of our tuple here. So this looks like a data frame. And indeed here we have a data frame with all rows where we have females. And still here on the left side, the index labels are the same as here in our original data frame. So here we have for the females the index labels 1, 2, 3, 8, and 9. And also here we have 1, 2, 3, 8, and 9. And we can also check here the data types. So this should be a pandas data frame. Exactly. And for the sake of completeness, we can also check the second element in our tuple here. So this time we have here a tuple with the first element the string male, and the second element our data frame with rows where we have male passengers. Alright. So what the group by method actually did, it splitted our original data frame into two data frames. And the first data frame contains all rows with female passengers, and the second data frame contains all rows with male passengers. And alternatively, we could also slice our data frame with the log operator and slice for all rows where the sex column is female. So we can also do this in this way here. And here we can see that we get here the same slice. So here we have all rows with females, and here we have all rows with females. And we can also save here the slice with all females in the variable Titanic slice female. And we can do the same with male. And then we can check with the equals method whether the data frame with all female passengers, which we created here with the log operator, is actually the same as our sliced group by object here. So here we get a true. So this confirms that the group by method splits our data frame by the key sex and creates two data frames, one female data frame and one male data frame. And we can also iterate over our group by object with a for loop. And for each element in our group by object we want to print the data frame, so we can also do this here. And we get here our female data frame and our male data frame. Alright, so now let's go also back to our slides here. And this is actually exactly what we did right now. So we created here a group by object, and this is actually the split part. So we had here our original data frame, or actually our slice of our data frame with 9 passengers and the sex and age column. And then we applied here the group by method by the key sex. And by doing so, we splitted our data frame into 2 data frames, where in the first data frame we have all female rows here. And in the second data frame we have here all rows where we have a male passenger. So and this is now our group by object. So we have 2 groups or 2 data frames split by the key sex. Alright, so we are finished now with this video, and in the next video we can see that we can also split a data frame by more than 1 key, so by many keys, by 2, 3 or 4 keys. So hope to see you there. Bye! In this video we will split our data frame by more than 1 key. So in principle we can split our data frames by 1, 2, 3 or whatever number of keys, so this is no problem. And first of all we import pandas as always, and then now we are working with the Summer Olympics data frame, and we will have a look at the first 5 rows here and also add some meta information. And this time we are working with the whole data frame, so no toy examples this time. And let's have a look here at the country column. So now let's first have a look how many different or unique countries we have in our data frame. So up to now athletes from 147 countries have already won medals in Summer Olympic Games. And in the last video, where we have split our Titanic data frame into a male data frame and a female data frame, we have seen that we can also do this with the log operator and create a group by group. So this is quite easy if we only have 2 groups, so males and females. But if we have here 147 groups, like in this case, then doing this manually with the log operator is getting quite messy. And with the group by method, we can do this actually in 1 line. So let's do this. We are splitting our Summer Olympics data frame by the key country, and we save our group by object in the variable split1. And let's transform our group by object into a list and store it in the variable L. So let's have a look here at our list L. First of all, let's check here the length. So we have 147 countries and the length of our list is 147. And for each country actually we have here in our list a tuple consisting of the country code here starting with Afghanistan. And then the second element here in the tuple is actually the data frame with all rows where we have athletes from Afghanistan. So in total here we have 2 medals, both medals awarded here in Taekwondo. And here we have the second element of our list. It's the country AHO, so actually I do not know which country it is. And then the third element is here Algeria. So we can also randomly select here a data frame. And we slice for the tuple at index position 100 and we slice for the data frame. So let's see what we get here. And we get here a data frame with all medals won by athletes from the Philippines. And now instead of splitting our data frame only by the country, we want to split our data frame by country and gender. So here with our group by method, we have the parameter by, and before we just passed here 1 column name, but we can pass here a list of multiple column names. So here we are passing the column name country and gender, and by doing so we can split our data frame by country and gender. So let's do this, and we save our group by object in the variable split2. So let's run here the cell. And then we are transforming our group by object into a list and save the list in the variable L2, and let's print here L2. And first of all we can see here the first element. We have here all men from Afghanistan that already won a medal in Summer Olympic Games. And we can also check here the length of our list too. So intuitively we could say, okay, we have 147 countries and we have male and female, so the number of possible combinations should be 2 times 147. It's 294. So potentially we have 294 groups, but I do think, at least for the small countries, that we have countries where only male athletes or female athletes have already won medals. So I do not expect to have here in our L2 list a length of 294. So let's check this out. And we have only 236 groups. And let's randomly select the group at index position 104. And here we can see that we have the group with female athletes from Ireland. So actually we have here 1, 2, 3, 4, 5, 6 medals that has been awarded to female athletes from Ireland. And apparently here we have a tuple, so we can also check here for the first element in our tuple. And here it's not a string, but also a tuple consisting of 2 strings. So here are our 2 groups, so we have Ireland and women. And we can also slice here our tuple for the second element. So the second element here is the data frame. And here we have the data frame with all rows or all medals where we have female athletes from Ireland. And still here on the left side, we have here the index labels from our original data frame. Alright, so now in this video we splitted our Summer Olympics data frame not only by 1 key but by 2 keys. And we could also do the same for more keys. So for example, we could say that we want to split our data frame by country, athlete, and let's say the year or the edition of the Olympic Games. Then here Michelle Marie Smith would actually form one group, so female athletes from Ireland who won in the edition 1996 a medal. And a second group would be female athletes also from Ireland that won in the year or in the edition 2000 a medal. So here in this data frame we only would have Sonia O'Sullivan. Alright, we are finished now with this video, and I do think we have now a good impression how group by splits our original data frame in many data frames or in many groups. And in the next video we will learn how split apply combine works. So this is the real power of group by, and I hope to see you in the next video. Bye! In this video we learn how to perform split apply combine operations on a data frame with the group by method. So in the last videos we already learned how to split a data frame into groups. And now we apply a function to our group by object, and by doing so we are creating a new combined data frame. This sounds complicated, but you will see that it's really easy and straightforward. So let's start coding, and we import pandas. And we are working with the Titanic dataset. And also this time we are working with our toy example, so we are slicing our Titanic data frame, and we only use in the first 10 rows and the columns sex and age. So here's our toy example. And we have already learned that by applying the group by method and, for example, using the key sex, we are splitting our data frame here into, in this example, 2 data frames. So we have one data frame with all rows where the passenger is female, and we have another data frame with rows where the passenger is male. And we can transform our group by object into a list, and then we can slice our list. And here our first data frame and our group by object is the female data frame, and the second data frame is the male data frame. And now let's assume that we want to calculate the average age of the females and the average age of the male passengers. And therefore we are using here the group by method on our slice. And we group by the sex column, so male and female. And by doing so we are creating a group by object. And then we have to apply a function on our group by object. And the function will be applied on both data frames in our group by object. And after we have applied both functions here, both data frames will be combined to one new data frame. So this sounds complicated, but let's just do it. And we are using the function mean. And let's run the cell and let's see what we get here. So we are getting here a brand new data frame where we have as index here our sex column, so female and male. And we have here a single column, age. And here we have the mean or the average age for all females and for all males. So actually here 28 is the mean or the average of all of the females here in our split. And also here for our males, so 28.25 is the mean or the average of all male passengers here. And by default, pandas is just ignoring here the missing value or any n value. And this is actually all. So with the group by method, we split our original data frame in a female and a male data frame. And then for the female and the male data frame, we calculated the average age, and then we combined the average age of females and the average age of males into one final data frame here. And let's also have a look at our slides here. So here we had our original data frame. Then we used here the group by method and used as a key the sex column. And by doing so, we created a group by object. So we split our data frame into all rows where we have females and all rows where we have males. And then we applied the function mean. And by doing so, pandas actually calculated the mean age of all females and the mean age of all males. And then both mean values were combined into a brand new data frame. So by applying the group by method, we splitted our data frame, and by using here the mean function, we applied a function on both data frames, and at the same time we combined our groups into a new data frame. Alright, so now let's go back coding. And in theory, as a function here, we can apply any function. And the most frequently used functions are actually aggregations, so taking the mean or the sum or the min or the max of the groups. So as a next step, we could also use here the sum function on our group by object. So let's see what we get here. And we are using here the group by and sum function on our whole data frame. So we are having all 891 rows and all columns, and let's see what we get here. So again, we splitted our data frame here by the sex column, so we have female and male. And then we have for each column here actually the sum. So we have here the survived column, and in total 233 female passengers survived and only 109 male passengers survived. And we have also the sum of the p-class, so in this case it doesn't make really sense. And we have also the sum of the age, so all females together are 7,286 years old. And we have also the sum of all siblings and spouses. So all female passengers together had 218 siblings and spouses on board. And we have the same here for parents and children. And also we have the sum of the fare. So all females together paid about $14,000 or pound. And all male passengers together paid slightly more than the females. And you can see here that taking the sum does not make sense for all columns. So let's assume we are only interested in the survived column, and we can do so here by here just only choosing the survived column, so dot survived. So this is actually method chaining. So first of all, we are using the group by method on our Titanic data frame. And we group our Titanic data frame by the sex column. Then we are only interested in the survived column. And for each group, so female and male, we want to know the amount of female and male who survived. Alright, so let's do this. And we can see here that we only get aggregations for the survived columns. So we have 233 females who survived and only 109 men. Alright, and of course we can select more than one column. So here we only selected the survived column, but we can also select the fare and the age column. So we have to pass here within our spare brackets a list with the fare and the age column. And we split our data frame by the sex column, and then we want to know the maximum. So we want to know the maximum fare paid by a female and by a male, and we want to know the maximum age of females and males. So let's do this here. So the highest fare paid by a female is 512, and also the highest fare paid by a male is also 512. And the oldest female on board was 63 years old, and the oldest male on board was 80 years old. Alright, so now let's again split our whole Titanic data frame by the sex column. And we want to calculate the mean on all columns. So let's do this, and we assign the variable new data frame. So let's have a look at new data frame. So here we have the mean for all columns by female and male. So on average 74% of all females survived the Titanic disaster and only about 19% of all males. And the average passenger class is a little bit higher for the males. And also the male passengers are a bit older on average than the female passengers. And on average the female passengers paid more for their tickets than the male passengers. So on average the females paid $44 or pound and the males paid $25 or pound. Alright, and now we can also visualize here our new data frame, and we import matplotlib and we use the seaborn style. And we want to have a bar plot for each column where we can see the difference between female and male. So let's do this and let's have a look here. So here we use the subplots true. So for each column here we have a subplot, and here the first subplot is for survive. And we can see here on the left side are the females and on the right side are the males. And we can see that the survival rate is tremendously higher for females. And here we have the average of the passenger class, and here the average of the age. So here we can see that on average the male passengers were a bit older than the female passengers. And here we have the information about the fare. So on average the female passengers paid significantly more than the male passengers. Alright, so now we are finished with our video, and in the next video we will apply our new split apply combine skills to some more cases, so hope to see you there. Bye! In this video we will learn some very helpful datetime index methods and attributes, and with these methods and attributes we can, for example, create additional features for our data frame containing some kind of customized representation of date or time. So let's first of all import pandas, and we import our stocks CSV, and we set the date column as being the datetime index. So let's have a look here. And then we only select here the opening prices for our 6 stocks, and we are creating here a copy and store the new data frame in the variable close. So let's have a look here. So this is our closed data frame with daily closing prices for our 6 stocks. And let's also call here the info method. And we can see here that we have a datetime index with actually daily timestamps. And with the index attribute we can also have a closer look at our datetime index. So here we have the datetime index with the timestamps. So in total we have 2290 daily timestamps. And here we can see, for example, for one timestamp, so here we have the 4th of January 2010. And it might be quite helpful to get here additional information or different representation of the date. So for example, it might be useful to have the day of the week, so for example Tuesday or Wednesday, or the quarter of the year. So here in this example it's the first quarter. And we can do this with quite helpful attributes and methods on the index. So first of all we have here the day attribute. And here we get actually the day of the month. So for example here in our first timestamp we have the 31st of December, and here we get the 31st. So the data type is here an integer. And consequently we get here for the other timestamps, for example here 4, then we get 5, and so on. And we can also get an integer representation of the month, and we can do this with the month attribute. So here we have the data type integer, And we get 12 here for the timestamp in December, and 1 for the timestamps in January, and so on. Next, we can also get the year with the year attribute. So here again we have integer data types, 2009, 2010, and so on. And for each row or for each timestamp in our data frame, we can also get the day of the week or the day name with the method day name. So here we have Thursday, Monday, Tuesday, and so on. And we can actually do the very same with the attribute week name or weekday name, and here we get actually the same weekday names. And also, instead of getting an integer representation of the month, so here 12, 1, 2, 3, you can get the month name. So here with the method month name. And here we get December, January, February, and so on. So next we have the attribute weekday. And instead of getting here the string representation, Thursday, Monday, Tuesday, we get here an integer representation. So 0 stands for Monday, then 1 stands for Tuesday, and so on. And we can also get the quarter with the quarter attribute. And by default, the first quarter is from January to March, the second from April to June, and so on. So here we can see for the timestamp in December we get a 4, and for the timestamps in January a 1 as integer. Then next we have also the attribute days in month. And here we get for each row or for each timestamp the amount of days in the respective month. So here in December we have 31, in January 31, and so on. And next there's also the week attribute. And here we get actually the calendar week. So the very last week in December is the week 53, then the very first week in January is week 1, and so on. And the same we can actually get with the attribute week of year. So this is the same. And there's another attribute called isMonthEnd. And here pandas checks for each row or for each timestamp whether the day is actually the very last day of the month. So here we have for the 31st of December a true, and for the 1st of January or for the 2nd a false. So these were some very helpful attributes and methods on the datetime index, and there are even more methods, so feel free to have a closer look. And now we can also create new columns and new features for our data frame. So for example, we want to have the day name as a new feature, and we can create here a new column called day, and we want to have the quarter as a new column or new feature. So let's do this here, and let's have a look here at our new data frame. So here we have our adjusted closed data frame, where we have here on the right hand side the 2 additional columns, day and quarter. And here for each row or for each timestamp we have here the weekday and the quarter. So creating additional features with different representation of date might be in some cases quite helpful. And with this we are finished now, and I hope to see you also in the next video. Bye! In this video we learn how to fill missing values in time series with backfill, forward fill, and also with interpolation. So NA or missing values are typical problems in time series, because typically we do not have for all timestamps in our index corresponding values in our features. And in particular when we resample, re-index or merge time series, it's very often the case that we create missing values. So for example, we do not have official stock trading prices on bank holidays or on weekends. And therefore it's quite important to handle and fill missing values. So let's start with our closed data frame. So this is still imported. So we have here the daily closing prices for the 6 stocks, and we have also here the additional information on the weekday and on the quarter. And let's also have a look at the last 5 rows. And we can see here on the left hand side in our datetime index that we only have rows or timestamps for business days. So for example, here we have the 31st of December. Then we have here kind of a gap. So the next day is the 4th of January. And this is because, so the 1st of January is a bank holiday. Then the 2nd and the 3rd are Saturday and Sunday, so weekend. And as we imported here our stock data from Yahoo Finance, so by default we only have here timestamps for business days. And now let's assume that here in our data frame we want to have all days, so also the weekends and the bank holidays. And therefore we're creating here a datetime index with the pd.dateRange method. And the start should be the 31st of December to 9. And the end date here should be the very last day of our stock or closed data frame. So it's here the 6th of February to 19. And we want to have daily frequencies. And then we store here the datetime index in the variable all days. So let's do this and let's have a look here. So here we have a datetime index with all days from the 31st of December 2009 till the 6th February 2019. And now here in our closed data frame, instead of having a datetime index that does not contain bank holidays and weekends, we now want to have the datetime index with all days. And we can do this by re-indexing the closed data frame. And we can pass here within the brackets our new datetime index, all days. And then actually we override our data frame close. So let's do this. And let's have a look here at our new data frame with the new datetime index. So in our new datetime index here, we have now the timestamps January the 1st, the 2nd and the 3rd. And consequently we have here everywhere missing values. So again here January the 1st was a bank holiday, then here we had a Saturday and Sunday, and here we have a Saturday and Sunday and so on. And now our task is to actually handle and fill the missing values. And for the columns day and quarter, we can do this by actually reassigning here the weekday name attribute and the attribute quarter and to override the columns. So let's do this here. And let's re-inspect. So here we have now also the weekdays for the new timestamps here and also the quarter. Alright, and now it's time to fill the missing values in the stock price data. And it actually always depends on the specific case what makes most sense. So first of all we use here the fillNA method on our data frame. And let's have a look here inside the brackets. So we've already seen here that we can pass to the values parameter a specific scalar value. So for example, we can say that for all missing values, we want to have the value 0. And in this case, this does not really make sense. And there comes actually the parameter method into play, and by default it's set to none. So, and here we can define the method to use for filling holes in re-indexed series. And by passing ffill, we can propagate the last valid observation forward to a next valid, or we can use backfill to use the next valid observation. So let's first of all pass here bfill for backfill. And if we have a look here at our data frame with the missing values and with the backfill method, we take the next value, which is not a missing value, and backfill the missing values. So for example, here for our Apple stock, we should have here in these 3 days with the backfill method the value 30.57. And here we have 30.57. So we backfilled the missing values. And we can also use the forward fill method. And here we actually use the last valid value. So for example, here the value at the 31st of December, and we forward filled the missing values. So now we should have here the value 30.10. And exactly here we have it. And as I said before, it always depends on the case which method makes most sense. And in the case of stock prices, we should actually always use the forward fill method. So we use here the very last valid traded price. And this is actually the best indication of the price at the weekend. So here in our stock example, we use forward fill, but there might be other cases where backward fill is more appropriate. And once we are happy here with our method, then we can actually override our data frame and save the changes by passing here true to the in-place parameter. And now let's finally re-inspect our data frame. So, and here we have successfully replaced all missing values. All right. So as a summary, in this case, we actually used here the reindex method on our closed data frame. And by doing so, we created here missing values. And then we filled and handled the missing values with the fill_NA method. But we can also do this directly when reindexing here the data frame. So also the reindex method provides here for the same tools to handle missing values. So also here we can see the parameter method, and also here we can define that the resulting missing values should be filled with the backfill or the forward fill method. So we can reindex and fill the missing values here in one step, or we can do this in 2 steps. Alright. So now let's have a look at another example, and therefore we import here our temperature data frame. So here we have hourly temperatures for Los Angeles and New York. And now let's assume that we want to upsample our data. So we want to change the frequency from hourly to 30 minutes. And we can do this with the resample method. And as new frequency, we can pass here 30 minutes. And we want to take here the mean. So let's do this. And by doing so, we are creating here missing values. So we are creating more timestamps than we actually have here. So here we have data for all hourly timestamps, but for the 30-minute timestamps, we do not have any values. So here we have missing values. And also here in this example, we could decide that we want to use the backfill or the forward fill method. However, in this case, with the continuous temperature or weather data, it could also make sense to interpolate here the values. So for all missing values, we use here the interpolated value of the values that we have before and after the missing value. So here, for example, for 30 minutes after midnight, if we use here interpolated values, then I might expect to get here the mean of 11.7 and 10.7, which is actually 11.2. And we can quite simply do this with the method interpolate. So let's do this here. And we can see here that we successfully have filled all missing values with the interpolated values. And actually the interpolate method provides quite a lot of customization. So here we can, for example, define the method, and by default it's linear interpolation, but we can also change this here. And finally, if we want to save our changes, we also have to set the in-place parameter to true. Alright, so with this we are finished now with this video, and I hope to see you also in the next one. Bye! Working and handling time zones is considered one of the most unpleasant parts when working with time series data. If you have time series data with datetime information, first of all, you never know which time zones the datetime information is referring to. And therefore, many users choose to work with the Coordinated Universal Time, or short UTC, which is currently the international standard. And among others, the United Kingdom, Portugal, and Iceland are located in the UTC time zone. So let's have a look at an example, and we import pandas. And then we import historical stock prices for General Electric, GE. And let's have a look here. So here we have on the left hand side a datetime index, and we have actually time increments of 30 minutes. And we have actually open, high, low, close, and volume data. So let's have a more detailed look here. And we will examine the first 30 timestamps. So actually here we are starting at 9:30 till 10 a.m. Then we have here the next period from 10 a.m. to 10:30 and so on. And actually the very last timestamp on a day is actually here from 15:30 till 4 p.m. So these are actually the regular trading hours on New York stock exchanges. So this daytime information is here actually based on New York time, or actually Eastern time. And actually New York time or Eastern time is 4 hours behind UTC. And we can also get some meta information here. So that's a daytime index, and let's have a closer look on the index. And apparently here we cannot see any information on the time zone, and we can explicitly get information on the time zone with the index method tset. And obviously here we have no information on the time zone, so we have actually no time zone addressed here to our data frame or to our datetime index. So to say our data frame and our datetime index is here time zoneless. And that's actually our first step here. We have to localize our datetime index. And we can actually do this with the method tset localize. And by doing so, we actually set or save a time zone on our datetime index. And for example, we can choose here UTC. So we know that here our datetime index is based on Eastern or New York time. But first of all, we can, for example, localize it to UTC. And still we have here the day and the time. And then we have here an additional information plus 0 hours and minutes. And actually, once we have localized our datetime index, then here we can see the difference or the time offset to the UTC time. And if we localize our index to UTC, then of course the time difference or offset is 0. So now let's localize our datetime index to New York time. And we can do this by passing here America, New York. And still, of course, we have here the same datetime information. So the 29th of July, and the first timestamp is here 10 o'clock. But here we have the additional information that we are 4 hours behind the UTC time. So that's New York or Eastern time, and we have 10 a.m. And the corresponding UTC time is actually 2 p.m. or 14 p.m. All right. And actually, to save our time zone information, we have to overwrite here our data frame. So we have to reassign it here to the variable GE. So here we have on the left-hand side the localized datetime index. And in the next video, we will see how to convert a localized datetime index to another time zone. So for example, to LA. So for example, we can get the LA time corresponding to the New York time. So thanks for watching, and I'll see you also in the next video. Bye. In the last video, we have localized our G stock price time series to New York time. So here we can see that New York time is 4 hours behind the UTC time. And we can also check this here with the index attribute tset. So this is New York time. And now let's assume that we want to convert these New York times to LA time, because we are located in LA and frequently trade in the GE stock or whatever. And actually we can convert to other time zones with the method tset convert. And it's actually required that we have localized our time series before. So if we haven't localized it, we cannot convert it. So first of all, we can convert our New York time to UTC by passing here UTC. And here we have the corresponding UTC time, so 10 a.m. New York is 2 p.m. UTC time. And also here we have the difference to UTC time, and of course it's 0. And now let's convert our New York time to Los Angeles time by passing America, Los Angeles. So apparently Los Angeles time is 3 hours behind the New York time and 7 hours behind UTC time. So 10 a.m. New York is actually corresponding to 7 a.m. Los Angeles time. And also here, if you want to save our new time zone and actually change our data frame, we have to assign it to a variable. And for example, we can assign here our GE price data frame with Los Angeles time to the variable GELA. So now we have 2 data frames for our GE data set. So we have it in LA time and also New York time. And now let's assume that we want to concatenate both data frames horizontally. And we can do this with the direct pandas method concat, and we pass GE and the GELA data frame. And the interesting question is now, how will the rows and the timestamps be aligned in the concatenated data frame? And let's simply have a look here. So we save the concatenated data frame in the variable comp. And let's have a look at comp. So that's actually the GE data set coming from the New York data frame. And here we have the Los Angeles data frame. And actually it looks like that the rows match here. So we have the same prices and volume data. And here on the left-hand side, we have actually a datetime index, which is localized to UTC time. So pandas actually recognized that the GE New York data frame was localized in New York time and the Los Angeles data frame in Los Angeles time. And it actually aligns both data frames by simply using here the UTC time. And we can also check here our new index. And here we can actually see that it is UTC time. And then we can actually add 2 new columns to our combined data frame. So 1 column with New York time and 1 column with Los Angeles time. And we actually convert here our datetime index with UTC time to the corresponding time zones. So let's have a look here. And here we have on the right-hand side 2 new columns, New York time and Los Angeles time. And finally, you might ask yourself where to get here the time zones that you have to pass here. And therefore, we have to import the PyTset module. And we can actually get all available time zones with the attribute all time zones. And we can check here the length. So in total, we have 592 time zones. And we can also get the most common time zones with the attribute common time zones. So here we have quite a few time zones. So let's scroll down here. And here we can see US time zones. So US Eastern, US Central, and so on. And finally, we can also see UTC. That were the videos on time zones. Probably not one of the most attractive topics, but pretty important nevertheless. So thanks for watching, and I'll see you also in the next video. Bye. Hi and welcome to this section on object-oriented programming, or short OOP. So OOP is one of the most important and powerful tools, not only in Python, but also in other programming languages. And if you know the very basics of Python coding, like data types, for loops, conditional statements, some operators, and user-defined functions, you shouldn't have any problems to create your own classes. So this is not more complex or more difficult than what you have learned so far. However, in my experience, many students struggle with OOP and find it hard to create their own classes. And the reason probably is that when students start learning OOP, they typically get overwhelmed by theoretical concepts and buzzwords like class, object, instance, methods, attributes, parameters, arguments, so the modularity, abstraction, composition, polymorphism, encapsulation, aggregation, inheritance, and more. And starting with those buzzwords and their definitions is not a good idea and can be daunting and puzzling. So in my view, OOP and creating classes is a very hands-on and practical thing that helps us to solve real-world problems. And also here, learning by doing is the best way to learn and master OOP. So once you have created your first classes, you will also understand concepts like inheritance or polymorphism. Like I said, OOP isn't difficult or complex, and in Python, everything is an object anyway. And you have already used and worked with objects and classes, maybe without even knowing it. So for example, we have strings, and one example is dog. And we could say the following here. So a string is a class or also a data type. So people use that interchangeably. And one example or one instance of the class string is dog. So the number of possible examples or instances is unlimited. And we might think of millions or billions of different examples for string. And we could also say that the string class is like an abstract template that we can use to work with any text data. So not only with the string dog, but with any text data. And we could also say that the class string is like a set of rules that define how we can work with any text data. So not only with one example like dog, but with any text data. Now another class or data type is a list, like 1, 2, 3. So that's one example or one instance of the class list. And finally, we have also worked with pandas data frames. And pandas data frames actually help us to work with tabular data. And one example or one instance could be the Titanic dataset. And also here with pandas data frames, we could rephrase the sentence here. So the pandas data frame class is like an abstract template that we can use to create and work with any tabular data. Now there are many available classes in the Python standard library and also in other libraries like NumPy or Pandas or whatever. And the good thing is that Python also allows us to create our own classes to solve our specific problems and perform our customized tasks and workflows. And with our own classes, we can do this in a very efficient manner. And it allows us to reuse code. And one example in this course is that we will create and define a class to analyze the financial instruments, like for example stocks. And actually object orientation is the natural or human way of thinking. So human thinking typically evolves around real-world objects, like for example a bubble maker that consists of two pieces. So here the blue one and the yellow one. And these are characteristics or attributes of the bubble maker. And we can use the bubble maker to make bubbles. And also the bubbles are objects with certain characteristics like the size or the color. Now, object orientation is the natural human way of thinking, and even small kids and babies learn and grow with object orientation. And also learning OOP in Python is a simple task if it's done in the right way. And typically, it's best to learn and master OOP with simple and intuitive real-world examples. And in this course here, we will start with the final solution. So before we define a class, we simply use the class to understand how and why the class can help us to solve our real-world problems and workflows. And once we understand the functionality of our class, defining the class and creating the class is simple and straightforward. And finally, we will do this step by step. So we add one functionality after another and see the impact of the additional functionality on our workflows. So this is definitely the best way of doing it. And next, let's have a short look at some classes that we are already familiar with. Pandas data frame is an example of a class, and the goal of the class is to handle, manipulate, and analyze tabular data in an efficient and user-friendly manner. And that means that the class should be easy and intuitive to use with concise and short code fragments. And the pandas data frame class is a perfect example for this. So with only few lines of code, we can perform very complex workflows on tabular data using quite complex code fragments in the background with dozens or even hundreds of lines of code. Now, before we can work with pandas, we have to import pandas, and the convention is SPD. So pandas isn't part of the Python standard library. Now, instantiation means creating a concrete or specific object of the class pandas data frame. And here we import the tabular dataset Titanic from the CSV file titanic.csv into pandas. And read CSV is an instantiation method that allows us to create a specific data frame object from a CSV file. And then we save the specific object or instance of the class data frame in the variable df. So this is the instantiation, and let's run the cell here. And we have saved the object or the instance of the class pandas data frame here in df. And that's the Titanic dataset with the Titanic passengers. And with the type function, we can also check the data type or the class of our object here. And it's no surprise, it's an instance of the class pandas data frame. Now, specific objects have attributes or properties or also characteristics. And a pandas data frame has the attribute columns. And here we can get the column headers like survived p-class and sex. And also we can get the shape of the table, so the number of rows and the number of columns with shape. And here we can see that we have here a tuple, and the first element is here actually the number of rows, 891. And then we have the number of columns, 9. And finally, methods allow us to perform operations on the specific object. So with the info method, we can get some more information, so to say meta information on our data frame. And here we can see for each and every column the number of non-missing values or the data types or the memory usage. And another example for a data frames method is sort values. So here we can sort the data frame by a specific column, for instance, age, and we can decide whether we want to have ascending or descending order. So let's simply run the method here or call the method, and here we get our data frame sorted by the age in a descending order from high to low, so starting with the oldest passenger that is 80 years old. And again, sort values is an example for a method. So the method here performs a specific operation on our object. So it sorts our data frame, and methods can include parameters like here by and ascending. And here we have to pass arguments like that you want to sort the data frame by the age. So age is the argument for the parameter by. And we pass false to ascending to have a descending order. And the key message is that the whole functionality work on any tabular dataset. So not only for the specific Titanic dataset, but also for like the Olympic medals dataset or for stock price tabular dataset, and millions or billions of other examples. So the class pandas data frame contains abstract definitions and rules that should work for any tabular dataset. And this is how classes work in general. And in the next lecture, we will have a look at the class financial instrument that help us to analyze financial instruments like stocks. So hope to see you there. Bye. In this and the next lectures, we are going to create our own class financial instrument to analyze financial instruments like stocks, currencies, funds, and more. And like I said in the previous lecture, we don't start with the definition of the class. So we start with the final result and just use the class and observe the functionalities to understand why and how the class can help us to analyze any financial instrument we can think of. So for the class financial instrument, we require some packages and libraries, and we import pandas, numpy, matplotlib, and also yfinance. So we will retrieve data from Yahoo Finance. And then we have here the definition of the class, and let's simply skip this. So we run the cell here, and let's go on. Now, first of all, we have the instantiation, and here we can create one instance of the class financial instrument. So in other words, we can create an object of the data type financial instrument, and we can do this with the financial instrument, and let's have a look inside here. So this is a class for analyzing financial instruments like stocks. And we have here a couple of parameters. So we have the ticker parameter, and here we have to pass the ticker symbol like Apple. Then we have the start parameter and the end parameter, and here we have to define dates at which we want to start and end our analysis. And here we want to analyze the stock Apple from 2015 till the end of 2019. And when running the cell here, we create an instance of the class financial instrument instantiation, and we save the object in the variable stock. And let's simply run here stock. And here we get the information that this is a financial instrument, so Apple from 2015 till 2019. And we can also check the data type, and it's of the data type financial instrument. Now our financial instrument has a couple of attributes and methods. And if we type here stock dot and then the tab key, we can see a drop-down menu here with all attributes and methods. And one attribute is the ticker attribute, and it's no surprise that the ticker symbol is here Apple. And the start date is the 1st of January 2015, and the end date is the last day of 2019. And in addition, we have the attribute data. And here we have a data frame. So we have a data frame with the prices, daily closing prices, and also log returns. So when instantiating our object here, we not only save some properties, like we pass here Apple and the start and end, we also download price data from Yahoo Finance, and we calculate the log returns. So this is all done when instantiating the object here. And now let's go on and let's have a look at some methods. And first of all, we have the method plot prices. And we can have a look inside here with Shift tab. And there are no parameters, so it simply creates a price chart. And now let's call the method. And here we have the price chart for Apple from 215 to 220. And next we can also plot returns. And here we have one parameter kind, and the default argument is TS. So actually plot returns plots log returns either as time series, TS, or histogram. So first of all, let's plot the time series. And here we have the daily log returns. And of course, it's actually oscillating around 0. And also we can create a histogram to have a look at the frequency of returns. And it's no surprise that the highest frequency is around 0. But we have some negative outliers here and also some very positive returns. So this was the first part, and looking forward to seeing you also in part 2. All right, let's continue and let's have a look at some more methods that allow us to further analyze Apple and also other stocks. And first of all, we can calculate the mean return. So the mean of daily log returns. And here we have 0.00077. And actually the same we can also do with the following code. So again, we have the attribute data where we have the data frame with daily prices and daily log returns. And now we can select the column log returns and calculate the mean. So of course we get here the very same result. And again, let's have a look here inside the method mean return. So we have one parameter, frequency, and by default we calculate the mean daily return, but we can also pass a specific frequency like weekly or monthly. So let's pass here W for weekly, and by doing so we calculate weekly mean returns, so 0.0037. Next, we can also calculate the risk of the stock and actually calculate the standard deviation of returns. And here we get a standard deviation of daily returns of 1.5%. And also here we can select a frequency, so whether the risk should be based on daily returns or weekly returns or monthly returns. And the standard deviation of weekly returns is 0.03. And finally, we have the method annualized performance. And we don't have any parameters here. And this method calculates the annualized return and risk. So we have here an annualized return of 19.5% and an annualized risk of 24.9%. So this was a short analysis of the Apple stock. So with only a few lines of code, we actually visualized the prices and also the returns, and we calculated the returns and risk and so on. And now we can also change the ticker and analyze another stock, for instance, GE, General Electric. And we can change the ticker with the method setTicker. So here we can set a new ticker and we pass GE. And by doing so, as you can see here, we download the GE data from Yahoo Finance. And now the ticker symbol is GE, and we can also plot the prices. And here the graph looks a bit different. So there are some problems with the GE stock in the recent past. And also we can calculate the annualized performance, and it's no surprise that we have a negative return of minus 15.7% and a quite high risk of 29.8%. So also switching from one instrument to another is pretty simple. And this was the financial instrument class. And of course, the way how it works does not come out of nowhere. So we have to define attributes and methods in the class itself. And that's exactly what we are going to do in the next lectures. So hope to see you there. Bye. All right, in this and the next lectures, we will define and build our financial instrument class step by step. And we start defining a class with the keyword class. So it's turning green, and this is an indication that this is a keyword, and followed by our desired class name, like financial instrument. And actually it can be any name. However, there are some rules and some conventions. So for example, white spaces are not allowed. And in cases where we have too many words in the class name, we shouldn't use a separator like underscore. So we shouldn't use that, and that's the convention here. And also typically we use a title case, and that means that each word starts with an uppercase letter. So financial starts with an uppercase F, and instrument with an uppercase I. So that's the convention. But theoretically, you can do that in a different way and use lowercase letters here. Finally, let's add some empty brackets and a colon, and then press the Enter key. And similar to user-defined functions, Python automatically creates an indent here. And then we can start defining attributes and methods for our class. And now the most simple class is just do nothing. And we can define do nothing with the pass keyword. So this is a keyword. And now let's run the cell here. And by doing so, we have actually created and defined our very first class, financial instrument. And then we can instantiate our very first financial instrument object. And for example, we can use the variable name stock. And we can instantiate with the financial instruments. And let's simply run the cell here. And let's print stock. And here we can see that this is an instance of a financial instrument. So we have successfully created an instance. But of course, we have absolutely no functionalities here for our financial instrument class. So we have no attributes and also no methods. But this is the very first step here. And now let's copy here the definition and let's remove pass. And typically when creating an instance of a class, at least we want to assign some very first specific properties to our specific object. So properties that are specific to this object, for example, the ticker symbol of the instrument like Apple, or the specific time period for which we want to further analyze the instrument. And we can do this with the special method init. And we can define a method with the def keyword, like a user-defined function. And then we have a double underscore init, double underscore. And in short, this method is also called dunder init, so double underscore init. And actually, dunder methods are also called special methods. And we will cover 2 or 3 of them in this course. And the special method, the dunder init, is a so-called initializer. So it initializes some very first properties of our object once the object has been created. And whenever we define user-defined functions or methods, we can add some parameters here within the parentheses. And actually, methods are typically called on the specific object itself. And therefore, the very first parameter is always the self parameter. And many students struggle with self, so they ask, what is self? Now, when defining methods that can be called on specific objects, we have to start with the first parameter self. That's simply the rule, and that's how it works. And I guess this is getting more clear in this and also the next videos. So immediately after the instantiation, we call the initializer method init on the object itself. And actually, we want to have the following additional parameters. So we are interested in the ticker symbol, in the start date, and also in the end date. So these are the 4 parameters of our special method here. And let's continue with a colon. And then we can define what will happen when we actually initialize our object. And we have seen before that a financial instrument object should at least have some attributes. So stock.ticker should return the ticker symbol, and stock.start and stock.end should return start date and end date. Now, in our examples here, we use the variable name stock, but of course, this is flexible, and therefore we have to use the self. So the object, the name itself, and the first attribute should be ticker, and the value of the attribute should be the value that we pass here to the parameter ticker. Then second, we have the attribute start. And it should be the value that we pass here to the initializer. And finally, we have the attribute end. And with this, we have successfully defined some initial properties. And now let's define the class. And again, let's create a first instance. And if we go here inside the parentheses, then we can see that we have 3 arguments that we have to pass to the parameters ticker, start, and end. And for example, we can use here Apple, then a start date like 2015, January the 1st, and an end date, so 2/19, and the very last day. So whenever we have an initializer method with some parameters, then we have to pass here values to the parameters. Otherwise, we cannot instantiate our object. So let's run the cell here. And we have stock here. And then we can also access the attributes ticker, start, and end. So let's press here dot, and let's press the tab key as well. And here we have a drop-down menu with the available attributes, ticker, for instance, and we get Apple. And also we have end and start. And maybe already here it's getting more clear what self actually is. So to say it's a placeholder for the variable name that we use. So when using the variable name stock, we have the attribute stock.ticker, and here in the class we define this in a more general way, self.ticker, self.start, and so on. So with the special method in it, we initialized some first properties, ticker, end, and start, and still we do not have any functionality here for our class, but this will change in the next lecture, so hope to see you there. Bye. In this lecture, we are going to create our very first method, the getData method, and getData should retrieve stock price data for our instrument for the specified time period from the start till the end date from Yahoo Finance. So we will use the yfinance library here. And first of all, let's remember how we can retrieve data from yfinance. So we can do this with the download method. And essentially we have here 3 parameters, tickers, start, and end. And here we can pass Apple from 2/15 till 2/19. And if we run the cell here, then we get open, high, low, close, adjusted close, and also volume data. And very often it is the case that we are only interested in daily close prices, and therefore we can select here the column close. And if we only select one column, then by default we get a panda series. And we can convert a panda series to a data frame with one column with the method toFrame. So this is not a problem at all. Now this is a data frame with raw data for Apple, and we can also store the data frame in a variable, like for instance raw. And it definitely makes sense to rename here the column label from close to price. So this is the stock price. And we set in place to true to actually override the object that is stored in raw. And let's have a look again. So now here we have the column label price. And actually this is the functionality that we want to add to our class as the method getData. So let's define the method with the def keyword. And we use the method name getData. And we don't have parameters here. And actually it's pretty simple to adopt the code here above to a method. So first of all, let's copy and paste this line here. So here we download prices for Apple and save it in the variable raw. And then we change the column label. And there are only minor things that we have to adjust here. So instead of having Apple, we want to pass self.ticker to download. And instead of having here the start date, we have self.start. And finally we have self.end. So we use the attributes ticker, start, and end to actually download price data for the ticker from start till the end date. And that's actually all we need to do here. So let's define again the class financial instrument. And let's call it again. So let's copy here. And still we have the attributes available. And now we can also get the data with the method getData. So here we can see now we have the method getData. And we can simply call the method. And now we get here a very typical error. So the type error getData takes 0 positional arguments, but 1 was given. So this is a very typical error for beginners. And the reason is that we actually called the method getData on the object stock itself. And we actually forgot here the parameter self. So whenever we define a method that can be called on a specific object itself, then at least we have to add one parameter. It's the self parameter. So let's redefine here our class. And then it should work. And as you can see, we don't get an output here, but we can change this with return raw. And let's have a look again. And here we have our raw data with the price data. But it actually makes more sense to store the data frame here as an attribute. So let's create the new attribute self.data. And we pass our data frame raw. And then we can actually access the data frame with the attribute data. And here we have. Now there's one last thing that I want to show you. And it would be great if actually our class automatically downloads the data at instantiation. And now we can do the following actually. We can say that we want to call the method getData when we instantiate an object, and therefore we can add self.getData to the init method. So this is pretty simple, and this works, self.getData. So whenever an object is instantiated, then initially we create the attributes ticker, start, and end. And we retrieve the price data from Yahoo Finance. So let's rerun here the definition. Already here you can see that when we instantiated the object stock, then automatically the data gets downloaded. And now we have available the attribute data. And here we have the price data. So this is pretty cool and pretty powerful. Thanks for watching, and see you also in the next lecture. Bye. In the last lecture we have seen that we can call a method in another method. That's totally fine. So we call the method getData whenever the special method dunder init is called. So directly after the new object is instantiated. And now let's have another example. And first of all, let's recall that getData creates a new attribute, self.data. And of course, we can also access the attribute data here. So that's the data frame with the prices, the daily close prices. And now the plan is to add another column to self.data. So log returns with the daily log returns. And we can do that by introducing another method, the log returns method. And again, we can do this with the def keyword. And we shouldn't forget self. So we don't have any parameter, but at least we shouldn't forget self, because we can call the method logReturns on the specific object itself. And what logReturn does, it actually adds another column logReturns to self.data. So this is self.data with one column, and we add another column logReturns. And the calculation is pretty simple, and it should already be familiar. So we divide the price by the shifted price. So we have self-data.price divided by self-data.price.shift by one leg. Now let's again redefine our class financial instrument, and let's instantiate with Apple and this period here. And let's have a look at data. So we have only the price, but now if we call the method logReturns, then we add another column with the daily logReturns. And also here it might be more convenient to add the logReturns automatically when we instantiate the object. So we are fully flexible here, and we can add this to the init method, to the special method init, and we can say that please run the method logReturns here. So let's again redefine our class, and let's instantiate the object stock. And let's have a look at the data attribute. And already here we have the logReturns. So we have the price and also the logReturns automatically when we instantiate a financial instrument object. And with this, there's actually no need to call the method logReturns explicitly. So it's already called here when our object is instantiated. That's pretty smart actually. Thanks for watching, and see you also in the next lecture. Bye. We are coming now to another special method, the double underscore wrapper, and wrapper stands for representation. And with this special method, we can determine how an instance of a class is represented when displayed or printed. This sounds complicated, but let me give you an idea why this can be helpful for users. So we still have the object stock, and that's actually the instrument Apple from 2.15 till 2.19. And if we simply display the object, then we get a rather technical representation. So stock is an instance of the class financial instrument. And we can actually also see here the memory position of the object. And that's not really helpful. And also if we print the object with the print, then we get more or less the very same representation. So for a user, that is not really helpful and not really intuitive. And it would be better if we could see at a glance that it's Apple and maybe also the time period. And that's exactly what we can do with the special method wrapper. So let's add here def double underscore wrapper, and again double underscore. And then we have one parameter, it's the self parameter, so we shouldn't forget that. And then we can say that if we display or print the object, then Python should return the following string. So we are actually pretty flexible and free here, and maybe the following makes sense. So we have here a financial instrument. And this instrument is determined by the ticker. And let's have a placeholder here, curly brackets. Then we have the start date and another placeholder. And finally, we have the end date. And this is the string representation for any object of the type financial instrument. And we have 3 placeholders, and let's create here a string replacement with format. And here in the first position, we want to replace this with the ticker symbol that is saved in self.ticker. Then we have self.start. And finally, we have self.end. So this should work, and let's redefine our class. And let's create an instance, so Apple from 215 till 218. And let's display the object. And here we can see immediately that this is a financial instrument, and it's Apple from 215 till 219. And the same we can also see with the print. So to sum up, creating customized string representations isn't required, and it doesn't change or improve functionality of our class. However, it improves the user experience, as the users can see at a first glance what is inside the object. So thanks for watching, and see you also in the next lecture. Bye. Sometimes a graph tells more than many numbers, and that is in particular true in finance. So it's always a good idea and also beneficial to create price charts and also to visualize the financial returns. And still we have the object stock, and we can access the raw data, so prices and returns, with the attribute data. And here we get a data frame with prices and log returns. And now we could actually create a price chart by selecting the column price and use plot to create a line plot. So here we have the price chart for Apple from 215 till 220. And of course, we can also select log returns and create a line chart. And actually, here we are plotting the returns time series over time. And it's no surprise that this is oscillating around a return of 0. So to say, here we can see volatility clusters. For example, here in 219, we have more volatility than, for example, here. And there's also another option to plot returns. And it might be also informative and helpful to have the frequency distribution. So to say a histogram, and we can do this with hist, and we have to define the number of bins, for example, 100. So this is the histogram or the frequency distribution, and also here we can see that the highest frequency is around a return of 0%. And actually many theories and formulas in finance assume that financial returns are normally distributed, and with a histogram we can see at a first glance whether this is true or not. At least the histogram is the first indicator whether returns are normally distributed or not. And of course later on we can also perform an hypothesis test to test for the normality. Alright, now it's pretty simple and straightforward to add the plotting functionality here to our class. And we can add two more methods. One method to create a price chart, and it's in the method plot prices. So we have def plot prices. And again, we shouldn't forget self, and that's the only parameter here. And what plot prices actually does, so it selects the attribute data and then selects the price column and creates a line plot. And also we define that the fixed size should be 12.8, and we also add a title here, so it's a price chart. And here we have the placeholder for the ticker symbol, and we have a font size of 15. Last but not least, we define the method plot returns to plot the financial returns. And again, we start with self. And then we have here one additional parameter. It's the kind parameter. So either we plot the time series, so the line plot here, or we plot the histogram. So we can either pass here TS for time series or hist for histogram. And we have here an if-elif statement. So if kind is TS, then we select log returns and create a line plot with fixed size 12.8. And also we add a title, so returns for the respective ticker, so self.ticker, and we have a font size of 15 for the title. And elif if the kind is histogram. Then again, we select log returns and create a histogram with fixed size 12.8. And as a rule of thumb, so the number of bins should be around about equal to the square root of the number of observations. So, and we convert this here into an integer, so bins must be an integer. So we have np.square root and then the length of self.data, so the number of rows or the number of timestamps. And also here finally we add a title, so frequency of returns of the ticker symbol self.ticker. So let's redefine our class here and let's instantiate again Apple. And then we can simply plot prices with the plot prices. And here we have the line chart and the title price chart for Apple. And finally we can also plot the returns. And the default argument for kind is the time series. So here we get the time series, and if we pass hist to the kind parameter, then we get the histogram. Thanks for watching and see you also in the next lecture. Bye. Encapsulation is a fundamental concept in object-oriented programming, not only in Python but also in other programming languages. And it's not just a fancy word. So encapsulation solves a real and severe problem in OOP. And I think it's best to just demonstrate the problem first. So still we have the object stock, and it's the Apple stock. And then of course we can create a price chart. So the Apple stock performed pretty well in the most recent years, from less than 30 to over 70. And actually Python does not prevent us to access attributes. So we can access the ticker attribute and we get Apple. And also changing and overriding attributes is not prohibited in Python. So we can assign a new ticker symbol like GE for General Electric. And this works. So ticker is now GE. However, now if we plot prices, then still we have the price chart for Apple. So we only changed the attribute ticker, but we didn't change the data and the data frame with the prices and the log returns. And this is a severe problem in object-oriented programming. So we can change an attribute without changing the rest. But there's a solution for it. And we can hide and protect an attribute and create a so-called protected attribute. And we can do this by prefixing the name of the attribute with a single underscore. So let's create the protected attribute single underscore ticker. And we have to do this everywhere in our code. So we have it here. Then also here. And here. And finally here. So let's redefine our class and let's create the instance stock. And now if we try to access the attribute ticker, then of course we don't have the attribute ticker. And also if we try to get the drop-down menu here with the tab key, then we can neither see the attribute ticker nor the protected attribute underscore ticker. So the protected attribute underscore ticker is hidden and not visible. And indeed we can say that it is partly hidden and protected from being accessed and overwritten. But in Python there's no 100% protection, and we will see this now. So we can still access and also override underscore ticker if we simply code here stock.underscore ticker, so that's possible. However, the prefix underscore is a clear warning for developers and also for users, so please be careful about this attribute, and it might not be a good idea to just change it. Now we have a protected attribute, but still we want to have the option to change the ticker symbol and analyze another instrument without the need to create a new instance. And actually, encapsulation in a broader sense has two steps. So first, hiding some attributes by creating protected attributes with a prefix underscore. And second, creating an official method that allows us to set new values for the protected attribute. And that's exactly what we are going to do in the next lecture. So hope to see you there. Bye. All right, we have created the protected attribute underscore.ticker. But still we want to have the option to change the ticker symbol, and we can do this with a so-called set method. So it can be any name, but typically we use method names like setTicker for methods that set new values to protected properties. So let's create here a new method, def setTicker. And again, as a first parameter, we have self. And then let's create a second parameter. So if we do not pass any new ticker symbol, then we just have none as the default parameter. So if we call the method setTicker, and if we do not pass a new ticker symbol, then we simply use the old one that is already stored. So let's create an if statement. So if ticker is not none. So if it's none, we actually do not change anything. But if it's not none, then in this case, we want to change the protected attribute self.ticker and assign the new value. And these lines of code allow us to actually override the ticker, but this isn't sufficient actually. So once we change the ticker and set a new ticker, then immediately we want to download and get price data for the new ticker symbol. And also we want to calculate the log returns. So we want to actually retrieve the full new data, and therefore the following has to be done. So once we change the ticker, then again we have to run the method getData. And also we have to run the method log returns. So let's run the cell here and let's redefine our class. And let's create an instance, again, Apple from 215 till 219. And we can plot the prices. So this is the great performance of Apple. And now let's change the ticker symbol to GE, General Electric. And automatically you can see here that we download the price data from Yahoo Finance for GE, and we calculate log returns. So we can plot the prices for GE. And here we can see that GE most recently had some problems. So this performance isn't great. So as you can see, changing private attributes isn't difficult with a set method, but we have to be careful here, and typically we have to change some other things and run some other methods like getData and log returns. So thanks for watching, and see you also in the next lecture. Bye. In this lecture we will add some more methods that allow us to calculate some more performance metrics. And in finance and investments, return and risk are probably the most important performance metrics. So first of all, we have here the method mean return that calculates the mean return or the average return over time. And again, we start with the def keyword, and the name of the method is mean return. And as always, the first parameter is the self parameter. So we can use the mean return on a specific object itself. Then I added here the flexibility to change the frequency. So depending on the purpose, sometimes it's more meaningful to calculate risk and return based on daily price data, and sometimes it's more meaningful to base the risk and return on weekly or even monthly prices. And therefore we have here the parameter frequency, and by default it's set to none. So by default, we calculate mean returns based on daily data. Now we have here an if-else statement, And if the frequency is none, so if we don't pass any frequency, then the method returns the mean log return based on daily log returns. And else if we pass a frequency like weekly, then first of all, mean return calculates resampled prices. So it takes the price column in the self.data and uses the resample method and uses the past frequency. And then it takes the last price. So for example, the last price of the week or the last price of the month. And then in the next step, it calculates the resampled returns. So the resampled log returns with np.log, and we use here the resampled prices. And then it returns the resampled mean returns. So this is the method mean return. And very similar to this is the method standard deviation of returns. So typically the standard deviation of returns is a metric for the risk of the instrument. And also here we have the choice to change the frequency. So if we do not pass a frequency, then the risk is calculated based on daily data. And if we pass a frequency, then once again, we resample the prices first of all, and then we calculate the risk based on resampled prices. So in the first step, we calculate the log returns based on resampled prices, and then we take the standard deviation, and then the method returns the standard deviation of resampled returns. So this is pretty simple and straightforward. And finally, we also have annualized performance. And this method actually returns the annualized return and the annualized risk based on daily data. So first of all, let's have a look at the first line. And here we calculate the daily mean return annualized. So we select the log returns column and take the mean and multiply the mean with 252. So 252 trading days in a year. And then we round the mean return to 3 decimals. And the same we do also for the risk. So we calculate the standard deviation of log returns and multiply it with the square root of 252. So this is how we annualize return and risk. And then actually annualized performance, so the method prints the following statement. So the return is the mean return and the risk is the risk. All right, let's run the cell and let's define the class. And let's create a new instance. And then we can calculate the mean return. And by default, it's the mean return based on daily data. But we can also select the mean return based on monthly data, so the monthly return. And it's no surprise that the monthly return is higher. So we have here 1.6% per month. And the very same we can also do for the standard deviation of returns, the risk. So by default, we calculate the standard deviation based on daily data. And we have here a risk of 1.5%. But of course, we can also change to weekly, monthly, or even yearly or annual. And we get here a monthly standard deviation of 7.5%. And as I said, we can also change mean return and standard deviation to weekly or also to annual with Y, or I think even A works. And this is true. And finally, we can calculate the annualized performance. And we get here a return of 19.5% and a risk of 24.9%. So these are a few examples of performance metrics. And of course, there are many more. So feel free to add some more methods that calculate another or additional performance metrics. Thanks for watching and see you also in the next lecture. Bye. All right, we have now a pretty nice financial instruments class that helps us to retrieve price data from the web and to calculate log returns and visualize the prices and returns, and also to calculate the mean return, the standard deviation of returns, and also annualized return and risk. And sometimes it is desirable to split one larger class into several smaller classes to have a more modular structure. And also here in our example, it could make sense to have a financial instruments base class with the very basics like retrieving the data, calculating log returns, and visualizing prices and returns. So that's the very basics and the starting point for many other workflows, like calculating risk and return or calculating alpha and beta for the stock or whatever. So let's create two classes here, one base class with the basic functionalities like getting the data. So we have here financial instrument base class, getting the data, calculating log returns, and plotting prices and returns, and setting the ticker. So let's define the base class here. And then we have another class, risk and return. And the major functionality is here below. So here we have the method mean return, then a standard deviation of returns and annualized performance. But unfortunately, we have to copy and paste all other methods as they are the prerequisite to calculate risk and returns. So we have to rewrite major parts of the code twice. So here we have all methods that we also have in our base class, like getting the data, log returns, and so on. So theoretically, we could delete here plot prices or plot returns, but at least we require get data and log returns. So this is not really efficient, but it works. And let's define here risk return, and let's create an instance, for example, Apple, and we save for the object in stock, and then we can call one of the major methods like annualized performance. So this works, but it's not really great. And here comes the concept of inheritance into play. So inheritance allows us to create a class that inherits the functionality from another class. And the only thing that we have to do, we have to pass the parent class. So in our example here, the financial instrument base class is the parent. And risk and return is the child class. And we have to pass the parent class to the child class. So we pass here financial instrument base class. And with this, the child class risk return inherits all properties and all methods from the parent class. So we can actually delete all methods that we also have here in the parent class. So essentially, we can delete all methods except mean return and standard deviation of returns and annualized performance. So let's redefine the class risk return that inherits the class financial instrument base. And let's again create an instance. And again, you can see here that we download data. So the class risk return still uses the method of the parent class, so getting the data. And of course, now we can also calculate the annualized performance. And if you have a look at the available methods and attributes, then we can see that we have all methods and attributes available that are either in our child class or in our parent class. So we can get the data, the raw data, with prices and log returns. And also we can get, for example, the prices. We can plot the prices, so this is no problem. And also we can change the ticker by setting a new ticker like GE. And then we can update here our plot. And this works pretty well. Now there's one drawback, and let's just display or print our object, the stock. And here we get the string representation of the parent class, so financial instrument, and that's not really true. So our object stock is actually an instance of the class risk return, and the problem is that risk return also inherits the dunder representation method, and this doesn't really make sense. And therefore, we should redefine this in our child class. So we define here our own string representation. And this could be, instead of financial instrument, this could be a risk return. So let's redefine here risk return. And let's again create an instance. And again, we can calculate the annualized performance and many more things. And finally, let's have a look at the string representation. And now here we get the representation that this is an instance of risk return for Apple. So what happened actually is that the child's representation method overrides the inheritance of the parent's representation method. And the simple rule is, so if the child class has a method with the very same name as the parent class, so here we have the very same method, dunder wrapper, then in this case, the child's method overrides the inheritance of the parent's method. And actually, the child's method prevails. So here. So as a final remark, sometimes there are good reasons to use inheritance. And in particular in cases where we have a base class that introduces some basic workflows that are required for many other workflows. And then we can inherit this base class to other more specialized classes, like the risk return class, or the alpha beta class or whatever. And this can, for example, improve readability and user experience, as users directly see what they get when using specialized classes like risk return or alpha beta. And there's one last thing that I want to highlight here. So if you have some first experience with OOP, you might have asked yourself why we used the empty brackets here when defining the financial instruments class or the financial instruments base class. So as long as the class does not inherit from other classes, we actually don't need the brackets, so we can just delete them and define the class. So that's perfectly fine. But in my view, it's a more general approach to always use the brackets, even if they are just empty. And in all cases where we have empty brackets, we simply don't inherit from other classes. All right, this was a short introduction to inheritance, and I hope that this was helpful. Thanks for watching, and see you also in the next lecture. Bye. All right, this lecture is all about inheritance and the super function. So if you Google the super function, you may find many explanations and examples that are highly technical. So this topic seems to be a complex one, but in reality it isn't that complex. And it's actually best to start with a real-world problem that we can solve with the super function. And still we have here our parent class or base class financial instrument base. And a parent class is also called the super class. And then, so let's run the cell here. And then we have the child class risk return, which is also called the subclass. And we've already learned that the subclass inherits from the superclass. So we pass here the superclass financial instrument base. And now we have here two methods, the mean return method and the standard deviation of returns method. And we can set a frequency here in both methods to determine whether mean returns and also the standard deviation of returns should be based on daily data, weekly data, monthly data, or whatsoever. And now let's assume that we want to set the frequency already when instantiating a risk return object. So when creating an object, we want to decide whether mean returns and the standard deviation of returns should be based on weekly data, monthly data, or whatsoever. Then in this case, we need to create and call a dunder init method also here for the risk return class, and also create a new attribute, self.frequency. So let's do this here. So we define the dunder init method. And then let's copy and paste the parameters of the parent's dunder init method. So ticker, start, and end. And also we create a new parameter or argument. It's the frequency argument. And if we do not pass anything here, so by default it's none. And then we create an attribute. So the self.frequency attribute. Then next we have to slightly change a couple of things. So now we have the frequency already stored in an attribute. So we don't have to pass it here in the methods. And if self.frequency, and also here self. And the same also here for the standard deviation of returns. And also here. So this is the naive approach, and let's have a look if it works. So we've already defined the parent class, and let's also define the subclass. And let's create an instance, risk return, and we pass Apple, then the start date, the end date, and in addition to that also the frequency, weekly frequency. And already here we can see that obviously we haven't downloaded the data from Yahoo Finance, but obviously we can access the frequency attribute. And now let's try to do the same for the protected attribute underscore ticker. And here it says that the object has no attribute underscore ticker. And let's also try to access the data. And also here the risk return object has no attribute data. And it seems that we haven't initialized the properties that we actually want to initialize here in our parent class. And obviously we haven't set the underscore ticker attribute. And also we haven't run or called the get data method. And the problem here is that we haven't called the dunder init method of our superclass. So to say, this was overridden by the dunder init method of our subclass. But there's actually a solution for it. And we can use the super function. And the super function gives us access to methods in the superclass. So in the financial instrument base class from the subclass here. So with the super function, we create a temporary object of the superclass. And then we simply have to call the dunder init method. And we pass here the arguments. So we have ticker, start, and end. And this should work. So this is all. Now let's redefine here our subclass, risk return. And let's again instantiate an object. And already here we can see that we have successfully downloaded data from Yahoo Finance. So we can access the frequency, which is weekly. And we can also access the ticker attribute, and it's Apple. And we can also have a look at the data frame with price and log returns. And then we can also plot prices and calculate the mean return. But now here we don't have any choice. So the setting is weekly. And finally, we can also calculate the annualized performance. So as a summary, whenever we have a superclass and a subclass that inherits from the superclass, and whenever we want to initialize some properties in the subclass, then we have to use the dunder init method. And actually the dunder init method overrides the dunder init method of the parent class. However, we can call the dunder init method of the superclass with the function super. And this is all you need to know about the super function. Thanks for watching, and see you also in the next lecture. Bye. We are coming now to another important topic, docstrings, and for developers, creating docstrings is typically an unpleasant and time-consuming task that doesn't improve the functionality of the class and its methods, but it's really helpful for users and also co-developers to understand what they're actually doing. And docstrings are like a written manual that guides users through the purpose and the functionalities of classes and methods. And we as developers are free to write whatever we want, but it should be concise and understandable for external users. So let's have an example, and we have our financial instrument class with all methods, so also the return and risk methods. And let's define the class here. And now if we create an instance with financial instruments, then we can go here inside with Shift Tab, and we can see that there's no docstring available. So an uninformed user might not really know and understand what the financial instrument is doing. So let's create stock. And also if we call methods, then we can go here inside and have a look with Shift Tab. And also here we have no docstring. And we can only see here in the signature that the method has one parameter, and the default argument is TS. And also here an uninformed user might not really know and understand what's going on here and what the options are for the parameter kind. So it's definitely a good idea to add here some docstrings, and let's add a docstring to the method plot returns. So let's go here above. And let's change the mode from code to markdown to actually add a text here. And actually we have to create an indent here. And now we can start with our docstring, and actually docstrings always start and end with triple quotes. And then we can start writing, and for example we can write the following. So the method plot returns plots log returns either as time series, short TS, or as histogram, short hist. And finally we have to close our docstring with triple quotes, and typically we move this to the next line. So now it's getting clearer that this is the docstring here. And let's turn again to code. And here we can see the docstring in red. So this isn't a code, and this isn't part of the code. This is just the text, the docstring. And let's again define our class here. And let's create one object. And now if you want to plot returns, we can go here inside. And here we can see our docstring. So the method plot returns plots the log returns either as time series, TS, or as histogram, hist. Now we can add docstrings to methods, but we can also add docstrings to the entire class. So let's add a docstring to financial instruments to describe and explain what the financial instrument actually does. So let's go here above, and let's again switch here to markdown mode. And let's create here an indent. And then we start with triple quotes. And then we can write, for example, the following. So the class financial instrument is a class to analyze financial instruments like stocks. And let's go to the next line and let's close the triple quotes. And let's switch again to code. And here we can see that this is here text, so a docstring. And let's again define the class. And let's create an instance and let's go here inside. And now here we can see that the financial instruments is a class to analyze financial instruments like stocks. So these were just two simple and short examples how to create docstrings from methods and also for the class itself. And actually the level of detail depends on the complexity of classes and methods and also on the target audience. So if you are planning to create a new library for the wider public and for completely uninformed users, it should be more detailed. But in our case, we are among us and you are definitely an informed user. So less details are appropriate here. And also our class and methods aren't too complex with only 1 or 2 parameters per method. And let's have a look at a final example here. So here we have a more detailed docstring for the class. So it's a class for analyzing financial instruments like stocks. And then we can have a description for all attributes. So for the initializing attributes like ticker, start and end, and also for the methods. And here we close the docstring. And then for each and every method, we could have a rather short docstring like get data, retrieves and prepares the data from Yahoo Finance, or calculates log returns, creates a price chart, and so on. So these are just the simple examples, and typically for libraries that are publicly available, you can see more detailed docstrings, which is okay here. So thanks for watching, and see you also in the next lecture. Bye. Alright, we have here the final version of our financial instrument class, and we defined the class here in our Jupyter notebook. Now in case we want to use the class in other notebooks, we have to copy and paste the class definition to the new notebooks, and that's not really convenient. And it's best to just import the class like we import NumPy or Pandas. And actually it's pretty easy and straightforward to create a Python module in .py format with the class financial instrument and import the module and the class. And one option is to convert here the Jupyter notebook into a Py file. And we can do this here with download as python.py. And let's save the Python module in part 2 materials in the video lecture notebooks. And let's give a name to the module. And for example, we can use and choose a financial instrument. So financial instrument is the name of the module, and it's a Py file. And let's click on save. And now let's have a look here at our folder. And here we have now the Py file financial instrument.py. And actually we can also now open the file. And we should delete most of the cells here. So we only keep the import of some libraries like Pandas and YFinance and so on. And the definition of the class financial instrument. So here we are just left with importing some libraries and packages and the final version of our class. And now we shouldn't forget to save the file here. And now let's go back to our current directory. And now here we have financial instrument.py. And now let's create another Jupyter notebook where we will use the financial instrument module and import the module. So let's import financial instrument. And then we can also define an abbreviation. So we can import financial instrument, for example, as FI. And let's run the cell here. And we have successfully imported FI. And now let's create an instance or an object of the class financial instrument like stocks. And now we can do the following. So in the module FI, there's the class financial instrument. And let's have a look inside here. So here we have to pass a ticker, for example, Apple, and a start and end date, for example, 2015, January the 1st, till 2018, January the 1st. And now let's run the cell and let's create the object stocks. And it worked. So now we have here stocks. And we can also have a look here at the data. And here we have prices and log returns for Apple. So this was a short introduction to Python modules. And again, it's important to notice here that this only works because the Jupyter Notebook where we are coding in and the Python module are in the very same location, so in the current working directory. And you should make sure that this is the case. Otherwise, it's not that simple to import here the module financial instrument. So thanks for watching, and see you also in the next lecture. Bye. Hi and welcome to the third coding exercise. Here you will have the opportunity to create a class from scratch, the rectangle class. And this here is a rectangle, and a rectangle has 4 right angles and 4 sides. So 2 short sides with the length A and 2 longer sides with the length B. And then with the following formulas we can calculate the area, the perimeter, and also the diagonal. So the area, the shaded area here, is simply A times B. Then the perimeter here is simply 2 times A plus 2 times B. And finally we have here the diagonal, and we can calculate the diagonal with the square root of A squared plus B squared. Now first of all, let's see the rectangle class live in action before you will create the class from scratch. So I've already imported NumPy and I have defined the rectangle class below. And let's create an object here. So let's go here inside, and this is the rectangle class. And we have 2 parameters, A and B. And here we have to pass numbers, for example, 3 and 4. And we save actually the resulting object in a rec. And here we can see that this is a rectangle object with A equals 3 and B equals 4. And then we can also check the attributes. So let's first of all type here rec dot and let's press the tab key. And here we have the methods and attributes area, calculate diagonal, calculate perimeter, and set parameters. So we don't have the attribute A and B. And actually the class is defined in a way that we have the protected attributes underscore A and underscore B. And here we have 3 and 4. And also we have the attribute area. So this is simply 3 times 4 is 12. And there's also a second option to get the area. And there's the method calculate area. And of course we get the same result, 12. So it seems that the method calculate area is called already at instantiation, and the result is saved in the attribute area. So keep this in mind. And then we have another method. So we have calculate diagonal, and here we get 5. So this is simply the square root of 3 squared plus 4 squared. So actually 9 plus 16 is 25, and the square root is 5. And then we can also calculate the perimeter. So it's 14, 2 times 3 plus 2 times 4. And then we can also change the values for A and B with the method set parameters. So we have here the default arguments, none. But if we pass here 5 to the B parameter, then we set B to 5. And now we have here a rectangle with a equals 3 and b equals 5. And actually, when we run the set parameters method, we automatically recalculate and update the attribute area. So now the area is 3 times 5 is 15. And finally, we can also calculate the perimeter, which is 16. So this was the rectangle class live in action. And now it's your turn to actually create and define the rectangle class. And there are actually two options. So either you create the rectangle class without hints, or there's also a second option, so some help. And you can have a look here. So if you want to do the exercise now on your own, then please stop the video, because I will continue now with the solution. All right, now let's go on, and here we have the second option, and here we have some help, so we have the methods. And now let's go to the solution. So first of all, we need NumPy, because we calculate later on the square root with np.squareroot. And then first of all, we have the dunder init method, where we initialize some properties. And actually, we have here two parameters, a and b. And we save those parameters in the protected attributes _a and _b. And then we also run the method calculate area. So we will have a look at this method in 2 minutes. But first of all, we define a string representation, and we could define the following statement. So this is a rectangle with a equals something and b equals something. And we replace here the curly brackets by self.a and self.b. And then we have the method calculate the area. And actually the area is simply a times b. And we save the area in the attribute self.area. And also we return the value here when calling the method. Then next we have the method calculate perimeter. And this is simply here 2 times a plus 2 times b. And we return the value. And finally, we have the diagonal, so calculate diagonal. And here we simply return the value of the diagonal. It's the square root of a squared plus b squared. And finally, we have the option to set new values for a and b. And we have the default arguments none. And if we do not pass any value for a and b, then we take the existing values. But if we do pass new values, so if a is not none, then we override the protected attribute a, and we pass here the new value. And then we also call the method calculate area and update the attribute area. And for b, it works in the very same way. So if we pass a value to b, then we update _b and recalculate the area. So this was the coding exercise on object-oriented programming and classes. And if you have any problems or further questions here, then please let me know and write on the Q&A board. So thanks a lot, and see you in the next lecture. Bye.